CAT interviews at Uber, Confluent, Indeed, and many more companies. I have seen it all. After countless hours on the other side of the table, I know exactly what top companies are looking for, especially in LLD. In this course, I'll share the insider blueprints, what to focus on, especially key design patterns, how much multithreading, very important, counter question, traps, and how to tackle them confidently. This course is structured, practical, and tailored on what companies are looking for right now. Let's get you interview ready right now.
Now, continuing ahead with one of the most important concepts, which obviously in today's world you should be knowing, is concurrency. Now, again, we will primarily see in Java, although there are many concepts which you can apply literally anywhere about threads, about how synchronization locks actually work, Semaphore and stuff. But their like entirely syntax will be Java related, and obviously with that we'll also see Leetcode questions for it, and then we will apply all these concepts in LLD plus concurrency Leetcode problems. Now, in this crash course, you will literally see a lot of stuff. Very big disclaimer that please watch the entire video and then decide, did you get this concept or not. In the very beginning, it will be hard. You will see, Aaron, there are a lot of stuff which I don't know, because it's a cyclic behavior of concepts. For threads to showcase how they are working, I will have to showcase, let's say, runnable, callable. For callable, you should know about futures, or like computable futures. For that, you should know about threads. So it's a cycle, which means that the entire video should be completed before you can jump on to conclusion that you got the idea or not. Okay, with that said, I'll tell you what exactly we'll cover in this entire crash course. We'll cover about threads, runnable and callable. Then obviously we'll discuss about thread pool and thread lifecycle. Now you might obviously can start asking that, are in thread lifecycle after covering callable? Yes, because obviously we want to cover same and similar things in one go. Obviously there will be a lot of concepts like block state, running state, which I will be telling, although I will be explaining their actual inferences like a 5-year-old as well, but still the sequence is very consciously written like this. And again, that's the reason I told you that you have to watch the entire crash course to figure out if you got the video or not. Now, next we'll discuss about thread executors. This is very important. Then we will see about thread synchronization. Then we'll see thread communication. Then we will see obviously locks and type of locks. But you will see that in the entire portion we will be discussing about locks. But still, actual locks we'll be discussing. Okay, what type of locks are there in Java and how to use them? It's very important to know about them. Then we'll discuss Semaphore, one of the very favorites for the folks who have been solving Leetcode questions. They know that it's very favorite for them. Then again, the beauty of Java is that all of this becomes much more simpler in comparison to C++, and that was the prime reason. Again, if you haven't watched the first video of the series, which is regarding introduction, please go and watch this video. Then you will realize that why exactly we have taken Java for covering our LLD. Then obviously we'll discuss Java concurrent collection. This is one of the favorite things of mine in Java. Like, they are such a beautiful collections. Oh my god, I just love them. Now, next we'll discuss future and CompletableFuture. These are very important as soon as you start writing any of the code which is a bit next step. Obviously in these codes you will not use futures or CompletableFuture, but as soon as you will start writing the LLD code, which we obviously want to focus on, because nowadays, if you don't know, the interview bar has gone a bit higher and people are expecting you to know concurrency and also solve these questions. Now again, whenever I say I will teach you concurrency concepts here as well, you can easily apply those concepts in previous LLD problems as well. Obviously, for elevator, booking multiple, or basically calling multiple elevators concurrently, car rental system, booking multiple cars concurrently, vending machine, multiple people trying to access at the same time. Again, although it doesn't happen, but still maybe. So all of these logics can be applied, can be, we can say it's backward compatible to the previous thing which we have seen already previously. Now, after discussing the core concepts, again, this is going to be a big video, so no worries. Then we will discuss some very important Leetcode questions on concurrency and multithreading. Now, why specifically I have chosen Leetcode questions? Because I want to give you a quick, small idea on how to write code, how to write only concurrency specific code and how to make sure. Although, when you will be going through, entirely of this thing, you will be pretty much perfect to literally write write any code, because in this portion only, we will discuss a hell lot of examples, like literally a hell lot of examples, and I will show you a hell lot of code in this portion only. So you will be very perfect in actual concurrency and multithreading in this portion only. And again, I am repeating, I will not teach literally everything here, because let's say if I have logs, I'll not teach you stamped logs. Obviously, I'll teach you read write log, I'll teach you reentrant log. But obviously, I know what exactly is important for you. I know that there is literally a hell lot of stuff, but I want to cover the most important part, which you will obviously 99% cases you will encounter everything from this course. With that said, let's start off with the basic thing, which is threads. Again, I have referred Java threads, but again, you can just assume that threads as well. But I highly recommend, if you have been following the entire LLD series, that's a part of this. And obviously, that's kind of saying that in any interview where you are encountering any questions regarding concurrency and multithreading, this is a video for you. Again, the intro itself is very big, but no worries. The video itself will cover literally everything. Why I'm stressing on that is when I was back 1.5 years back, when I was learning multithreading, I literally struggled a lot, and I don't want you guys to struggle it. Cool. Now let's start off. Obviously, we have threads. Now, threads are basically a fundamental unit of execution, and it allows your program to allow multiple tasks concurrently. Obviously, it's a straightforward definition, but imagine that you have some task, let's say baking. Now you have to bake cookies. This is a task. So obviously, there's a program you can write to actually bake the task. And let's say you have your mother, your mom will actually bake the cookies. She is the only one who will bake it. So basically, for this entire process of baking the cookies, your mom is the actual thread who will bake those cookies. So the actual thing, again, on a high level, you can say that these cookies are being baked, but the actual thing which is actually handling the process, the main thing, the fundamental execution, unit of execution, that is my thread. And the best part is that it allows the program to perform multiple tasks concurrently. We will see how, but yeah, that's the best part, which means I can utilize multi-core processors efficiently and improve my application performance. Because obviously, if you're able to utilize your cores, when I say cores, imagine that you have a 4-core processor, which ultimately says I can run 4 threads concurrently. Does it mean that only 4 tasks can run parallelly? No. So whenever I say I have 4 cores, I am saying at a specific point in time, I can run only 4 threads. But what happens is that we do context switching. One thread will come up, do its work, go. Other thread will come up, but at a specific point in time, only 4 threads can actually work. And because 4 threads can actually work, imagine that you have this cookie making, right? Baking the cookie. Right now, only 1 thread. Your mom is actually working on it. But what if you and your sister joins in? Now 3 people are actually making your process entirely fast of making these cookies. And thus, more the cores, it is much beneficial. You can perform multiple tasks, because obviously this is one task, baking the cookie. Obviously, you have to, let's say clean the room. Now, when I say clean the room, you have to clean the ceiling, you have to clean the nets, you have to clean the floor, you have to clean the table. So obviously, there are multiple tasks here. So obviously, I can incorporate multiple threads also here, right? So that's the reason. Obviously, multi-core actually helps us to utilize that and improve the performance, because if there are multiple people working just to clean the room, obviously the room will be cleaned much faster, and that is the performance benefit. Now, whenever I say performance benefit, obviously I should make sure that you know the difference between a process and a thread. Because again, although you might have now seen that basically a thread is the fundamental unit of execution, and a process basically will have a corresponding thread, but it is much more important that you understand with the actual terminology. And as I was mentioning, that baking the cookies, it's a process, it's a whole activity, and it will involve many things, getting ingredients, mixing, baking everything, and so on and so forth. But a thread is basically doing one step in the process. Now, a thread can do literally all the process, but then it has to do sequentially. Because again, a thread can only perform one thing at a time, right? Your thread can only perform one thing at a time. So the thread can only do one thing. So that's the thing. So I can do one step in that baking process. Maybe I can do mixing the dough. Maybe I can do putting cookies on the tray and so on and so forth. But I can also do multiple steps, which means I can use multiple threads at the same time in just one baking process. So baking is actually a process, and in that, basically in the process, although I can just use one thread to step by step go on to every step, or I can do multiple steps at the same time by using multiple threads. For example, you mixing the dough, and let's say your sister preheating the oven, and let's say your mom getting the corresponding ingredients. So you see that how you are literally, your sister, your mom actually now are threads in this entire process of baking the corresponding cookies and performing the job. And it is not important that you, like, let's say if you and your sister would not have been there, your mom could have still performed it, but obviously it would have taken more time, because firstly she will get the ingredients. When it is done, then she will mix it. Then when it is done, then she will go and put the oven to preheat. So she will have to perform all this tasks by herself. But now, because you have threads, because you have multiple threads, you, your sister, and your mom also is also a thread, so now with that, you can actually fast track this baking process of cookies. Now, with that analogy in mind, let's start off with seeing the basic concrete differences. Now, why I actually focus on both practical and theoretical is because in an interview, you can explain this analogy, but you have to still give a one-word answer. This is called as that you should know what exactly is a one-word answer. Although you understand it, it's good, but you have to give a one-word answer. And I will tell you why exactly is this beneficial. Because you might ask, Aryan, why exactly me and my sister needs to do? My mom also has her friends, right? My mom can ask her friends sitting at their own homes to do the process, right? But that's the thing. That's an overhead. Firstly, there's a lot of context which needs to be given to them, and then bringing up stuff from them obviously actually very difficult, which ultimately gives that they are not in the same memory space. Now, what is that and how it is useful? Let's see that. So basically, a process says it is an independent program with its own memory space, while the thread, it's a unit of execution within a process, and make sure that any of the process will have a thread running. Now, as we said, it has its own separate memory space, and it uses shared memory within the same process. And that is the reason we mentioned, because it is the shared memory. Just imagine the memory as the brain. Obviously, it's the shared space, shared brain, and shared stuff. So it's much more like this person, like, your mom thinks of something and then you do it easily. Like, for example, your mom shows eyes to you, and then you will stop the mixing right then and there. Let's say your mom shows eyes to your sister, like she will let's say like put it in a less heating capacity. So basically, that's the thing, that using that shared memory, it's much faster to do anything. So what happens in a process is it's fully independent resource allocation. Obviously, they are at their own space. They are at their, like, my mom's friends are at their own houses all together. So it's kind of like it's very fully independent. But here in thread, what happens is that it shares resources with the threads in the same process. And because of the sharing of resources, it is much more easier to do the task also parallelly, and also there's no overhead of figuring out what exactly to do, and building cache and all that stuff. Which means that obviously in a process the overhead is very high. Creating a new process is actually resource intensive, while in my threads it's low. Threads are lightweight and quick to create, which means that whenever your mom needs to think of, okay, I'm doing something, I have to call a friend of mine. So like she'll call a friend of mine at a different house. But if let's say your father is there, then she just has to, just say, hey, can you please do this? And then, yeah, it's done. So obviously for threads, the overhead is very low to even make new threads or to use that same memory space. But
For a process, it's high because I have to start everything from scratch. I have to give the entire context to it. I have to give, like the entire resources needs to be regulated separately and so on and so forth. Same way for communication. Inter-process communication is complex, while thread communication is easy, very easy communication, and especially through the shared memory. Imagine that shared memory is the shared practice inside your home. So obviously you will be following a shared practice inside your home, right? But obviously in different houses, they will follow their own practices. So here it's much more easier to give that corresponding context, but it is hard here at different houses. And that's the thing. Same way for isolation. It has very high isolation between processes. The isolation is very low. Threads can directly affect each other. For example, let's say here your mom's friend would have been cooking something, and let's say she had a task to bake something, some portion of the cookie, let's say some biscuit which will be added on top of the cookie. Then let's say her hand got burned. Then obviously until unless my corresponding moms from the moms, like this is the friend of my mom, so from her house, until unless someone contacts back to my mom and say, oh no, this, like, she has burned her hand, she will not know about it, and thus she will continue doing her own process, and there's a high chance that my mom's friend feel like, okay, it's a very small burn and I should ignore it, and I don't need to call my actual friend. So okay, there's a very high isolation because obviously they are separated apart in a different memory space altogether. But if it's a thread, it's a low isolation. For example, your mom burned your hand, every one of you will literally go, oh, what happened mom, what happened mom, and thus literally it can impact every of your fathers, your sisters, yours, and your moms. Like every of the actual process got impacted. Like a thread, like the work which they were doing got impacted, and that's the reason there's a very low isolation. Threads can directly affect each other because they literally affected, right? Because they were sharing the same memory space. Something happened to them, like let's say if the mom got angry, she literally threw something into the cylinder, and then it burst. With the burst, literally the entire memory space all went away. So that can actually, I mean, this is very extreme, but yeah, this is kind of that how it can actually impact other threads. Now, switching cost, expensive context switching. Here it's very inexpensive, and this is what we saw also. Now, failure impact, this is the same thing, that one process crash does not typically affect others until unless we actually want to know. Until unless there's something happened in my mom's friend's house, she will not tell what exactly happened until unless, like, I'm asking, I have built a corresponding TCP connection. I just want every 5 minutes, what's the update, until unless, and again, even if I got to know, I may or may not get impacted. But if something happens in a thread, it can literally crash the entire process. So if something happens to any thread, it can literally crash the entire process. And that is how you can understand about a thread and a process. Now, obviously, this is a small diagram that a process is literally built up of many threads, and they will literally, do their corresponding own jobs. And again, I have given the same context here as well. Now, a quick key differences, obviously the same thing which we saw above as well. This is memory management. That process have their separate memory space. This is very, 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 very important point, and that is what makes the process indestructible. As in, like, when I say indestructible, I mean like they will not impact each other, and that's the same point which makes the inter-process communication very difficult, right? And that's also providing the process strong isolation. They are different, they are different from each other, while the threads within the same process share the memory, and this actually allows efficient data sharing between them, and thus making my context switching much more easier, and all that good stuff. Now, resource consumption, obviously, because creating a process is computationally expensive because it requires significant system resources in terms of memory, in terms of CPU, and all that stuff. Because obviously, you have to give everything separately to it right now. But threads are super lightweight. You can literally create and destroy many threads quickly with minimal overhead. Although, mark my words, there is still a overhead
So it is not that you will keep on making and deleting threads unnecessarily. No, you should not do it, because there is still a overhead. Although it is minimal in comparison to a process, but there's still a overhead. And this is, we will see in the later part of this course, that when I say course, I mean this crash course, that this overhead is actually bit, still expensive for us. That's the reason we try to not make and destroy threads again and again. Now, as you mentioned, the communication can be done between processes, but it's a complex mechanism. We can use pipes, sockets, or message queues to communicate between two processes. But threads can literally communicate directly because they are using shared memory space. Now, fault tolerance, as we also said, that if a process crashes, it will not impact any of the processes. But if a thread crashes, it can literally bring down the entire process, which means every thread inside that specific process will or can be impacted. Again, if I handle it correctly, then probably I might not. But obviously, if they're using the shared memory space, if I just put something in the memory and then it will corrupt it, and then there can be many edge cases here. Now you might ask, Aaron, okay, you told a lot of good stuff, which ideally mean that I should use only threads, never processes, right? I guess this question would not have come in your mind, because we saw that how beautiful are processes because they have a very strong isolation, and how beautiful are threads because they are lightweight and they actually communicate very fast with each other. So both have their own pros and cons. So I'll say the exact same thing, that if you want strong isolation between different parts of your application and you want them to run independently and not impact each other, then use processes. For example, you have web browsers. For example, you must have seen that something wrong happens in one Chrome tab. It literally does not impact your entire Chrome browser, right? And that's the beauty. And you will also see that because of the same reason, your entire RAM is filled up of Chrome memory space taken. Like whenever you bring up Chrome and then you keep on making the new tab. Although right now you will see there's new inactive feature that as soon as it is inactive for a time, it actually leaves that specific memory. But obviously when you come back to it, it will take time to boot it up. But yeah, with that said, you will notice that fact that it will take a lot of memory space, because obviously it's a new process built every time as soon as you are making corresponding new tab. Now again, they have optimized it to make tab groups, to make give corresponding differences there, here and there. But yeah, that is a very good use case which you can see. Same way for image processing, in Photoshop, video editors, you also see the same thing. Same way in game engines as well. Now for threads, obviously that if you want to perform multiple tasks within the same application and want to share data quickly and want to keep things responsive and perform it, then you will use threads. Obviously, you have mobile apps in which you want to update the UI, as well as you want to do some background jobs, maybe fetching something, or maybe some network operations, so on and so forth. Obviously, you will try to use threads. Same way for e-commerce platforms, where you have multiple users which browse carts, and you want to implement inventory management and payments and stuff. Many things happen at the same time for multiple users. That's where we can use threads. Same way for music streaming as well. I want to make the UI responsive, along with I want to buffer the audio to the user in the background. That's where I can actually use threads. Now, literally, you can use processes anywhere, but obviously it has its own overhead, and thus wherever possible you tend to use multi-threading. Now, some of the key feature of threads, because obviously the entire course is going to be about threads and not processes. I will not discuss how two processes will communicate via socket. No, I will not do it. This is gonna be entirely about threads, because obviously you will be making an application in which you will be designing services, and these services you want it for them to be multi-threaded. Now, with that said, the feature of threads will include concurrent execution. And as we already saw, that in web browser, you have one thread handling user interactions, for example, scrolling, clicking, and so on and so forth, with another thread loading the page in the background, because you don't want things to freeze. It's a very bad if you are keeping things sequential. No, it should not. Whatever task can be performed parallelly or concurrently, I should do it. Now, resource sharing is a very important thing, that threads with the same process share the same memory resources, right? And that's what makes the communication very, very, very effective. For example, in a simple text editor, you can take Notepad, WordPad, anything whatsoever. One thread checks the spelling and grammar, and the other thread can actually save the document and process the user input and so on and so forth. And that is what actually can make things much more faster. And again, that's it, making things lightweight. For example, the threads required fewer resources compared to multiple processes, and this we can easily see in any multiplayer game. You have the player movement, you have the background music, you have the network connection. They can be literally other other tasks which will be running parallelly. Now, with all that in mind, let's actually see that how to write and make a program for it. For what? For threads. So how will you create threads? Now, specifically, we will see in Java, and this is also a very famous interview question on how will you create threads. And especially whenever you will say that, the next question will be which one you will choose and why. So the first, and again, please don't be confused in the code. I will literally tell you the easiest possible code you can write, not complicating stuff. Only remember the piece of portion which I'm stressing specifically. Again, you will see by my words when I'm stressing on something, and then only remember that portion, complete the entire video, and then you can come back for the portion which you did not understand. But make sure that the portion which has stress, you will have to understand it before proceeding forward, else you will actually stumble upon in the future portion of whatever I will be teaching. So threads, obviously I can extend the corresponding thread class. What I mean by that is I can make any class by any name, but I will extend the thread class. Again, mark my words, it's a extend. If you don't know about basic OOPS, please make sure that you are following the OOPS crash course which we covered. Again, simple OOPS crash course. This is the OOPS crash course. Will cover your all OOPS concept along with generics. So cover that and then come back to it if you don't know about all these basic features. Now, this will simply say that you have a run method. This run method, again, simple run method saying the return type is void. Obviously, we have to be public. You can write literally any code here. Any code you can write here. So the only thing which you have to remember is that whenever I say extend a thread class and just have a run method which will be implemented or overrun. That's it. So what will happen? Whenever I will say that my class, which can be literally any name, right? And I'm saying its object is thread1. Let's thread2. I'm making a new corresponding object. And when I do this, which means I'm making corresponding new object. So it ultimately means I'm creating a new instance of a thread. So because it is extending the thread. So again, remember this portion only, extending a thread class and implementing the run object, like a run method. And with that, I will have two threads, thread1, thread2. When I call the start, it will literally start. When I call the start on the first thread, it will start the first thread. Start the next thread, start the next thread. What does the start actually mean? What will be happening is that there will be a main thread which will be running your main program, right? And as I mentioned, every program will have its own thread. So even if I did not write this code of multi-threading here, if I even would have written a simple sout statement, still that would have run on the main thread. So what will that main thread do? Main thread will say that, bro, firstly I will make an object thread1. Then I will make an object thread2 as an instance thread1 and thread2. Then I will actually start the first thread. So I'll make the thread and then I will start it. Whenever I say I will start it, which means a new thread, let's say T1, will be spawned, and that will end up whenever I say start. Firstly, it will be spawned and then it will call this run method. And whatever is performed will be performed in this run method. Now, while it is being performing, or while the thread1 is performing the run method, what will happen is, meanwhile, obviously, because the main thread is still going down. So right now, so far you have the main thread which is running. You have your thread1 which is spawned and has called to run this run function. Meanwhile, it is running, right? It is running. Again, forget about the sleep and stuff. I will teach you literally everything. So meanwhile, it is running. the thread 1 is running, what will happen is that thread 2 has also started, which means thread 2, a new thread is spawned and then again called the same run method. So while the thread 1 was running, another thread 2 has also come up and saying, bro, I will also run parallelly along with you. So now two threads T1 and T2, again main thread is still free. Two threads T1 and T2 are running in parallel. Now this sleep will say that that specific thread should ideally sleep. So again sleep will say, okay, I'll just pause the execution and I will not go further. I'll just simply sleep here. Imagine the sleep as like the thread is a person. Imagine thread is a person. Thread came up here and put up his bed and slept. That's it. Put up his bed. Again, mark my analogies very carefully. Put up his bed and slept. Same way, thread 2 came here, put up his bed and slept. And then obviously when it comes back, it has to go through this for loop. It will come up, write out the statement, and then again go to sleep. Again come up, write out the statement, again go to sleep. What will be the output? Let's see. So firstly, as you mentioned, thread 1 came up. Thread 1 came up. It will say that, bro, I will print this line. What is this line? This line is sout line, saying thread and the corresponding ID and just mentioning it is running for, let's say, this I. So I'll say that thread 1, right? If it's a thread 1, let's say thread 1 is running, let's say 0. So I'll say thread 1, again, here the ID we have given, let's say 11. Again, the ID can come up anything, whatever you want, although we can actually give the corresponding names as well. So you can define the corresponding thread name as well here, right? So again, it's totally up to you however you want to go about it. So it will say thread 1 is running. Then obviously the thread 1 would have slept. Meanwhile, thread 2 come and say my thread 2 is running. Now obviously in that while thread 1 could have got up and then it will run the next thing. Same way, it will again go to sleep. Then thread 2 will come up and will again write and again go to sleep. Meanwhile, thread 1 would have got up and then it will again wrote and then again go to sleep. So this is how execution would look like. This is one of the execution how it will look like. It can also look like that thread 1 0, thread 2 0, thread 1 1, thread 1 2, thread 2 1, thread 2 2, thread 3, let's say, okay, thread 2 3, thread 1 3, and so on and so forth. It can also look like this, because it's primarily, again, because it can happen the thread might have stuck somewhere, it is kind of waiting and then it did not get that chance to come back, or maybe it is kind of taking some more time to process it. It can be literally anything. So it is not necessarily it will be output very uniform output. It's just that the analogy is how these two threads are actually parallelly making the corresponding output and this output. Now this is first way of implementing the thread by using the extending the thread class. Make sure there's a word extending some other class, and that will be the biggest drawback in future of using this specific approach. And I guess you must have thought of so far that using this approach, which means you cannot extend any other class. That seems like drawback, right? Because again, if you would have followed the OOPS crash course, you would have realized that we cannot extend two classes. We can implement two interfaces, but not extend two classes. And to resolve that, we have implementing the runnable interface. So now, rather than extending thread, you will implement runnable. Everything is exactly the same thing. You will still have that run method, still have that void, and then still writing your own business logic here. Now, how will the initialization change? So earlier what was happening is you were making thread 1, new thread, and nothing passing in. You were doing it earlier, but now you have to implement runnable, so you have to pass in this runnable somehow. How I will pass it? I will say that, okay, my runnable, and simply make a runnable instance and then pass that to your thread constructor. And with that, now you can easily use. So With that, did you see the difference? The only difference is the code is exactly same. Earlier you were doing extend thread, now you're doing implement runnable, right? Earlier you were calling only thread but not passing anything because not required, but now because you are utilizing on runnable, then you will just simply make an instance of runnable and then simply pass it as a constructor. That's it. Everything else is exactly same, functionality exactly same, everything else is same. Obviously now you would have realized that what and why you will use it. You will obviously in the actual code, production code, you will use this strategy. Now if I ask any of the engineers, are they using this, they will say no. People never use this. People never even make threads by themselves. So obviously in actual production code, this you will never see. This is only for, very beginning people who are just, very SD ones and giving interviews. Only for them when they have to write a very short, concise code and just to showcase about threads, this is what they use. Is this used in production? Never. You will never see any production code literally making their own threads and you're writing all this stuff down. No, they will never do it. Now, with that said, am I saying that this runnable also is never used? No. I'm saying making the thread like this is never done. Obviously, I will use ExecutorService, which will manage threads for me from my behalf. But obviously, I should know about all this because ultimately I can literally make any of the things as runnable by implementing the corresponding run method. And this we will also see in one of the LLD problems when we will be discussing these last 4 problems. Right? Cool. Now, again, the implementation output exactly same thing because it is doing. So, quick thing, what happens is you create a runnable object, then you create the thread object by passing in the actual runnable, then it starts a new thread and obviously the call returns immediately and a new thread execution begins. So obviously, as I mentioned, that whenever you call a start, a new thread is spun and that thread he has to look for a run method to start executing that. There are still some caveats here that what if that specific location is locked by someone else, then I have to look for, do I get access to go inside? If not, then I have to wait. All these things I will tell as we go ahead. So a quick difference between thread and runnable. Obviously, basically one is saying that extending the thread class for the corresponding thread. Now it is simpler to implement for beginners because it is thread t1, let's say simply like very simple thread t1 equal to new thread, and that's it, done. No runnable, no complex stuff, no passing in the argument, nothing. Very simple one line. And how you make a simple car object, same way you make a thread object, call that start and you're good to go. But obviously it limits inheritance because Java does not support multiple inheritance. I cannot extend any other class. I am done. I'm screwed. So I should keep my business logic, which means obviously there could be a business logic class, which I will have to extend. I have no other way. Then I should be actually going ahead with runnable because runnable allows extending other classes, and that's the biggest benefit of it. The only slight disadvantage is that it might take a bit more code to write because one-liner code which you actually wrote above, that's kind of a drawback. I don't think so. It's a drawback. It's a kind of win-win thing to always use runnable. So again, people always use runnable. In the examples, you will see that I will use threads as well just to show the examples. Although in the production code basis or in the actual good code basis, you will use runnable because again, it's unnecessary and like it's kind of that, okay, I have, let's say, a paper knife and a blade. You might, and again, let's say, that pocket knife, and let's say I have a pencil knife by which you cut the pencil. Both are of same size. Why would I even keep my pencil knife? I will always keep a paper knife or let's say pocket knife. Cool. Now, we saw thread class, we saw runnable. There is another word which you might end up being asked, which is callable, because it looks very similar to runnable and also used in the same multi-threading scenarios. So you should obviously, because again, the moment you are asked with, how do you actually implement threads? Okay, you will say about thread and runnable. And then the next question they will ask you, do you know about callable? If yes, they will, like, firstly, they will ask you what exactly it is. And if you know callable, then what is the difference between these two and when you will use which one? So firstly, they trap you in asking this thing, then they will go on to this thing, ask you this, and then they will ask you difference between these two things. This is how a simple flow would look like. So let's see what a callable interface is. It's exactly same as runnable interface, but it is actually a more powerful thing than runnable because it can return the results. Did you remember something? I guess you should remember it, because if you remember, it returns a void. The run method returns a void. But my callable can return something, and that is the beauty. See, returning something is actually very, 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 very important, because again, like, I guess this is obvious for you guys also, that you write functions, right? Just imagine that whatever functions you write, if you only had void as a return type, how bad you would have felt, right? How bad you would have felt. You would have never been able to use these functions. Same way, if you would have only had a void return type, how bad you would have felt. And that's the reason callable came in. And thus, you can return the corresponding results. And whenever you return the results, which also means that it also gives an add-on advantage of throwing the checked exception. Now, although we will discuss about checked and unchecked exception, but I'll just tell a key features of callable. One of them we already saw, that it returns the value, which means it returns the result, because runnable does not do it, and also helps us in exception handling, which means I can throw checked exception. For the folks who don't know, again, we will discuss it just in a second. But lastly, I can actually work with futures. Again, for the folks who don't know about future imagine as something which is in future, which will come in future, and I will get to know about it. Although we will discuss about futures in the last portion, because it is a bit tricky and people don't understand that much easily. But still, as I mentioned that in the first lecture, we are referring a concept which we will learn in the last lecture or last section of this crash course. So it sounds a bit, that's the thing. I mentioned that watch the entire video and then you will actually be able to grasp things. Now, obviously, I can work with the future objects, which means to retrieve the results back after a task is completed. Again, we will see all this with an example right now also, and in the entire portion of the crash course as well. But before that, a quick glimpse on checked and unchecked exception. Basically, checked exception says that obviously exceptions which must be declared, and I can actually handle that by using throws or by handling specifically by try catch. So these are exceptions which are actually checked at compile time. Now, examples can be a simple IO exception, a simple SQL exception, simple interrupt exception, which means a thread is interrupted from somewhere. IO exception. Whenever you write any corresponding code which involves a file being accessed, you will have to handle the IO exception, which means that I'm not saying the file was not found while I was running it. I'm saying that I know there's a possibility that the file will not be found when you are trying to access or read a file. So you should declare that, which means it is checked. Already it is checked, and you should actually handle that exception easily at compile time. I'm not saying runtime, I'm saying compile time. Same way, if let's say I am making DB connection, still I have to declare SQL exception. I have to actually handle that SQL exception. Now, unchecked exception says that exception which occur at runtime. I don't know, it may occur, but it might occur. And I might, again, it's my opportunity, like it's my headache if I want to handle these explicitly, but even if not, then I'm good to go. Now, it occurs due to logical errors in the program. Now, what I mean by that is, for example, null point exception, that you do a simple division by 0, because you never know what the user will input as. Let's say I put the input as variable r. I don't know what r the input, like the user could input as, and if I don't handle it, I would get my runtime exception. Same way, array index out of bound exception, arithmetic exception, so on and so forth. So basically, ultimately, the key difference is that the checked exception is handled at compile time, while unchecked is handled at runtime, or it occurs at runtime. But let's come back to our main thing, which was callable. Basically, Callable actually works with executor service. Now, this also is something which we will see in the later portion. Executors and executor service. But it does not work directly by extending thread. It doesn't work like that, which means that I will do something of the sort, that I will implement, rather than runnable, I will implement callable. But now I will have to tell what will be the corresponding return type here, because obviously this entire thing is based on return type. So I have to name that, okay, what can the corresponding return type. And because runnable was having the run method, callable will have the call method. And then exact same business logic. The only catch is now you can return something, and this will be done. And when I say return something, it will be returned as a corresponding future. Again, don't worry about all these words. If you understand it, well and good. If not, then no worries. But what the idea here is that you will use executor service. For now, just imagine that executor service is something which can handle the thread management on your behalf. And then you will simply call same way runnable, like the way you call runnable, like new thread and then runnable. Same way you can actually like the way you call actually runnable by saying runnable equal to new runnable and so on and so forth. Same way you can call callable, but obviously you can give the corresponding string to it. And then you will simply say executor.submit. Again, executor.submit simply says that whatever threads I have, because executor has some threads in its thread pool, it has 2 threads. So submitting one task to it will say that one thread will take this task and will go away and will perform that task, which means perform the call method. Same way, if I come up here, I will say, okay, another thread will come up, take this task and will perform on the another thread. And that is how executor will help us. Again, if you don't understand this, no worries at all. We will discuss them very deep in future. But again, for the folks who understood the analogy, well and good for them. Now, for the folks who are still confused about future basically tells that the result will be ready in future, in later portion, and you can check back it if it is ready or wait until you have it. So when I call the future.get, again, it's a blocking call. What I mean by blocking call is that the main thread will block here. And even if this future one is taking time to compute, still I have to block here. Again, all these things, blocking, unblocking, how to resolve this, and what is the alternative, all of this, we will discuss this as we go ahead. But yeah, this will block, which means it has to complete first. Then my main thread will proceed forward. Then again a get. It is again blocked here. Again, it has to complete and again print, and then only I can proceed forward. This is what actually means by a blocking call or a block. And same way as we mentioned that because I was calling future one is simply saying that my executor will disperse in one thread for the corresponding task which I have, which is callable one. Callable one will come up here and will say that in my result, I will say callable and the name which came up, the corresponding name which came up to me. This is the corresponding name which I said was task one in this case, So callable task one is running, and then I can just say this thing, callable task one is running, and then I can say the number, which is I in this case. And obviously I know that future one.get is being called. So firstly, future one, they are trying to complete first. So this entire thing will run firstly for future one. So this thing will keep on running. So 0, 1, 2, 3, 4, 5 will run until the end for first callable. Then for another one. Then you might ask, aren't this on multi-threading? How to resolve this? Again, we will see all that as we go ahead, that how to actually simulate, multiple these of things being performed parallelly. But this is how exactly this is happening for callable, because right now our focus was how callable is actually working. Now, again, giving a distinction between callable and runnable. And as we mentioned that the runnable or the run method does not allow checked exception, but basically callable does. And if an exception which needs to be handled, it should be handled with a try catch inside the run method. I cannot throw an exception, because you will see that in here I can throw an exception, which means I can throw a checked exception, and that is the beauty of callable as well. So now lastly, I can return result, yes, in callable, but no in runnable and threads. I can throw exceptions. I can throw checked in callable, and obviously unchecked can be literally thrown anywhere. Creation method. I will create by saying new thread, and then I will simply call the start. I will create by saying new thread, but passing in the runnable and then calling my start. I will use executor service and then submit a task, and that will be callable. Return type will be void because I cannot return anything from my threads and runnable, but for my callable, I can return any type, whatever I want. This is generic type. Again, if you don't know about generics, please make sure that you cover this video. Again, this is a simple crash course which will cover generics for you very easily. Now, method, I have to implement run method, and here call. Now, it works with threads, it works with executor service and features. So you should know about them. Now, obviously, this is the best practices chart. It says that I should always try to use runnable, and you know why. Now, this is the very important stuff that you should always try to keep synchronization minimal, because it can end up giving performance bottlenecks and also can affect your program if not handled correctly. With that said, make sure that you handle interruptions correctly, because you want graceful termination of your threads. If not done properly, it will literally halt your entire process. Make sure that you avoid thread starvation by balancing the priorities. It should not happen if you have multiple threads, and if you ignore one of the threads, it can literally halt the entire program. This is the same analogy that if, let's say, you have a team and you have a task which you distribute between the different teammates, and one of them did not even get the chance to get his code reviewed, obviously all of them will complete, and then this one will remain, and this will take the most time to complete the entire process, and thus making the bottleneck for the release. Same way, make sure that you use high level concurrency utilities which come from Java concurrent collection package. Why? Because for complex scenarios, it handles many things very beautifully, and that is the primary reason I chose Java. You will see that this concurrent collection is literally beautiful, like beautiful, out of this world beautiful. Now, coming on, for exactly the difference between start and run method, although I taught you very beginning in the beginning as well, that start basically begins the thread execution and then calls the run method. But run directly, just run, like call the run method, which means it would not create the new thread and will execute in the current, or more precisely to the main thread. So if you have something, if you call start, then I will make a new thread and then we'll call the run method. But if I call run directly, I will not create a new thread and I will just directly call it, which means whatever thread would have been handling the main distribution, that will actually be handling the run. Which means that in this main function, here I made a new thread and then call the start. Well and good. It will make a corresponding thread and then will call the corresponding run method. In this case, I call run directly. This will not make the new thread. The main thread will have to perform this run task. So that is the thing that you should make sure that you call start if you don't want to halt your program, and obviously want to utilize that multi-threading portion. Now, can you call start twice, which means like this? Obviously not, because it will give you illegal thread state exception. Why? Because the thread that has completed execution, it cannot be restarted. So it will work fine for the first time, but next time you call it again, it will give you illegal thread state exception. What is thread safety and how can we achieve? So thread safety simply says that I should be able to perform simultaneous execution by using multiple threads and safely. How that can be done safely? By using synchronization, immutable objects, concurrent collections, atomic variables, and thread local variables. What are these? How to use them? We will see in the future sections. What if an exception occurs in the thread run method? Obviously, we saw that there's no as such thing for handling, checked exception. Unchecked exception can occur. So if an uncaught exception is occurring in the run method, thread will terminate then and there, because obviously it cannot handle it, and the exception does not propagate to the parent thread. That's a good part, which means that okay, you call the thread, it will come up in the run method. Let's say I threw an exception, or a simple runtime exception. Now, what if this catch would not have been there? Again, what if this catch would not have been there? Then obviously my main thread, because I was calling start, so another thread was spawned and then this run was called. So in that exception was created, but the main thread can still work as is, right? So the main thread will still print main thread is running, but then the thread T1, which was here, which went above, that thread will actually be crashing and saying exception is exception the thread. So what happens? That main thread is running, but that thread, again, this is when this catch is not there. So that thread will say that, exception the thread number, and then giving the corresponding exception. But if you want to handle it, you can handle by using try catch, by saying, okay, let's say if you throw an exception, I will catch it here. So with that said, although again, main thread will still be running, but obviously main thread is still running, but obviously here it will be catched. And again, if you want to do something else, you can do something else as well. So yeah, here it will be catched and set called exception in the thread, and then exception in the thread. This thing. Cool. Now, obviously, as this was saying that the main thread is running even if the child thread throws an exception, because that's a beauty that you are not impacting any other thing. Now, what's the difference between sleep and wait? Make sure that you understand very, very, very carefully. This is very important. This is very important, I swear. People get confused a lot. As if you remember, like when we're discussing about sleep in the very beginning, if you remember, I just mentioned that it will put up his bed and he will go to sleep. Remember that analogy. I will repeat that analogy again right now here as well. So sleep says, I will put up my bed and I'll go to sleep. So I'll cause my current thread to pause for a specific time without releasing the lock. What I mean by that is that imagine you are in a home, right? Imagine you are in a home and then there's a main door to it. And then there is a main door to it. Now, obviously, main door has a lock to it. So what happened is that you came in, let's say you came inside, you opened the lock because you had the key, you opened the lock, then you close it from inside. Now you are actually here right now. And then you put up your bed and then you went to sleep. Now the door is locked. And you're also sleeping. And let's say if you sleep for, let's say 5 seconds, or let's say take 5 hours. If you sleep for 5 hours, no one else can come inside, no matter what. While, and again, this is exactly what they're saying, that I did not release the lock, because obviously the actual door is still locked. But in case of wait, what happens is that I will come here. I know I have the key, so I'll open the lock. Again, the same thing as what happened previously as well. Now I came inside, and I saw, okay, here's a bed, but I realized, my girlfriend is missing, right? My girlfriend is missing, and I want to sleep with her only. Let's say my girlfriend is missing, so I will say, okay, bro, I will wait. When I say I will wait, I will do, okay, let's do one thing, because I cannot sleep right now, so I should not take this resource. I will wait for my girlfriend. So I'm kind of waiting for my girlfriend to come up, because I want to sleep with her only. So I will wait. And with that said, when I will say I'll wait, so I know, okay, this is a corresponding space which I can, utilize. So whenever I say I'll say I'll wait for my girlfriend, which means I'll say I will go and put the keys back, so that anyone else, let's say my mom come up, and then she can take that key, she can come inside, and then she can utilize her resource. And let's say she want to, take a half an hour nap, and then she will go away. And then let's say 1 hour back, my girlfriend came up, I will come inside and I'll put up. And again, when I say my mom went away, while going away, she put the keys back, because now she's done. She slept for half an hour, she's done. Now, when my girlfriend came up, I will again take the corresponding lock, because obviously I will not be outside waiting for her. I will again take the lock, I will go inside, and then I will sleep with her. Again, the analogies are not good, but again, this is the best part how you can understand. So you saw that in the first analogy, let's say in the first analogy, if I would have slept, which means that if I would have come up and let's say I know that, let's say I took the keys from here and then I came inside. I know that right now it's not feeling like to sleep. I can only sleep with my girlfriend, but then I still lie down on the bed. right? Although I know that I don't necessarily want to, sleep here by putting myself on the bed, but because I know that I have to wait for my girlfriend ultimately. In that case, if I would have still occupied this resource, obviously my mom would be waiting outside and would not be able to sleep. So that is the reason. This is the difference between sleep and wait. So sleep says that I will pause the execution for a specific time, let's say 5 seconds, 4 seconds, and so on and so forth. I will not release the lock. No one can come inside. But wait says the current thread will try to wait until another thread invokes notify or notify all. Because what if my friend, my friend in the same office as my girlfriend will say, okay, bro, your girlfriend has left. So he will notify me that, okay, let's say your girlfriend has left. So now I know, okay, someone has notified me, and then I will take the keys. So this is how a notify works. My friend will notify that my girlfriend has left, and obviously, let's say it takes her 1 second to reach. I'll take the lock, and then I can simply go to sleep with her. So let's see the example. We saw the real life analogy, but let's see the example as well. So example says that, let's see example of sleep. Firstly, I'll show you example of sleep, very plain example. Then I'll show you example of wait. Then I'll show you actual concurrent example of wait. Then I'll show you actual concurrent example of sleep. So let's get ready and let's see. So whenever I call sleep, so obviously it's a main. So it's a main thread going on right now. Sleep will say whatever thread is here, he will sleep. He will pause execution right here. And it will sleep for 2 seconds. Again, this is 2000 milliseconds, which is 2 seconds. So this will simply sleep. And obviously, when I say output will be that the thread is going to sleep, this line, and then here the thread is actually sleeping. So whatever is in bracket is not the output, it's simply sleeping. And then obviously, when it is done, it will wake up. So this is how you simply write a sleep. A simple sleep this is how it is written. Now, a wait, how you write a wait is that obviously you make a thread, and then in that thread, I just said, okay, bro, just simply call the corresponding function. So I have this corresponding, shared resource. I will simply call my wait example, and then let's say this thread T1 will come inside here, and then he will wait. When I say wait, he will release the lock. Now you might say, Aryan, what does lock release mean here? No worries, but just understand, it will release the lock. And then when I say release the lock, and then he will go and do something, which means another one can come up here. But when I will call notify, so you will see that here I'm calling notify after 2 seconds. I will call notify. So this will actually release this, come back and now continue corresponding process. So I can simply write resume after notify. So what will happen? Resume after notify is called. But obviously before that, you literally notified a waiting thread. You notified a waiting thread, and the thread was actually waiting for you to get notified. So you see that the thread T1 was waiting here. Then obviously he released the lock. Again, I will show the example of what does the lock release mean here. But obviously he released the lock. He's waiting here. Someone notified him that, bro, now you can proceed forward. He will proceed forward then. So T1 came up, came in this line, waited. Then it will keep on waiting. He cannot proceed forward. Then T2 simply waited for a couple of minutes or a couple of seconds. He then called notify. So I came up inside here. Notify will simply go and call notify, and then he can proceed forward with this line. So the order of execution is this line, then this line, and then this line. Now let's see that what does lock release mean here. So imagine that you have two threads, T1 and T2, right? Thread 1 and thread 2. Now I just simply call thread 1 thread 2, which means my thread 1 will come inside, and thread 1 is right now here. So thread 1 will simply first print entering wait example, then thread 1 will print calling wait, and then thread 1 will wait. So thread 1 is waiting. Now whenever we call wait, we have released the lock from here. So it is synchronized. Again, we will see what does the synchronize mean. But the synchronize actually mean that only one thread can visit this function at a time. For the folks who don't worry, like if you don't understand it, don't worry about it. Watch the entire course and then you'll understand everything. But for the folks who have a very small idea, synchronize means that This method, wait example, will be locked and only one thread can access it at a time. So when my T1 is waiting here, it will release the lock. Now another thread can also come inside. So what happened? T2 will also print entering wait example and then calling wait. So you will see the output entering wait example, calling wait, entering wait example, calling wait. Both T1 and T2 called this. Now both T1 and T2 are waiting. And again, T2 also would have released the lock onto this specific thing. Now what we did is we just called another thing and this said, okay, sleep for a while and then call notify. Why I am writing sleep for a while? This is a very standard practice to showcase any task being done. In industry or in interview or anywhere, it is a very standard practice to write sleep to showcase any task being done. So here the sleep is not referring the sleep example. No, it is to showcase that a task is being done. So again, here that sleep will say a task is being done, same way here also. But the fact is that I will notify one. What is this notify one? I will go on to the function notify one. Again, it is a synchronized. So only one thread can come inside. He will come and he will calling notify and then notify one of the waiting threads. Right now, two threads are waiting. That can notify any one of the waiting threads. So I will calling notify and then anyone. Right now it was, let's say, thread 1 who got lucky and then he resumed after notify. So which means that thread 1 got lucky, he will resume as in he will resume after notify. But make sure that when I say thread 1 will not, okay, oh bro, thread 1 will directly not jump up here. He will firstly again have to check, because it's a synchronized block. What if thread 3 would have been at this step? What if thread 3 would have been come up inside and thread 3 would have been at this step? Then it would wait for thread 3 to release the lock and then continue his process. That is the beauty of threads, and also making sure that this is synchronized. So again, I'm repeating, if thread 3 would have been, let's say, at this step, this line, then my thread 1 will wait for it to come down here, then come down at wait, and then wait, thread 3 will wait, release his lock, and then thread 1 can again take that lock and then proceed his own line. So really taking a thread is important practice, taking a lock is important practice whenever you want to execute any statement, even if someone is calling a notify back. So this is what happened, and same way you will see that I called notify again, which means my one more waiting thread, which is T2, will again try to acquire the lock and then will again come up to print this line, resume.notify, and then you will see again come up to print this line. And that's how you saw that how does wait work. But the same is not true for sleep. So the sleep, how this sleep will work is, let's say I make a sleeper thread, sleep 1, sleep 2. So this will simply go and come inside and say, okay, let's say the thread 1 came up. Let's say thread S1 came up. He will firstly write entering sleep example, then going back to sleep for 2 seconds and then sleep. Now it is going to sleep, but he will not release the lock. So sleeping and then going to sleep. So entering sleep example, going to sleep. I wrote that here, but this S1 will not release the lock, which means that S2 want to start. S2 is still waiting, but S2 will keep on waiting because S1 is still inside and S1 hasn't released the lock. So the lock is still intact here. S1 has not released. Although S1 is sleeping right now here, but it is not letting anyone come inside. If that is the case, okay, S2 will keep on waiting outside. So, okay, let's say 2 seconds passed, then S2 will complete this line, woke up from sleeping, and then S1 will exit out. As he exits out, then he will release the lock. So S1 would have written woke up from sleep, and then only S2 can come inside. So you see that sleep, this is how sleep impacts, because it is synchronized, which means that only one thread or only one person can take a lock on this entire function. Again, for the folks who don't know about synchronized, no worries, just hold on for this video and you will understand everything. Then you will come inside, and then again S2 will perform his own task of entering, going to sleep, and then woke up, which means entering, going to sleep, and then woke up. Again, anything in bracket is kind of
what is actually happening and not the output. So this is the actual difference between sleep and wait. I hope so you guys got it, because this is very important to understand sleep and wait, because you will use it a lot. Now again, a couple of interview questions around it. That what happens to the resource a thread was holding on when a wait is called? Obviously, it will release the lock on that synchronized object or the resource it was holding on, which means that other thread can now acquire the lock and can continue their own execution. This is also we saw with the help of an example right here, right? And then again, waiting threads remain idle until another thread is called notify or notify all. Again, the small difference we will see right now as well. What is the difference between notify and notify all? Notify will only notify one thread. If you remember, here we called notify. So if you remember, there were two threads, T1 and T2, who were waiting. So it will only notify one thread, any one thread. It will just simply notify. But notify all will notify all the threads who are waiting. So it will notify all threads who are waiting on that object. So again and again, when I say notify both of them, still both of them will have to fight to take a lock. But it is that okay, both of them can now have the chance to take a lock. So this is the catch here, that I will notify all of them. So here it means that waiting thread does not immediately start running. So again, this simply says, okay, firstly we saw what exactly is notify and notify all. So notify only notifies any one of the waiting threads. Notify all notifies all of the waiting threads. But even if we call notify or notify all, the waiting thread who just right now got notified does not start immediately running. We also saw it will have to acquire a lock first and then can start running. So when the waiting threads is moved to a blocked or a runnable state, it does not start the execution immediately. It has to acquire the lock and then I can start running. And obviously, as and what we said, if I call notify, only one thread wakes up. If I call notify all, wakes up all the waiting threads. But obviously, again, all the threads will still have to compete for that lock who will go inside that specific synchronized block in this example. Now, obviously, one thread will obviously acquire the block and not all of them can acquire. So only one can acquire. And then that thread will continue its own execution. Now, what if we use notify all? Again, notify all will literally tell all the waiting threads to be notified, but still make sure that only one thread only can acquire the lock and can go inside the critical section. Now, what is the callable interface? We already saw. Then how it is different from runnable? We already saw that callable will actually have the call method. Runnable will have the run method. Now it can return the result. It will return void. Callable can throw checked exception. Runnable cannot throw. Callable works with future. Runnable, because it doesn't have any output or return type, so it doesn't need to work with it. Now, can you use callable with standard threads? Technically, no, but technically, yes. So no, directly, if I just ask, but I guess we can figure out some way, which means that I will still have runnable inside that I'm having callables. Again, it's kind of a hack to go around it just to prove the statement right, but again, not preferred at all. So obviously, the callable is designed to work with executor service only. Although the thread class accepts runnable objects, but I can adapt it to work with threads by creating a runnable that executes callable, which is stored inside it as a result. Again, not a good deal, but yeah, we can just ignore it. So with that said, we know that the threads are very powerful, and especially on how things are handled between, with using waits, wait, notify all, and so on. Although we'll discuss all of them in very deep detail, but this is very important for you to get started with how beautiful these threads are. Cool. Let's go on to the next section where we will actually discuss of the thread pool and thread lifecycle. Cool. Let's go. So now, after completing our thread class, runnable interface, and callable, and a couple of things around wait, notify, executor service, let's go on to a very important concept: thread pool and thread lifecycle. Primarily, from now on,
every time in future and also in production code basis, you will end up using thread pool rather than using the actual threads. Now, before discuss thread pool, let's discuss the thread life cycle. So basically, again, although we'll go deep, but so far there are many things that you have already seen. You have seen wait, right? You have seen sleep, right? You have seen all these things already. So what happens is that firstly, we are in a new state. As soon as we call start, we go on to a runnable state. We are not still in the running state, it's a runnable state. Again, with the code also we will see, so no worries, just hold on, relax and watch. Now, whenever my CPU select that okay, this thread will run, then I'll go to a running state. Now from this running state, if I want to sleep, I'll go to a timed waiting state. And then when my sleep expire, then I come back to a runnable state. I will wait for the CPU to give me time again, and then I can come back to the running state. Then if I want to wait, then I'll go to a waiting state. Then from that, if someone notifies, then I'll come back to a runnable state. Again, I will be allowed by the CPU to actually get the corresponding resources, and then we'll come back to the running state. Then from running state, if some IO comes up, then I will be in a blocked state. When it is done, then I'll come back to a runnable state. Then I'll ask CPU that bro, can I come up? Then he'll say yes bro. Then I'll come back to my running state. And whenever things are done, whenever I call stop or when my run method finishes, I'll go on to a terminate state. So this is how exactly your different thread lifecycle states are there. So let's go on individually with the help of code as well to figure out what exactly happens. Although many of these, this one, this one, this one, this one, this one and this one, you had already seen in the previous portion just before which we saw. Now, new state, basically it is saying the thread has been created but not started. So thread has been created but not started. So basically the thread object will exist, but the start hasn't been called on it, which means that there are no system resources which have been allocated to it. What I mean by that is that I have just instantiated it, but thread is in the new state here. I haven't called the start yet. When is in the runnable state? It is saying that the thread is ready for execution, which is it is waiting for CPU allocation. This is the same thing which ties back to that in the synchronized block we were saying that we had a lock. So only one thread could come inside it. Obviously, one will be waiting outside for it, but obviously before waiting, they are actually in a runnable state. They have the potential to go inside, right? That's the thing. And whenever the start is called, the thread moves to my runnable state and it says, okay, I'm ready to run. So whenever I call start, now my thread is in the runnable state. Now, again, I'm not saying it is in the running state. It will come in the running state only when my CPU will be blocked for it. Maybe again, as I mentioned, that some other task is performing this thing and it has to wait. Okay, if not, then it will still have to let it complete, and then when the CPU is allotted to it, then it will come inside. So what happens in the running state now? Basically, it will execute the current task on the CPU, and the CPU scheduler will allocate the processing time to this specific thread, which will be in the running state. So it ultimately means now I have come inside. Now the CPU has given the corresponding resources, and now my thread is in the running state. But obviously, it can become temporarily inactive and it can maybe wait to acquire some lock. So obviously, it will be in a blocked state, which means that it is trying to enter that specific synchronized block, but okay, not able to enter it. So it is trying to enter it, but not able to enter it. So it's in the blocked state. Now, what is waiting state? Waiting state says I am waiting indefinitely for another thread to perform some action for me to like notify or something of that sort, and then I can actually go inside. So I can enter in the waiting state by simply using wait or join or loud support or park and so on and so forth. Again, here the timeout is not specified, that I will indefinitely keep on waiting. There's no timeout specified to it. Obviously, we will see a timed waiting as well in future, which have a timeout specified to it. So here what will happen, that as soon as I call lock object.wait, my thread will enter the corresponding waiting state. Now that's a very standard thing which we already have seen before, that how another thread wakes up the corresponding waiting thread. This has been the entire scenario where I was discussing about my girlfriend. I want to sleep with her, but obviously I'm waiting for her, and exactly same thing. Again, just to showcase that specific thing as a waiter and a chef. So here the waiter, let's say he came inside and then he is actually waiting, then someone has to notify it. So let's say the chef, he comes inside, and now he can come inside because it was synchronized on the lock. Again, no worries on what does it mean, what does this syntax mean. Just as I mentioned, synchronized means that this portion, it can be a synchronized method or a synchronized block. It ultimately means that this portion is locked on this object. So synchronized lock. So on this object lock, again this is an object, right? It is locked. So this entire portion, only one thread can actually take the specific lock. Now as soon as it is waiting, so it released the lock. Now the chef can come inside and then he will notify. So notify will say whoever was waiting, please you can continue. And whenever I say continue, he will firstly try to acquire the lock back again. So chef will go outside, which means chef will release the lock. Then my waiter will be able to acquire the lock back. Now he will say I'll continue further by saying the food is ready. So what happened is that waiter and then chef released, call the notify. Waiter was waiting, then chef came up and notified, and then waiter was actually notified and then performed its further operation. Again, exact same thing as what we saw previously as well, by taking my mom, my girlfriend, and my friend, and so on and so forth. Now there is also a timed waiting, as we already saw, that it will wait for a specified period of time, which means we will define a timeout. For sleep, for wait, I'll define a timeout. And after this timeout, it will automatically return to the runnable state as soon as the timeout will expire. And also it is not necessarily after timeout expire. Maybe if someone notifies me, then also I will come back to my corresponding runnable state. So here we have defined a 1 second timeout. So it will automatically come back to the runnable state after 1 second. Now lastly, the state is terminated when the thread has completed its own execution or was stopped forcefully or by any means whatsoever. So it ultimately means that the run method has exited, again either normally or abnormally due to some exception. The thread object will still exist, but it cannot be started. So ultimately it's the last state. Just again, if I even call an interrupt or I do anything, if it has gone out, that's a terminated state. Now we have seen the thread life cycle, how exactly a thread moves in its life cycle, but it was for a specific thread. Now, as we saw that it is very hard to manage threads, right? Because obviously you cannot restart the threads, that same threads, which means that you have to make new threads, destroy existing threads, and so on and so forth. So as to handle that issue, we brought in thread pools. Right now, thread pool, basically it is manage collection of reusable threads. That is the biggest and the most important word, reusable threads, which helps us obviously, because again threads helps us to execute tasks concurrently. The only thing is the thread pool is a collection of threads that can be reused. Why reusing? Because deleting all that operation is pretty costly and I don't want to go about in that operation. So what I will do, I can use executors and I'll say make, again although we'll go a bit deep into executor service and stuff also, but as I also showed you in the previous portion of the lecture, basically executor service is kind of handling threads from your on your behalf. So I'll say executors and I'll call new fixed thread pool, as the word itself says, new fixed thread pool. So give me a thread pool having 3 threads and it's a fixed sized pool I want from you. So I will get 3 reusable threads. You will see I have 5 tasks and 3 threads. No worries. As soon as I have 3 threads, so 3 tasks will assign, let's say T1, T2 and T3 tasks are assigned to these 3 threads. As soon as one of the tasks is done, T4 task is assigned here, another task is done, T5 task is assigned here. So this is how my corresponding thread pool would work. So what will happen? As soon as you submit a corresponding task here, it will come inside, do the corresponding task. Again, as you can see, I am giving the corresponding task ID as well for it to actually, go through. But again, whenever I mention sleep, this is kind of simulating a task being done, fetching something, processing something, and so on and so forth. So this primarily showcases your thread pool simply taking 3 threads and trying to perform the task from them. So if I just want to replicate that, we realize that we have 3 threads which can perform the task. As soon as one of the threads does its own task, then another task can be started. So what happens that firstly, obviously 3 thread can start parallelly. One of them will finish and again one of them will finish, which means I had 3 threads. Now one of the task is finished, so let's say T1 T2 T3. You will see that T1 task is finished. I have an empty thread, so a T4 task will come up here. Then let's say T2 task is finished, as you can see in this line. Then obviously T5 task will come up here, and then ultimately T3 T5 and T4 task will be finished. And that's how I can end it by saying execute.shutdown. It will gracefully shut down the entire program. And that is the beauty, that now you don't have to individually go and assign tasks to these threads. No, I know I have only 3 threads. I can have literally as many tasks as possible, and then I will perform that. Now, the first question which will come to your mind is, Aryan, why can't I make 5 threads? Okay, let's say if you're saying for 5 threads, I'll simply say that, are you saying that you can make infinite threads? Obviously not, because I can have literally 50 tasks. I cannot make 50 threads for each task. Obviously, they will take resources. They will take my time. And also, I don't want to necessarily make so many threads. So that is the reason these will actually help us. Cool. So what happened here? We literally submitted 5 tasks, but I know I have only 3 threads. The first 3 tasks will start immediately, and as the tasks keep on completing, the available threads will keep on picking up the remaining corresponding tasks. With that, my threads are utilized much more, usefully, and I can reuse those threads, avoiding creating and deleting the existing threads, primarily because, again, as we mentioned, although it's a very minimal overhead in comparison to creating a process, but still there is a overhead of creating a thread. And again, as we saw, that the execution order can vary based on CPU scheduling. So it can happen that thread 2, thread 1, thread 3, like the task 2, task 1, task 3. So this order can actually differ. Now, this is very, very, very normal for the entire crash course, that your order of execution, because it's a multi-threading environment, will differ. So with that said, what are the benefits of your thread pool? Firstly is your resource management. It literally prevents system overload. As I mentioned, that when you are limiting number of threads, you are limiting the unnecessary system overload. If I make a lot of threads, then it might happen they will keep on doing, or they will keep on fighting for resources with each other, keep on doing context switching. My task will never be done. Second is performance improvement. Obviously, because of reusing existing threads, I am getting rid of creating and taking that overhead of creating new threads, and thus improving my performance. Predictability is much more higher because I now control the thread creation, and I can control, okay, only these many number of threads actually created, and keeping my task done. Task management also very good in this case whenever we use thread pools, although we will see task management a lot more as we go ahead in future lectures, especially regarding thread executors and stuff. But it will help us in queuing, scheduling, monitoring. Again, all that you will literally see. We have scheduler service and all that stuff, which will help us quite a lot. Now, let's see. Okay, we have seen thread pool, we have seen thread lifecycle, but thread lifecycle we saw for a specific thread. It is in a new state, runnable state, running state, waiting state, blocked state, so on and so forth. Now we will see the thread lifecycle for thread pool. Let's see. So obviously, very beginning we will have the pool creation, that the thread pool is created, which means that I will have some pre-created threads, also called as core threads. Now these will be in the new state. Same thing as what we saw in the very beginning, that any new thread also will be in the new state. Same way, these pre-created threads S will also be in the new state. Now the best part here is that these threads will immediately enter in the runnable state. We don't have to call dot start no, because these are handled by the executor service. As soon as we define them, they will immediately come on to the runnable state. Now comes the fun part, that when I call or any task is submitted, any ideal thread from the thread pool executes the corresponding task which is required. And as soon as the task is completed, the thread returns back to the pool. From there, again, when I say returns back to the pool, it will return back to its corresponding runnable state, which it got here, and will start waiting for the any new or the next task which it will receive. And as soon as you want to terminate everything, or you will say that you will shut down your executor, or you will shut down your pool, if you remember, right? Shut down, you will remember shutdown. So as soon as you want to shut down, which means you are shutting down the corresponding pool, so threads will complete the current task. Again, there are two things, shutdown and shutdown now. Shutdown will allow the threads to complete their current task and gracefully shut down and terminate. But shutdown now will just say what all tasks were immediately interrupted, and keep them in a list, and then eventually terminate. Both of them will eventually terminate, and again the exact difference code, all that stuff we'll also see as we go ahead. But this is how exactly there's a quick or small difference between a thread pool's life cycle and a simple threads life cycle. Okay, let's see the corresponding code. Firstly, as we saw, that we will have new fixed thread pool. Again, we will see cached thread pool as well. Again, we will see different kind of thread pools as we go ahead in future. Along with it, we will discuss a lot more on different kind of scheduling things and all that stuff. But here what happened initially is that I created a thread pool with 3 core threads. Again, remember this word, core threads. These will be helpful when we will be going ahead and discussing that some tasks, again obviously, because you will see there's some caveats to it, and then we'll discuss about cache thread pool, then we'll discuss, okay, there are some pros and cons for both of them, and then we'll go on to how these core threads are very important. So this will make the corresponding 3 threads for me, and will get them to a runnable state. Then I will say I will have corresponding tasks in hand, and then I will say that these threads, which are 3 threads, I have 5 tasks. So my threads will pick the corresponding task and will move to a running state. Again, like it will actually move to a running state. Now, again, when we say a corresponding running state, obviously it will have to come inside. So far they are still in the runnable state, but as soon as they come inside and they correspondingly performing some corresponding job, CP operation, they will actually be in the running state. So now I can say that, let's say my thread is in the running state, and again, to simulate some work, you can put up a sleep here as well. Let's say after sleep you are waiting it. Okay, now my threads are actually in the waiting state, and so on and so forth. I can do a couple of other operations. So the task where actual operation is happening, right, which means my CPU is being utilized, that is correspondingly my running state. Elsewise, it is about to run or waiting for something. All these will count as the different states for us. And then ultimately, I can shut down. Again, this is just to showcase that I have shut down now as well, which will make sure that the things are terminated instantly. Although we'll see the actual difference between them later on as well. But this ultimately shows us that all threads that were processing the task, again, even if they're running, blocked, waiting, or timed waiting, they will eventually reach my terminated state finally. Even if I want to do a shutdown and then wait, or if I do a shutdown now and then quickly do the termination, I will ultimately reach. And this will be a corresponding output just to indicate that how exactly my states are working. But again, more or less it is exactly same as how we saw previously. It's just that you don't individually call the start because now you have executor service. Now you will simply call that, execute that specific task or submit the corresponding task, and you will be good to go. Now, so what we saw that in thread lifecycle management, I will handle the interrupted exception to allow clean termination. What I mean by that is that whenever, let's say, someone calls interrupt, then I will handle it just for a very clean termination of the program. And I will try to avoid thread leaks. Now, how these can be done? It can be done by ensuring that threads do not get stuck in a waiting or in the blocked state forever. Now, basically, for the folks who already know that a thread waiting indefinitely for any notify will actually generate a leak, because obviously it will never get to a specific working state. So for that, we end up using timeout. Timeout says that I will prevent this to acquire any lock for a specific period of time. So I'll wait for this timeout and then I will ultimately release it. Again, before this timeout, if someone else notifies it, well and good. If not, then I will not wait indefinitely. Again, there's a small catch to it that you might say, Aryan, okay, as a safety net, I will apply timeout everywhere. So again, that's actually very risky to apply timeout. It's better that you yourself, again, you can keep a finally as well, in which you are unlocking it. Maybe you can do that part. Let's say if it is waiting for too long, let's say you throw an exception after a specific time, and then you actually finally just do something. But you should actually make sure that if you are okay with this timeout, because there can be certain processes which might take 5 seconds. So it could have completed in 5 seconds, but you literally are waiting for only 3 seconds and then putting down. So yeah, that's the reason I was just saying that it's a kind of risky thing. Do it at your own cost and considering your business logic. Now, with all that, we got to know about thread lifecycle, we got to know about thread pools and thread pools lifecycle, and also some caveats to it. Let's see thread pools usage. It's pretty easy that we have to choose the right pool type for the specific workload which we have. We have been using new fixed thread pool, right? So this is primarily for more of CPU intensive tasks, which means I have, let's say, 5 threads which I have defined, because all these threads will actually be made already and they will stay in the during the entire life cycle of my executor. So it is important I am using these all 5 threads. And how it can be possible if I'm using, how it can be possible to use all 5 threads? It is possible only when I have sufficient CPU tasks to be performed. That is the reason I am saying that it is, if you have some CPU intensive task, that is when you should use a fixed thread pool. Which means, again, it can be image processing, video encoding, complex calculation, or some complex processing for AI, ML, model training, so on and so forth. You can use it. Why this is beneficial is you will not make unnecessarily many threads. You have fixed number of threads, so too many threads will not be made. Thus excessive context switching will not happen. and then you can focus, your CPU can focus the time in performing the actual core job rather than doing the context switching if I would have made a lot of threads. So the best part is I'm not making a lot of threads, and that's what actually is benefiting me. So I'm making fixed number of threads, just resulting in the efficient resource usage. So here I'm saying I'll make fixed number of threads by using new fixed thread pool and thus calling the corresponding execute and the executing my corresponding task. Now, other can be cached thread pool. Now, it is opposite to fixed thread pool. This will say that I can dynamically create threads as needed. Now, why this will be beneficial? Exactly doing the opposite. So I am saying as and when the requirement increases, I can create more threads because I know I have more of IO bound operations rather than CPU bound operations. So it is much beneficial that I create less threads. But what if there is some spike? Obviously, in that case, I can create more threads. So that flexibility, and regarding that, okay, my primary use case was more of IO bound threads, or I can say also as more of short lived task, then in that case, I will try to use cached thread pool. Right? And again, this is ideal when the threads are reused to minimize overhead. If I just have, let's say, 3 tasks, I can just make two threads. I know that all three are very, highly IO based tasks. So I'll make just 2 threads, and then one task, okay, will just do something and then let it go to IO, come back, then do something, let it do IO, come back, and then again the other two also will do the same thing. So they are still free. So it is unnecessary to make 5 threads when only 2 threads can actually do your job. Those other 3 threads can be used by a different program running parallelly in a different, different concepts or different program is running. Those 3 threads can be used by them. So again, this is a limitation. I should not make infinite number of threads. That's the entire use case, right? So that is what we are saying, that we will use new cache thread pool. So same thing here. I will rather use a new cache thread pool. With that, I will make variable number of threads based on my system requirement. Now, as what we saw, that why would someone use a new cache thread pool for IO bound task rather than a new fixed thread pool? Exactly that my IO bound task spends significant amount of time waiting for IO to complete. Thus, as it is waiting for IO to complete, obviously this will leave the thread. So if it has left the thread, I can use that thread for something else. While in a new fixed thread pool, there are fixed number of threads. And again, these can be, might be blocked waiting, and even if others work could be done. So I will have, let's say, 5 threads. I know my 2 threads can actually do the job of, because even if I have 5 IO operations, again, let's say they are pretty big in, pretty big in number. So two threads did the job and then they are waiting. So unnecessarily, I am blocking these other threads for anyone else to use, because as I mentioned, as you define some fixed pool size, let's say of 5, all 5 threads will be allocated and will remain allocated in the up till the entire life cycle of the executor. So my cache thread pool will spin up new threads when needed, which will allow more tasks to proceed while others will be waiting for an IO. Again, this is based on if I actually spike up the corresponding demands which I have. Now, because new threads can be created quickly to handle incoming requests, I can create more and more threads. While a fixed thread pool might have a backlog of tasks waiting for the threads to become free. And that's also kind of a benefit for it. Now again, there's a catch also for it, that if you end up making a lot number of threads for a very high CPU intensive task, so they will keep on up, just doing context switching and stuff, and they will never be able to perform the actual CPU operation, and thus unnecessarily wasting your resources. So it is important to choose your that which executor service you are using. Now, if you are actually into a scenario, I'll highly recommend go and simply use a fixed thread pool. Don't go into using any other, although you can use any other as well. You will see that primarily we will be using fixed thread pool, but you will see that in the pub sub design we will use cache thread pool. So in the in the LLD concurrency, in the pub sub we'll use cache thread pool. Why? Because we want, okay, again, like, although I will not go deep into it, but yeah, we'll use cache thread pool there. But yeah, again, we'll explain also why we are using this, why we're using that. But again, they're kind of not a big deal. Even if in an interview you are using a fixed thread pool, you can use a fixed thread pool. Let's say based on the number of cores which you have in your CPU, you can use maybe that size or maybe any other random size, let's say 4 or 5. It's completely fine. Now, obviously, the cache thread pool automatically manages my thread creation and termination as well. Now, ideal threads will be reclaimed after a period of inactivity, and again, usually it's 60 seconds, which will obviously reduce my resource consumption when obviously my system is very busy. But with this fixed thread pool, the thread will exist for the lifetime of the executor, even if they are idle. So, fixed thread pool might be less ideal for your IO bound task in many scenarios because of underutilization, overhead of too many threads, and so on and so forth. So finally, your cache thread pool adapts better to fluctuating nature of IO bound tasks and also utilizing efficiently the resources by creating threads as needed and also reclaiming them back when they're idle. Because of this dynamic behavior, the throughput and responsiveness and the performance increase. So for CPU bound task, try to use fixed thread pool. For IO bound short task, use cache thread pool. For mixed workflow, you can use a thread pool executor. Now, what is this? It's kind of a mixture of custom definition of how much task to run, how much task to let them wait, on exceeding how much task or how much threads to make again, and then how much task to actually let drop out. So all that can be defined by your custom config, or I can say threadable executor. Now, how and what we do, we will see that later on, but that will primarily be dependent on the corresponding queue size. If you remember, I mentioned about the queue size, right? You'll define a queue size. Now, this queue size can be less or high because, again, as I mentioned, there will be some core threads, right? There will be a queue size or a queue having a corresponding queue size. Let's say queue size, and then there will be my max pool thread. Like I can make these many maximum number of threads and then ultimately dropping a request. So I'll drop the request. So what happens ultimately, although we'll go deep into it, but what happens here ultimately is that we have this threadable executor. It will say, bro, I have 2 core threads which I can give you. So let's say if I have 10 tasks, so 2 tasks can be performed on these 2 threads. Let's say my queue size is 4. So 4 tasks will be inside my queue. Again, I haven't assigned any threads to them, but they are inside my queue waiting. But if this is also filled, then I will say, because my max pool size was 4, let's say max pool size is 5, right? 2 are already waiting right now. I should make 3 more. So I'll make 3 more. So I'll make 3 more threads, and then my 3 more tasks can run parallelly. And then again, so right now 4, 5, 6, 7, 8, 9. 9 are still doing. Let's say 1 more. Again, always remember, right now none of the threads or none of the these threads are free. None of these are free. If these get free, obviously I will assign the corresponding task from the queue, and then obviously the other remaining task will come inside the queue. But imagine that none of them are free. Queue is also full, and these max pool threads also full. Then I will simply drop that request. Again, I can handle it also however I want, but yeah, this is how usually it look like. So the catch here, what I was trying to say here is that queue size depends. I can literally make this queue very long. Obviously, with that very long queue, I will never be dropping any request. Or I can make this queue very small. In that, I will be dropping many requests. So the catch is that if I make the queue very long, there will be slow execution. If I make small queue, there will be a lot many rejections. Lot many rejections. Lot many dropping of requests will actually happen, and that's where a balanced queue size is very much required. We will go deep into it, but not required. If you are looking for just a quick, crisp thing, always you can simply use and go ahead with fixed thread pool. If you're confused on how many threads to give, you can easily convert it or use cached thread pool. Don't go into ThreadPoolExecutor. No, don't have to do it. But yeah, obviously it's good to know about them. So obviously, in that case, you will see that I'm just saying that for easier debugging purposes, always make sure that you give a corresponding custom thread to your corresponding thread name. Come back to the interview questions. Again, this will also be a corresponding interview question. What is thread pool executor and how you modify the corresponding queue size? We'll see that as well. But the first question is that what happens to a thread in a thread pool after it finishes executing a task? As we've already seen, the thread does not terminate. It will return back to the pool and it is ready to execute another task. Right. This reuse eliminates the overhead of constantly creating and destroying thread. That's the most important line. Now, next, how does a thread pool executor queue size affect its behavior? As you already saw, that for a bigger queue size, what will happen? That I can handle more pending requests, but it will consume very big memory. Because obviously, I'm holding many requests in the memory, right? And obviously, if the queue will reach the corresponding capacity, the pool will end up creating additional threads up to the max pool size. This is the same thing I was mentioning here as well. As it reached its capacity, I will create additional threads up till the maxed pool size. So I have already created two threads. It has reached, the queue has reached its capacity. I will make three more threads because I have the maximum queue size as 5. Sorry, I have maximum pool size as 5. So this is that same thing. And again, obviously the max pool size is also reached and the queue is also full. I will start rejecting the corresponding request. So this is how it will look like a thread pool executor, where you pass in the core threads which will be assigned or which will be given the very beginning. These are the maximum number of threads which can be made in total, which means 2. I can make 2 more. In total, I can make 4. That's it. Then I have my queue size, that I have a queue size of 2, and then the rejection policy, that abort. It will reject the task if the queue and max threads are full. And again, this is exact same thing, that how we can simply go and see that just executing the corresponding task. Here I'm executing 10 tasks, and thus I can utilize and see how it is performing. I can increase this. Sorry, I can also increase this number of threads. I can increase this as well. I can decrease this as well. It's kind of liberty for me. So what happens in a small queue size? Obviously, what will happen? As we were saying, we had 10 tasks. 2 were the core threads. Then my queue size. I'm seeing the queue size is 2 now. Now I was saying I have 4 max threads, so I can make 2 more threads. So first 2 tasks will be assigned to the core threads. These are the core threads. These are max pool threads. Max pool size, let's say max pool size. Next 2 tasks will wait in the queue, right? This is a queue. They will wait. And when the queue is filled up, the new threads are created because I have still 10 tasks. 2 threads are here. 2 tasks are in queue. I have 6 more tasks which are pending because again, considering that these threads haven't become empty so far. So I can make maximum 4 threads. I'll make 2 more threads. Now I'm remaining with 4 tasks. Now, if there are any additional tasks which I will try to assign, and considering none of these threads none of these threads become free, these will be rejected. These 4 requests will be rejected. So if all 4 threads are busy and the queue is full, the new task which we have, which means these 4 tasks which we have, all of them will be rejected, which means that these will be handled by this abort policy, which we have defined. So what is the benefit of this? Obviously, it will help you with faster execution due to additional threads, because with the smaller queue size, the additional threads will be spawned much more quickly, and thus I will have higher CPU utilization, but with the cost of rejecting many requests or rejecting many tasks. With large queue size, The same thing will happen that I have, let's say, two threads, my core threads. I have a queue size of 6, 1, 2, 3, 4, 5, 6. This is my queue size of 6. Now I can make two more my threads, two more threads I can make. So like here were two threads. I, let's say, put 6 more requests here. Now I have two more tasks which I will for sure spend two more threads because I have max pool size as 4, so I can spawn two more threads, and with that all 10 tasks are already there. Right, when all 10 tasks are already there, you will simply see that I am I'm good, I'm not rejecting any request. But there will be less CPU usage because obviously, what if the task would have been only 8? In that case, these two threads would not have been spun, and only two tasks would have been there which have utilized the corresponding CPU. But there will be many tasks inside my queue, obviously taking more time to complete. And that's a kind of a drawback of using a larger queue. Cool. I hope you guys got it. Now, next is what's the difference between shutdown and shutdown now. As you already saw, that shutdown will initiate a graceful shutdown. Slowly, let the task complete. So whatever tasks were already there, which are queued, I will let them complete, but I will not allow any new task to be accepted. That's called as graceful shutdown. But shutdown now says that I will literally stop all executing tasks immediately. That's the biggest keyword here. Immediately. And I will return, because obviously I'm stopping all tasks immediately. So I should return the list of tasks that were awaiting execution and that were not completed. Because obviously, if I stopped something immediately, so I should let the other person know that what was not done. So when I call shutdown, it is a graceful shutdown. But when I call a shutdown now, I should tell what are the pending tasks which were not executed. So on a simple shutdown, I was saying that I cannot submit any new task. That's perfectly fine. But I will let you do the graceful shutdown and then I will terminate. But in shutdown now, obviously, I will give you that no task could be completed. But I will still give you the list of tasks which were interrupted, and then I will terminate. So that is the difference between shutdown and shutdown now. Now, can a thread in time waiting state move directly to a terminated state? Any thread can literally move from any state to a terminated state that we saw just above. That if a thread is interrupted during any state whatsoever, it will literally throw interrupt exception and will come to the corresponding terminated state. So my interrupt called, this thread doing anything will come and will be interrupted and will go to the corresponding terminated state. What is thread starvation? Although we have already seen this, and how can ThreadPool help prevent it? So thread starvation, we have already seen that it is nothing but when I'm unable to gain regular access to shared resources. When I say I mean threads. And also I'm stuck and cannot make any progress. That is starvation. Now, thread pools can simply control the number of active threads. Now, why starvation would happen? Like, why do you think, let's say in a family, you will never get food? Only when there are many of your brothers and sisters who are there. Only then you might be the one who will not get food. But imagine that you only are 3 children. Then obviously you will get food, considering you have food. Even if not, let's say if I just control more activeness, let's say you are the only child, obviously you will get food then, right? So that is the thing. I can control the number of active threads, and that's how I can prevent the thread starvation. Along with it, I can control fair scheduling policies. Because imagine my starvation would happen. The eldest brother will take up all the food, leave a small bit. The medium brother will then take the remaining food. Then you are remaining with nothing. Why? Because elder brother took the priority, then the second elder brother, and then you being smallest, you are gone. You have nothing in your hand. So scheduling policy says fair scheduling policy, which means I will put all 3 of them in a queue, and then one by one they will keep on accessing one of the item from the plate. Food plate, I will, let's say, keep all the items, and then one of them will keep the, like, will take the item, put it, like, go inside the queue. Then other of them will take the item, go inside the queue. Then other of them he will take the item, go inside the queue. Then again repeat this process. So with that, I will not go into starvation. How I can show the same thing? I will simply say that without a thread pool and with thread pool. Obviously, without thread pool, you are managing things. With thread pool, you can let the executor service manage things from your behalf. So without thread pool, in this basically we are saying that we are creating many threads with different priorities, just so that, because obviously we can just give 4 threads to him, but I will have to tell my OS that these have different priorities, right? So I just gave a corresponding priority to these threads. So if you see, if I come down, I have given thread corresponding priorities, right? And higher priority threads obviously will actually take monopoly on the CPU. That's obviously, you can right now also go to a task manager, right click and change the priority. If you think that some of your program need more CPU resources, you can give a custom priority also right now in your task manager as well. So this is exactly what I did here. But my thread executor will say that I will use queue-based scheduling, which will be fair. So I will use a simple executor. Again, this is the same thread pool executor which we saw, that I will have 4 core pool size, maximum also, let's say 4, and I will say keep a lifetime as 0, and I will use a FIFO queue. And then this is the corresponding rejection policies. Here I am saying I will put a fair scheduling strategy. Now with that, I will simply call the corresponding task, which means I will submit my task and then they will keep on running. So here the corresponding task will simulate the work with different priorities, and obviously higher priority task, let's say, is taking more time or utilizing more resources from your CPU, thus letting the others starve. With that said, what will happen? Because you used without thread pool, higher priority threads will be favored by the OS. That's obvious. But because now you are using an executor service, or you are using a thread pool executor, and with fixed number of worker threads, now the task is submitted to the corresponding queue and executed in order, thus providing you a fair scheduling, and all tasks will roughly get a fair chance of execution. With that, you will see that without thread pool, you have very different, like higher priority, corresponding task was like it completed much more tasks, and others were starving. While in a simple thread pool where we did fair scheduling, roughly all of them completed equal number of tasks, and that is the benefit. Now, some of the key benefits of thread pool for preventing starvation will be obviously controlling concurrency, fair scheduling, work queue management, and resource management. Exactly what we saw above as well. So, lastly, as a conclusion, you saw today in this lecture about thread pool. You also saw a lot about executor service and thread pool executor, new thread, a new fixed thread pool, you see cache thread pool, and so on and so forth. You saw thread lifecycle and how these things link with each other, and how they take up the corresponding resources. So thread pool and thread life cycle, like thread lifecycle management, these are very important concepts, and especially thread pool will never leave you, and thread lifecycle is very important as a basics of your threads. Although we already discussed a lot more about wait, notify, which will be very, very, very important, very highly used in future. And again, we also saw about sleep in the last portion of the lecture. These will be very importantly, and you should know that how exactly where your thread is waiting, what your thread is doing. Is he blocking? Is he not blocking? Is he leaving the resource? Is he occupying the resource? Is he taking the things or not? Because people literally always gets confused in that whenever a thread comes up, if he calls wait, is he actually letting other person wait, or is he actually letting other person come in and perform his own task or not? And people also get confused that is that thread who was waiting, can that thread perform a task or not? No, he cannot. He is waiting, but he will leave the corresponding lock. Others can come up and do the task, but he will wait until someone calls, notifies, and then he will resume his task. He himself cannot do, but he is also not blocking anyone else. That is a good child. I call him a good child. These are very important concepts which people usually get confused in. So it is very important that you should focus on these part. Now, obviously, with that said, they will help us in managing system resources, control over the creation and execution, and allowing us to properly monitor and manage threads. Managing threads is very important. That is, I was saying that in future, you will never be making your own threads. Again, when I say in future, I mean in this course, I will keep on making it for your understanding because it's simple and straightforward. But in production code basis, you will always use executor service, ThreadPoolExecutor, and so on and so forth to actually make the corresponding threads. So, proper thread management is actually a balance between maximizing performance and ensuring system stability, and that's how you achieve your target in any production code basis. Cool. I hope you guys liked it. Next, we will go on to our thread executors, and then we'll go on to a deep and see what are schedulers, how to schedule things, and so on and so forth. Next, see you in the next video. And this one is done. It was a big one, right? Yes, but it is important one. Bye bye. Now, after seeing a lot about thread pool, thread lifecycle, all about threads, runnable, callable, and also we have seen a couple of glimpses around executor, executor service, thread pool executor, and so on and so forth. Let's actually go and deep dive onto what are all the methods, all the interfaces for executors in Java. Now, basically, as we've already seen, they provide a very powerful abstraction over thread management. Like if you want your threads to be there, if let's say even if you want 3 threads, then we saw that we will rather use a new fixed thread pool rather than making our own threads. So it's very, very, very important that you are using executors for your own thread management. It literally simplifies the complex tasks of creating, scheduling, and controlling the threads, which means that you now can focus on your business logic, and the entire thread lifecycle management will be done by the executors. Now, obviously, you can have separation of task submissions from your execution details. So what happens is that you are submitting a task now without worrying about creating a thread and then starting it and so on and so forth. You just go and submit your task, and you don't have to worry about creating a thread or starting a thread and so on and so forth. Executor for you will actually handle it behind the scenes. So what comes up? Basically, we have built-in thread pooling and resource management which comes up. You can see that executor uses the same 5 threads. Again, this is exactly we have seen previously as well. We are using new fixed thread pool. So executor is using fixed 5 threads, same 5 threads for all the 10 tasks. So we know that we have 10 tasks which are being performed right now. Again, all tasks are just a simple print statement, but this will simply prevent the overhead from creating any new thread for each task. I can just only do my entire operation with these only 5 threads, and all things will be done. Apart from this, my task queuing, scheduling, and policies can also be implemented by using simple executor service or simple executors, which means that I can use new scheduled thread pool. What this will say that I can schedule periodically my task. I can delay my task. I can schedule the task periodically, and these are useful for your cron jobs, your all these jobs which needs to run at a specific delay, at a specific interval. All that can be done via using your executors. Again, in this case, new scheduled thread pool. Apart from this, your lifecycle control and your graceful shutdown can also be achieved, which means that I can simply call executor shutdown. This is also we have shown previously that we have shutdown now. Shutdown will help us in graceful termination of our program. which means that all the processes all the tasks which I have, they will be completed and they will not be abruptly killed. Apart from this, I also have some of the features for monitoring and management. For example, I can use get active count, get queue.size, getting the active thread count, getting the queue task, and so on and so forth, which obviously helps us in performance tuning and debugging. Let's say if I want to perform that why there's a bottleneck, why there's so much issues, I can simply go ahead and actually debug and also print log these stuff down. Now let's come down to the core executor interfaces and classes which we're going to use. Now, first we go ahead with executor. Again, make sure this is not executors. No, it is executor. This is the most basic interface defining the task execution. You will never use it. It's just that this is the most basic interface and all other corresponding classes would actually use this. Again, as I mentioned, you will never use this, but just it's good to know about it. So basically, as you can see, executor, and here I've just given the corresponding thread. So basically what's happening here is that I provide the task and it decides how to run it. And in this case, I have just given a new thread to create each time. Next is executor service, which you have been using, and it is very important. Obviously, it extends the executor, right, with lifecycle management. So it extends this executor, but obviously along with lifecycle management, and this is very, very, very important. You will be using it very, very much. So this will say that executors dot new fixed thread pool. So it's basically executor service, which we are saying that again, you would say, what is the executors? No worries. This is the factory which we will see on later on. But basically, this is executor service. We are saying that okay, it's a new fixed thread pool. So what will happen? New fixed thread pool. Obviously, whenever the executor service is done, I can submit any new task. Now, there's a thing which you might have a bit confused at a few places. Previously we have used executor service dot execute. At a few places we are using executor service dot submit. So again, although we will discuss this question as an interview question as well down below, but basically execute is a simple fire and forget mode, that you just simply put on some task and then you forget. You don't worry about what is being returned, what is if it is having some issues. There is no mechanism of obtaining any result or tracking if things go bad or down. While in submit, it returns a future which allows us to track things. And basically, if you want to retrieve the result, or if you want to even check for exceptions and so on and so forth, or for any failures, you can do that via using future. Now, as we have already told you before, future is simply okay. It will just give you things which will happen in future. Now you can just simply call get, which is a blocking call, and this will give you the output. Or if it's a failure, it will give you a failure exception. Although in very deep, we will be studying about future and CompletableFuture, so no worries on that part. Now, coming on back, we realize that executor service, this thing, allows really advanced task handling. Again, I can use submit, I can use invoke all, I can use shutdown, and so on and so forth. As you can see, we are using shutdown, we are using submit, and again, invoke all also I will show you down below. But yeah, all these things, again, we have execute method also, and as you can see, a future is being returned for the result retrieval, and so on and so forth. So it's very, very, very beautiful. Next, as we saw that we have executor service, we also have scheduled executor service. As the word itself would have shown you, it is a scheduled. Basically, I'm adding task scheduling capabilities here. So what I'm trying to do here is I called a schedule executor service. Again, exact same method. It's just that now I'm calling a new scheduled thread pool, right? Rather than calling a new fixed thread pool, I'm now calling a new scheduled thread pool, which will return the corresponding scheduled executor service. Now I will give an initial delay, which means this task should start after how much initial delay, and then considering it is scheduled at a fixed rate, which means I will have to give a period, which means it should schedule again and again at a fixed rate after a delay of 2 or after a period of 2, which means that obviously initial delay is 0. So I will start immediately. and I have to run at a fixed rate. So I'll run at a fixed rate, but the period is 2, which means I will run at a fixed rate every 2 seconds. And that is how you actually say that it will allow you to schedule your corresponding tasks in and after a delay or after a fixed rate. Again, there are a couple of more stuffs around it where you can use the corresponding different stuff. But this will help you to actually schedule your task with some delay, with some period, with some fixed rate, with some fixed delay, and so on and so forth. Although we will see as an interview question what is fixed rate, fixed delay, and so on and so forth. So no worries. But yeah, the idea is scheduling things, and then again, when I say things, I mean tasks. Then we have ThreadPoolExecutor. This also we saw previously as well, which is primarily implementation of ExecutorService, right? ExecutorService, if you remember, you had ExecutorService, right? So it's a primarily implementation of that only. But yeah, we already have seen the core pool size, the actual queue size, the max pool, and so on and so forth. We have already seen this thing. Next, obviously, like the benefit which we also saw in the last lecture was that it gives you a full control on everything, which means core threads, max threads, queue type, alive time, rejection policy, and so on and so forth. This gives you a very high flexibility on literal super tuning, thus giving you a very great performance. And again, if you have a very high task, then obviously you can be used in the production grade thread pool management as well. Next, we have scheduled thread pool executor. Obviously, our implementation of scheduled executor service, which we saw here. Scheduled executor service. We have scheduled thread pool executor. This is same way. Like the thread pool executor was an implementation of executor service. Same way, scheduled thread pool executor is implementation of scheduled executor service. Again, similar thing that we will have a scheduled pool, which is a scheduled thread pool executor. And I can simply use this by saying basically that it will enable us for delayed and repeated tasks. And I can schedule all that, I can do the scheduling with all thread pools and all corresponding tuning options for the same. Now, one more thing which you must be eager about is executors, which if you don't know, you have been using literally executors here, right? If you remember, executors, new fixed thread pool, executors, new scheduled thread pool, and so on and so forth. So basically, executors is nothing but a factory. So it's a factory class which will help us to create executor instances. So I'll use executor, fixed thread pool, executor, scheduled thread pool, and so on and so forth. So basically, this will help us even like say fixed thread pool, cache thread pool, single thread executor, and so on and so forth. Basically, it is very easy to just make new executors without any complex configuration or complex management. I just simply do it via this factory itself. Now, if you don't know what factory is, which means you have not been following the corresponding LLD course. So yeah, we can follow it. Again, concurrency multithreading is a crash course which is being covered as a part of this LLD course. Now, coming on back, as we have already seen that executor service and scheduled executor service are the primary two things, while executor service is actually the main thing, which will be very highly used for you. So let's see some of the essential methods inside executor service. So whenever you want to submit a task, as I already told that you have two methods, execute or submit. Execute, I can submit a corresponding task. The best part here is that no result is expected, just fire and forget mode. But the issue is that if the task throws any exception, it's lost. Like you literally are kind of lost, and there's no visibility on any success, failure, retry. There's like nothing you can do. It's kind of literally fire and forget. And obviously, if a machine crashes, the things are obviously lost. While we have submit, this is much better because now you get a future out of it. So you can submit a callable or a runnable, that's perfectly fine, but you get a future out of it. Now, this future, again, obviously you can block and get the result by using future.get. This will literally get you the result of the future. If the task fail, obviously this thing will throw an exception and I can just handle that however I want. Or I can use the future.is cancelled or future.is done to check the status of what is the status like. Is it cancelled? Is it done? And so on and so forth. Next, if you remember, I told you that we have invoke all method as well. This tells us that, just simply invoke all the tasks which you have, just give it. So it will run all the tasks in parallel and wait until all of them finishes, and you will get a list of features. So you will get list of features, and then that list of features you can actually utilize that to do anything in future. But again, there are a couple of catches here that if one task fails, then its feature will throw an exception on .get, but others will still keep on running. And also, if the executor shut down in the middle, only the remaining tasks are interrupted and the rest all remains as is. There is also one thing that this invoke all, rather than only accepting a corresponding task, it has some overloaded method of getting timeout, unit, and so on and so forth, which will allow you to specify corresponding timeout for completion of all the tasks. If they're not done, then probably I can do some stuff there. So what happened there is I can have invoke all, in which I'm passing in all the tasks, or I can have invoke all where I can also give specific timeout functionalities. Now, lifecycle management is the primary aim of what we have been studying. So lifecycle management will not be completed until unless we shut down things. So obviously shutdown and shutdown now is very important. As we have already seen, the shutdown is for graceful shutdown. Shutdown now is for instant shutdown, returning all the corresponding tasks which were obviously had to go through the abrupt shutdown phase. Now, we saw scheduled executor service, right? Now, it has its own methods. We saw methods of executor service. So if I go up, we saw executor service methods, execute, then we have submit, then we have invoke all, then we have invoke all with some overload parameters. Now we will see that scheduled executor service has what all methods. Obviously, rather than now executing or submitting, here we have schedule method. So simply this will say that, bro, simply schedule things. So it will do simply schedule things. Now, obviously, I will give a delay. That this is a corresponding delay. Obviously, I will have to give a runnable, right? But I'll give a delay. And this is the time unit for the delay. So you have to schedule a task to run once after a delay. Again, this is if you want to schedule some jobs. And obviously, if the task throws an exceptions, it won't run again because this is only for once. This is not a repeating thing. If you want to repeat it, which means you will schedule at a fixed rate, in which you will give initial delay, but then you will also give a period that in this period with this fixed rate, you should keep on running. So you will keep on running things repeatedly with this specific fixed rate. It will run after 1 second, but with this, interval of 3 seconds. Now, we saw methods of scheduled executor service and executor service, which are very, very, very important. Especially executor service is very important. You should know about it no matter what. And again, it's good to know about scheduled executor service as well. Like just a couple of methods. Again, there are more, but we are not covering all. We are only covering the very, very, very important ones, which is scheduled as fixed rate and let's say only schedule. Now, on top of it, as we saw about executor factory, let's see a couple of very famous ones which you will be using again and again. New fixed thread pool, which we have been using again and again. New cache thread pool, which we also saw previously. Now one more was added in this lecture, was new scheduled thread pool. There is one more, which is new single threaded executor. Now you will realize that this single thread executor we will be using in our cache. Now why, when, what? It's primarily, just imagine that you still wanted the functionality of a single thread, but also let's say you want to number those threads. If you remember that now you are using a thread pool. So this is primarily for a thread pool. It's a thread pool of n threads. It's a cache thread pool. But now let's say if I want, okay, thread pool, I'm good. Let's say I want to make 5 threads. So I'll say I'll make 5 threads by again and again calling new single thread executor. So I will call this 5 times to make 5 threads. Now you will say, Aryan, why are you doing this? Why can't you simply do this? Because I want that a task should go to, let's say, executor 1 thread. Next task should go to executor 2 thread. I want that task to specifically go to that specific thread, which means that specific executor, and that is the reason I would be needing this. Right? Again, we will use that in our cache, because you will see that we will be wanting the request to go to only one thread to implement our read your own write policies. Again, no worries if you didn't understand this. As you will keep on watching, you will get things. Now, obviously, ThreadPoolExecutor we literally saw in very depth in the previous portion. So again, we can skip this one. Now, let's go, a couple of interview questions. As we already seen, the difference between execute and submit of our executor service. If you realize that in an executor service, we have execute and submit. We already saw that execute will accept a runnable task, only runnable task. That's the biggest word, only runnable task, because I cannot accept callable, because I cannot return anything, and it does not return any result, and that's the reason it cannot accept a callable. While submit accepts both runnable and callable, because obviously he returns a future object, and that can be used to retrieve results and also check for completion status, exceptions, and so on and so forth. So my callable here, as you can see, will return 42, and when I say return, I mean it's a future. So when I call a get, then it will block right now, will then print it. Meanwhile, as you can see, while this execute was happening, so it is simply a runnable. It will simply run executable. It will simply print this thing. Now, second question. How does ThreadPoolExecutor decide whether to create a new thread or query or queue a task? This we have already seen previously, that it checks that if it has the core threads, if these are filled, then it will try to queue the task. If these are filled, then it will try to create more threads by using max pool size. If these are also filled, then those requests are dropped. This is exactly how things happen. Now, what happens if you don't explicitly shut down executor service? That's a very bad thing. You should never do it. But if you don't do it, what will happen is that executor threads will continue running. And obviously, they will prevent my JVM from shutting down. And again, I'm also always expecting that these are not daemon threads. So forget about daemon threads. I'm expecting that that these are not daemon threads, and these are actual main working threads which I have in my place. What will happen because of this is, if it keeps on running, and this will result in memory leak and resource exhaustion, ultimately making us deprived of resources for any other processes as well. So what we can do, obviously we should use shutdown or shutdownNow. Again, we know that shutdown for graceful and shutdownNow for abrupt shutdown. Right now, next, what's the difference between schedule at a fixed rate and schedule at a fixed delay? This is what I was referring earlier as well, that I'll explain. So scheduled at a fixed rate, say that, okay, imagine that this is the line and you will schedule the task at a fixed rate. Let's say at 12 o'clock, at 1 o'clock, at 2 o'clock, at 3 o'clock, at 4 o'clock. This is scheduled at a fixed rate. And I don't care that, okay, whatever task I scheduled at 12 o'clock, how long it runs. It can literally run as long as it wants. I don't care about it. But I will schedule, no matter what, exactly 1 hour next, 1 hour next, 1 hour next, and so on and so forth. But schedule at a fixed delay says that, okay, you will schedule first task, then the delay at which the next task is scheduled is fixed. So the task 2 is scheduled, then again the delay is fixed, again it is scheduled, the delay again is fixed. Let's say the delay again here is 1 hour, 1 hour, 1 hour, and let's say delay is 1 hour. So this is what it means, that delay is 1 hour, that it will schedule with this delay. So if I just ask you, the first task, let's say, took 2 hours, second task took, let's say, 1 hour, third task took 3 hours, fourth task, let's say, took 30 minutes, and then last task, let's say, took 1 hour. So in total, what will happen is that you will take roughly 2, let's say if this is 2 hours, like this, so you will take in total with this scheduled fixed rate, you will take 2 plus 3 plus, let's say this is half an hour. So you will take 5.5 hours at scheduled at fixed rate. While in fixed delay, you will take 2 hour, 1 hour, then again 1 hour, then again 1 hour, then again 3 hour, then again 30 minutes, and then again 1 hour. So in this you will take 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11.5 hours. This is the difference between scheduled fixed rate and scheduled fixed delay, because fixed rate says that I will attempt to execute tasks at a consistent rate, no matter how long the individual task will take. It might overlap, I don't care. While at a fixed delay will simply say that I will wait at a fixed time. I will wait for a fixed time after each task completes before I start the next task execution. That's a difference between fixed rate and fixed delay. Cool. And again, how they will be used? Simply using them with your scheduled executor service. Right? Again, I'm hoping that you guys remember that executor service. We have execute, invoke all, submit, invoke all with overload method. Same way for executor, schedule executor service. We have scheduled at fixed rate, scheduled at fixed delay, and a schedule method as well. Now, going forward, we say that how can you handle exceptions thrown by a task submitted to an executor service? Obviously, I will use a submit, because with that I can actually expect a future, and with the future I can handle the corresponding exceptions easily, right? By calling a simple .get, and obviously if the exception will be thrown, I can simply catch it. Now, next is last thing. What exactly we learned here? We exactly learned a lot about, again, primarily executor service, scheduled executor service, executor factory. This is primarily three things which you should be remembering post this portion of crash course, especially the methods inside executor service and scheduled executor service. Again, here we have submit, execute, invoke all, and invoke all many parameters. Executor factory, you should remember new fixed thread pool, new cache thread pool, and so on and so forth. And same way here, you should remember about how you have scheduled at a fixed rate, scheduled at a fixed delay, and schedule. So this is what you should be remembering. Again, I'm not saying understanding, I'm saying remembering after this lecture. So this tells us that how important are thread executors. Basically, they abstract away the complexities of different thread manipulation while performing some powerful task management and execution control. And again, we saw very core interfaces, methods, and best practices which we can leverage and use. And with that, if we try and start using executor service and executors in general, we will be able to achieve a very predictable behavior and a good resource usage, a performant resource usage. Cool. I hope you guys liked it. Next, we will go on to thread synchronization. Like you must have seen in this lectures, in these two, we were referring about synchronized keyword, and only one person can go inside that block, and so on and so forth. That we will see in this lecture. Are you ready? I am. Let's see, and let's move on to thread synchronization. Now let's continue ahead with thread synchronization. This is very, very, very important, and you can't even imagine this synchronization or synchronized keyword itself will make your life very easy. And that is again the beauty of Java. So basically, what is synchronization? Basically, it's a mechanism which makes sure that only one and only one thread can access that shared resource. It can be critical section, can be literally anything you want, only one thread to access. If I want this portion, this piece of block that only one thread can access at a time, I can make it synchronized. That's it. That's the only thing I have to do. And thus, you can easily see the beauty of it, that by just writing one word, I can make my process or my entire program handle multiple threads simultaneously, because now I will only allow one thread at a time into this section. Now, Obviously, the thing it says is that it ensures multiple threads can access the shared resource in a controlled manner. Why I'm saying controlled manner is because I can tweak it the way I want, that how the different threads can access it. And that's the reason there is a controlled behavior associated with it. Now, with the help of proper synchronization, you will see that you will get rid of data corruption, race conditions, and will ensure thread safety. What I mean by standard data corruption is that imagine that if you have a counter, imagine you have a simple method, void increase count, and then you have this method. In this, you do an increase of count plus plus, right? Which means that you can write it as count is equals to count plus 1. Get the existing count, increase by 1 and put it back. Imagine a simple scenario in which this portion is not synchronized or multiple threads can come simultaneously here. What will they do? They will see the count as 0. Imagine I run 2 threads, right? Imagine a very basic thing I'm asking. Imagine I run 2 threads, T1 and T2, and I run both of them 5 times. And initially my count value is 0. So if this thread will run 5 times, so obviously it will increase the count to 5. Then again this will run 5 times, it will increase the count to 10. So ultimately, ideally, the count should ideally become a 10. But it was possible when I was saying that firstly thread 1 will run, then thread 2 will run. But now I am saying that no, this portion is not synchronized, as in so there are 3 different things I'm telling. First thing I told that okay, thread 1 will run completely, then thread 2 will run. Now what synchronized again, so this is a very standard case that I'm running 2 loops, one for first thread, one for next thread. But in general cases, when you run 2 threads simultaneously, what will happen is both of them will come together here, and then they will say okay, count is 0, increase by 1, increase the count to 1 and put the count. So in count made 1. Again, let's say thread 2 came up, he saw count was 1, increased by 1, count became 2. Let's say next time thread 1, thread 2 came simultaneously. Thread 1 saw count is 2 and then tried to increase by 1, count became 3. Thread 2 also saw the count is 2, increased by 1, count became 3. So basically at this point in time, both the threads saw the count was 2, both of them increased by 1, and both of them put a value as 3, which means that they actually missed a value. And that is the thing. But if I make it synchronized, right, this method is now synchronized, what will now happen is now thread 1 will come, thread 2 will come. Obviously one thread can go inside, so obviously other thread will wait outside. One thread will go inside, make the count as 1, will come outside. As he comes outside, now the next thread will come again inside. He will say count is 1 now, increase it to 1, again it will become 2. Now again the other thread, the thread 1 will be still waiting outside. So this is how the other thread is waiting outside. That waiting outside of thing and only going into this section one by one is making my program correct. Cool. So I hope so that you realize how data corruption can happen. Again, corruption is anything where the data becomes incorrect. And race conditions is the same thing what we also saw right now. Now, method of thread synchronization can easily be achieved via using synchronized keyword. As you already have been seeing that I was using a synchronized keyword, right? So, synchronized keyword will simply say that only one thread can execute the synchronized block or synchronized code at a time. Now, what and how to use the synchronized keyword? Either I can use it as a synchronized method or I can use it as a synchronized block. What I mean by a synchronized method? Synchronized method is any method whatever you write in normal programming, just before it write synchronized. What will happen is that the entire method will now become synchronized, which means only one thread can come inside this specific method. And that's the beauty, that with just one word, and again that's why I love Java, right? It makes things so goddamn simple, especially in concurrency. You will love it. So what happens here is that you declare the entire methods as synchronized, and lock is acquired on, that's very important thing, on the object instance or class if it's a static method. This is very, very, very important that you understand that how and what, on what does the lock is acquired on. Again, whenever I say lock, what lock actually does, again, although there's an entire lecture for locks, so no worries on that part, but you saw that we have been seeing about locks as we were proceeding forward. So lock is simply, okay, this is a specific method. The thread who came inside will take a lock on it. When he will go outside, he will release the lock. Again, another thread come inside, he will take a lock on it. And then he goes outside, he will release the lock. So internally, actually, a lock is being taken by any thread as he comes inside and releases the lock as he goes outside. And this is exactly what I was mentioning. The lock is acquired on object instance. Again, I'll explain, no worries, I'll explain everything with the help of code and explanation that what exactly that this means, but it requires locks on object instance for your normal methods and on class objects on the static methods. Now, when we say a lock is acquired, we will say a lock is acquired before the method is executed or when I come inside it, and as soon as I go outside, I will have to release it. So what happens? Let's see with this code. So you will see that a normal method would look like public void method name and then some statements, right? This is a normal method. To make it synchronized, just add a synchronized keyword. That is it. Now, what happens in a general scenario? I will make an object, right? So this counter is an object of this class. So this is a class which was there, and thus I made an object for it, which is counter. Now with this object, what I will do, I will make 5 threads, and for all of these threads, I will call counter dot increment. So all 5 threads actually will go to the same object instance. There is a very important point I am saying right now. All 5 threads are going to the same object instance, right? Thus, this synchronization is on that object instance, which means that for this object 1, here in this case, I only have just one object, which is counter, but in general, he's saying, again, I'm just kind of specifying it more in general, that if I have 5 threads only for one object, then it will be synchronized for that one object, which means let's say T1, T2, T3, T4 and T5. So T1 will go first. Again, when I say T1, it can be anyone else as well, because order doesn't matter for threads. It can T2 also who goes inside, but the fact is only one thread will go inside. But what if there's another object who has T6, T7 and let's say T8? Then for both these objects, it can happen independently, which means T1 for object 1 will go inside while it is doing the operation and it hasn't gone outside yet. Still T7 can come inside for object 2 and do its own operation. So this is unique for the object I'm going, and it is very normal also, right? We have been seeing in the very beginning as well, object is nothing but an instance of a class. So object will showcase me a unique entity which I have, and obviously all these threads will actually cater for the object of what they are referring to. So object 1, I am saying there are 5 threads. I am calling object 1 dot increment method. So these 5 threads will actually go one by one inside, but it will not impact other object threads which are there. And again, this is what it means by lock is acquired on object instance, that only for object 1 I will actually take a lock for these things and object 2 for these things. But if it's a static method, it will be a class. So if I declare it as a static, then obviously for a class itself, I will have to make sure that only one thread goes inside it. Now, with that said, what will happen? Obviously, this is the same thing that if I am running 5 threads, all of them is just incrementing the count and incrementing the count. So firstly, the first thing which you should observe or which you should know is that I have 5 threads and only one will go at a time. So first one will go, will print this line, increase counter, print this line, and will come out. Then next thread will come, who will print these lines and then will come out. Then next thread will come, who will print these lines and then will come out. So we will see a pattern in which first thread will do it, second thread will do it, then third thread will do it, then fourth thread will do it, and then fifth thread. This is how exactly my synchronized keyword actually helped me. Same way, the only drawback of above portion is that if you see very carefully, technically I should only be synchronizing this piece because this is the critical section, right? I don't want multiple threads to increase the count and cause that issue which we were seeing earlier, data corruption. I don't want that to happen here. So technically only this is the synchronized portion. Imagine that here an API call will be happening, here also an API call will be happening, and so on and so forth. So it is unnecessary to actually let threads wait on this portion, provided they could actually perform this concurrently. So with that drawback, we realize that we need something else. We are not no more sufficient with the synchronized keyword, or I can say synchronized method. I will rather make a synchronized block, which means only this block of code is now synchronized. And again, this is the same thing which we saw previously as well. Now we are saying that now we have a synchronized block. It specifically says I will allow a particular block of code to be synchronized. And again, I can synchronize that along an object on which I will acquire the lock. Again, this is a very important thing which we will see, and you will realize that we will use this synchronized block code while we will do our pub/sub model. You will see that in this pub/sub model, like Kafka, we will synchronize on the topic object and thus take a lock on the topic object. Now, coming on back, obviously we saw that it gives you a very fine grained access, compared to your synchronized method, because now you are only locking, or I can say only actually synchronizing that specific particular block, and I can perform any non-critical work outside this block, but also making sure that I'm protecting the portion of code that truly requires exclusive access. Now, what will happen? Obviously, these tasks can run concurrently, while only this will run sequentially, and thus improving performance and giving us better speed and output. Now, the primary reason why people tend to go choose synchronized block over synchronized method is that if I have some additional work outside, I don't want to keep that synchronized, I'll use a synchronized block. Now it is exactly same. Now the only catch is that I have this function, but I know that this is a not critical section, so I'll only have a synchronized block, keeping a synchronized keyword, then keeping your object here. Now it's a lock object, right? Again, as I mentioned that in our pub/sub, we will actually put up a topic object here just to lock on topic. There's a hell lot of advantages. Although, if you guys remember, we saw in the very beginning section when we're discussing about threads as well, that how I can call, wait, notify, all that good stuff I can do. If you remember, we took a reference of girlfriend, and lock was kept inside. There was a bed, I want to sleep with my girlfriend, all that stuff which we were discussing. So what we did, we were removing the lock on something, then my mom was coming inside, sleeping, and then going out, then releasing the lock, and then all that good stuff, wait, notify, all that can actually happen because of this. So it's very, very, very important. Now, coming on back, we know that this entire portion is a critical section. So this is synchronized on this specific lock. And as you can see, I have made a lock object, a simple lock object. It is not even a reentrant lock, retry lock. No, it's a very simple object. I just took, again, you can take any object. As I was referring in PubSub, you will take a topic, Kafka topic object. Now, what will happen is, again, you will do the same thing. I have 5 threads and all of them run concurrently. Now the catch is that you have T1, T2, T2, T3, T4, and let's say T5. So this portion will actually be executed concurrently. So it can happen that T1, T2, T3, T4, T5, all of them are executing it one by one in any order. It could happen that T3 execute this first, then T2, then T4, T1, T5, anything. But then in this portion, only one of them will go inside. Let's say T1 goes inside. So only one of them will go inside, which means T1 will perform his job, and then when it is done entirely, then he'll come outside. So this portion can only be executed by one thread. So you will see that these lines will be executed by one thread. But this can be, again, when I say one thread, which means all this sequentially by one thread, then next thread, then next thread, then next thread, and so on and so forth. But other ones, because they are not in the critical section, so they can be executed parallelly. So it can happen that T3 and T2 execute this line. One of them will go inside, let's say T3, print this entire portion, then execute this line. Meanwhile, it could have happened that T4 and T5 could have executed this line. Meanwhile, T2 will go inside, execute this, will come outside. Meanwhile, T4 will come inside, and meanwhile T1 could execute this line as well. Then T4 will go outside, then T5 will come inside, and again T5 will go outside, then T1 will come inside, then my T1 will go outside. So you saw that this is how this line was not critical and was also being performed concurrently, but this was a critical section, so it was performed, taking sure that one of them is being performed at a time. So the output would look like something like this, that two threads were able to access the non-synchronized piece of code, and then my synchronized block was accessed and written. Then again the not synchronized portion was accessed and again accessed. Again, this is the synchronized block. Same way, again non-synchronized, again synchronized block, again non-synchronized, synchronized block. So this is how exactly the output will be performed. Now, these are the two main methods which you will encounter a lot. I should say synchronized keyword, which you will encounter as synchronized method or synchronized block. Apart from it, there is two more things which you should do. One is volatile keyword, because again, you just now saw about synchronized keyword, right? You should also know about volatile keyword and about atomic variable. This also will be very important in the same lines as what we have been seeing. Now, this volatile keyword, it basically says that any changes to any variable which is marked as volatile will be immediately visible to all the threads, and this will prevent from caching the local variable, variables locally. What I mean by that is, imagine there is a flag. This is very much used in flags. Again, I hope so that you guys must have used flags in your DSA and stuff, where you say not flag and flag, putting the flag as true or false and so on and so forth. So imagine there are two threads running, and one of them modifies the flag from true to false. So obviously the other thread should pick up this updated value of the flag, and it should not, again, obviously, let's say right now both the flags or both the T1 and T2 threads were actually saying the flag as true. Now suddenly the T1 mentioned, oh no bro, flag I mentioned or I modified that as false. So other thread T2 should also get to know, okay, the flag value has changed to false, I should also change it to false. It should not go ahead with using its own local state. To prevent that, we use volatile keyword, which means to prevent using any thread to use its own local cache, I use volatile keyword. Volatile will say that flag will be volatile, which means I will pick up this from the main memory. Let's see what it says. So it simply says that the variable value will be modified by multiple threads. In that case, we tend to use volatile keyword. It primarily helps us in visibility because if there are multiple threads, everyone should be visible of, should be seeing exactly one value, and it's always read from and written to main memory, and that is how all of them are actually accessing, reading and writing one single source. Thus it is easy for visibility because you are modifying and maintaining only one single source. So no matter what, every thread will have to read the main memory to see the current state. And again, this is not only for flags but also for counters and stuff. You can maintain that specific count. So no thread will use their own local cache. No, they will use this main memory and they will read and write from there only. And also the best part is that changes made by one thread will immediately, again the focus is immediately visible to other threads. Other important thing which comes up is ordering. Again, visibility is the very important stuff. Ordering is something, okay, this is one more thing which comes up, as a side product, because operations on a volatile keyword cannot be reordered related to each other. For example, flag. Now when I say flag, if I put the flag from true to false and then someone here end up putting the flag from false to true, then this order matters. True to false and then false back to true. It should not be that false to true and then from true back to false. The things change. So ordering actually matters, and that is also maintained here. So it will be helpful, obviously, when we're using flags or controlling the execution flow, as in execution flow, whatever the corresponding flow is, and making sure that the intended order is being executed whatever we wanted. So obviously we will use primarily this volatile keyword for status flags and variables, flags and status variables. Again, if you guys remember, I hope so you must have remembered, we use this in singleton pattern when we were doing double check blocking. Again, if you don't know, then please make sure that we go up and then we will have singleton assign pattern. We can just watch this video. In this we have discussed that how did we use double volatile keyword for in singleton pattern. Obviously there is one more thing which is lightweight synchronization. Although this is never used, I haven't seen people using it because you can simply use a synchronized keyword, which is much more beneficial. You have very basic locks, which is much more beneficial, but also it gives you if you only need a visibility guarantee. So this volatile keyword is kind of light and fast weight for synchronization, which means that let's say if I give you an example, you have this running boolean flag. It is marked as volatile. Right now it is true. So inside my main function, I made a thread and ran a task. Now this run task will come up here. Now I know that one thread is running, so I don't have to worry about anything else, but it will come here, and because while is true, it will keep on increasing the count. It's a while loop. It will keep on going because it's true. But then inside my main thread itself, I called stop task. So stop task will go here and will mark the flag as false. Because it marked the flag as false, immediately, again mark my word, immediately this flag will come as false here and will stop right then and there. And thus I will be able to get the exact correct count. Did you see how it is very important in terms of, let's say if I'm igniting a rocket and I want to stop my launch immediately, and if the rocket hasn't launched yet, so I will be able to do it immediately, and that is the fact. This will actually happen immediately, so the counter will be exactly what I wanted because I stopped it immediately. Now apart from volatile, there's another thing which is very important, which is atomic variable. As the word says, it's atomic and a variable. So this gives you this atomic variable, which is simply found in a concurrent atomic package. This is designed to support lock free, thread safe operation on a single variable. as you would have been seeing so far, there's a count plus plus you were doing, and you were doing count minus minus. So don't you think that just to do a simple operation count plus plus, if I keep that inside a synchronized block again and again, isn't it very cumbersome? As in, like, don't you think it's too much for just a single variable? If you put that inside a synchronized block, take a lock, let it notify, and so on and so forth, don't you think it is too much? To actually get rid of this too much, we have this atomic variable. Whenever you have operations, whenever you want to perform operations, simple operations like plus, minus, increment, decrement, updating on any of the shared variable, which will be shared by multiple threads. In that case, I can use atomic variable. So obviously, this will actually get rid of the overhead of locking, because it's not required, right? And I can just simply use exactly as is. Again, rather than doing count plus plus, I'll do count dot and the corresponding methods which we have. Again, the method will simply increment it, update and increment it, increment and update it, and so on and so forth. So how this helps us? I will now initialize my counter by saying it's now an atomic integer, and initialize this by a value of 0. Now what happens? I again have now 10 threads, 10 threads. Each thread is running 100 times. You will see I am simply calling the increment method. Increment method now is no more synchronized. So there are 10 threads, 1, 2, 3, 4, 5, 6, 7, 8, 9 thread, 9, 10. There are 10 threads who can actually concurrently access this specific method. And it's completely fine, they can access it. But what will happen is, because this counter variable is now atomic, so increment and get will do increment and will get you the value in this new value, and then you can just simply print it. So what will happen, even though multiple threads can come inside, but still this operation will be performed atomically, and thus 10 threads will have to increment it 100 times, making the final new value, final corresponding count value as 1000. And that is the corresponding beauty of it, that you will get the final count value as 1000, right? And again, because now you don't have to use any of the synchronized keyword logs and so on so forth. No worries of that part. So what did we saw? We literally saw synchronized keyword, we saw synchronized block, synchronized method, we saw volatile, we saw atomic integer. So it is very important for building reliable concurrent applications, and synchronized, this basic synchronization is very important for you to know. There are many advanced stuff which we will see, as we will go ahead with locks and stuff, but this is very 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 easy and you should know about it. With that said, there's always a trade-off between different synchronization techniques which we saw, but obviously it helps us enable high performance and multi-threaded code, and which is both scalable and correct. There's always a point I always say whenever you are dealing with any of the multi-threaded applications: excessive locking or excessive synchronization can lead to contention and reduce performance. So please make sure that you write that specific code correctly and not use insufficient, wherever there is no synchronization needed, don't use it. Obviously it will cause unnecessary issues, and you have to find a right balance between using things, not using things, and also using what to achieve your desired target. Cool. I hope you guys liked it. Now we'll go on to a bit more deep onto locks, and specifically focusing on reentrant lock and read write lock. Although a simple lock object can be made as is, as we already have, as we already saw that any object can be used as a lock, right? If you remembered, we were saying if we go up, we were using that any object can actually become as a lock. So you can see any object, see it's a simple object, it can actually also become as a lock. With that said, I because of this lock, only one person will come inside. Again, you will utilize and you will see the benefits of how I can make other person release the lock, take a lock, notify, wait, all that stuff can be done such a beautifully, which means that linking synchronization with locks, wait, notify, using executor service, literally it's a combination of like beauty. It's a beauty. Cool. Let's see you in logs. Now, before we go on to actual logs and type of logs, although we have already had a good idea of logs and how they work, and when we have synchronization and we have already seen about wait, notify, let's take that in practice and let's see exactly how thread communication works. So basically that will allow multiple threads to coordinate and share data effectively. Primarily, we will see here about wait, notify and notify all. Now, I hope so guys remember that girlfriend analogy which we saw in the very beginning of the course. We will use the same analogy. It's just that now we will see the actual piece of code and seeing that how different threads will communicate with each other so that they can access the corresponding code correctly and with the corresponding output, whatever we want. Now, obviously, these methods which we have, they work with the thread monitor. Again, it's basically an intrinsic log on an object, which means that in the previous portion which we saw, that synchronized and then we are taking the lock. That specific lock is what is being referred here. How to coordinate between different threads. Now, obviously, they are used when one or more threads need to wait for a specific condition to occur and another thread will notify. Right? If you remember that in the girlfriend analogy, we'll just wait for my girlfriend to leave and then I can notify someone else as well. They will come out of the critical section, then I can go inside my critical section, or I can also go inside if I have the corresponding key. Now let's see again, we will see with the help of code, proper code in this video, the actual analogy which we have already seen, but yeah, the proper wait, notify all code which we will see here. So here the corresponding wait, simply say that whenever a thread calls the corresponding wait method on the object, it releases the lock, and again when I say lock, which it has already hold, it will release that and will go to the waiting state. So we use wait when the thread needs to pause the execution until some condition, and again this some condition happens and then someone else will notify about the corresponding changes, and with that word will come, we will have the notify as a word. For example, you will see that wherever you will use wait, obviously a consumer thread might wait for a producer to produce some item. For example, if you have some, let's say, shared memory space, right? Now, consumer, right now this space is empty. Producer, let's say, produce some item, will put up here. Then he can notify the consumer thread who was waiting for some item to be produced. He will notify that, bro, some item has been produced. Now you can start consuming that item. Right, again, and you will see that this is the exact same analogy also we will see in the later part of the course, like in the later part of this specific section, in which we will see about producer consumer problem as well. Now secondly, what is notify? As we already saw, that someone who is waiting on something, someone will notify the person who is waiting. So basically notify wakes up a signal thread that is waiting on some lock, some object monitor. Again, object monitor lock can be used interchangeably here. Now, if one or more threads is waiting, obviously the scheduler service will choose any one of them randomly, any one of them. And again, when one resource becomes available, it will continue its execution. Again, it is any one which becomes available, it can just continue. Notify all, Same thing as notify, is just that all the waiting threads will be notified. Still, if you remember, we also talked about even if all of them are notified, still only one of them can actually access the critical section. So obviously there will be they will still fight who can take the lock, but obviously yes, all of them are actually notified in this case. So it will wake up all the threads which were waiting on the lock. And we will use notify all obviously when a change happens in some condition and I want all the waiting threads to actually do the corresponding task which they were waiting on. For example, when a producer will produce an item to a queue and there are multiple consumers, separate, let's say separate, there are multiple separate consumers who are waiting on it, then I will run or I will do a notify all. I'll produce an item and then I'll call notify all. You will see exact same this thing, notify all, we will use in our Kafka, right? Because if you know in a pub sub, there are multiple publishers and multiple subscribers. All the subscribers should be notified. And that's when you will see that we will end up using same thing. So with that said, this important thing that all these methods must be called from a synchronized context, right? Because we don't want, again, you will see that why this is important and what I mean by that. But obviously it should be a synchronized method or a synchronized block taking a lock on that specific object, and then you can just, again, when I say method, it can be synchronized method, it is locked on the current object. If it's a synchronized block, you will either pass in the lock or you can pass in the current object. You can pass in anything on which the lock will be taken. So let's see the example. I have a function, let's say do wait. I have another function, let's say do notify. I have another function, let's say do notify all. Now I am making 3 waiting threads. Let's say W1, W2, W3. Again, W1, W2, W3. So, and I literally called them. So all of them will actually try to go here. So 3 threads W1, W2, W3 will try to go. Now you will see that there's a synchronized lock. Lock here I have taken a random lock, on an object. Now only one of them can go inside. Let's say W1 goes inside, right? Now I will say W1 goes inside. Now he will print this thing, his name is waiting, so W1 is waiting, and then W1, because obviously the condition, let's say here we have this corresponding flag, I will just loop and let's say you can see the condition is not met, so I'll come inside. With that coming inside, I will see that I have to wait. The beauty of wait is as soon as it is waiting, again make sure W2 and W3 they are still outside because the lock has been occupied by W1. W1 has taken the lock. He will not let anyone inside. But when W1 comes here, he saw, okay, I have to wait. If I have to wait, okay, he will go and wait. But as soon as W1 goes and waits, he will release the lock. So when he releases the lock, obviously anyone, now both of them were still competing, right? Anyone will get the chance. Let's say W3 comes inside. When W3 comes inside, W3 will take the lock, and thus he will not let anyone else come inside. And that is the significance of using a synchronized block or a synchronized keyword. Now W3 will come inside, he will again print this line, and he will also go in the waiting state. So he will also go in the waiting state and he will also release the lock. With that said, W2 was waiting, he will also come inside, and then when he comes inside, then he will also print this line and then he will also go in the waiting state. Now with all these going in the waiting state, you will see that there is no lock which is being occupied right now. Okay, let's proceed forward. Now all of them are waiting right now. I slept so that I can, I slept in the main thread so that I can enact the process. Now I directly called a notify all. This is another thread which is calling notify all. So I came up here and I will try to come inside. Again, first question is, can I come inside? there is no lock which is already taken, because W1, W2, W3 have already released this lock. Again, this is the same lock, right? This is the same lock. But now we saw that these three have released the lock. So notify all thread, this thread can actually come inside this block. Now when it came inside, it marks the condition as true and then print this line of notify all, and then he will say notify all. With that notify all, what will happen? That all of these waiting threads will be now notified. Now when these are notified, they will again, they obviously when these are notified, they will try to acquire the lock again. That's the beauty of lock. They will try to acquire the lock again. All of them cannot start concurrently now. No, they will try to still acquire the lock. So let's say W1 tried to acquire the lock, and let's say he got lucky. He acquired the lock. Obviously, he will resume from his own location. So he was here, then he completed his try, then he will go to the while loop. In the while loop, he realized the condition is now met. So this will become false. He will get out of the while loop and then he will print this line. Always make sure that while I was saying that W1 was able to come inside, which means that this lock should have been released by someone, which means that when my notify all thread was like, when he did that notify all, right, he went out, and with his going out, he released the lock. Only then the W1 was able to come inside. Now, when W1 came inside, as I mentioned, that he will just print this line. As he print this line, obviously he's done. Now again, if you remember that W3, W2 are still waiting, because I did a notify all, which means all were notified. It's just that they did not get the chance to come inside because W1 had taken a lock. So now W3 will come inside and he will take the lock, and then he will continue his process. He will repeat the while loop. He will exit from this condition. He will come outside and then he will print this line. And then when he will go, obviously he will release the lock. Then W2 was also waiting. He know now the lock is released. I will come inside. I will continue from my line. I will go again, check the while loop. It is not met. I will print this statement. I will also go away. And that is how you executed your all the waiting threads and the corresponding notify all. Now, output I will show you simultaneously, but it is exactly same as what we discussed. So again, although you will see that I will demonstrate notify as well, but let me show you the output of notify all. So you will see firstly the three threads were waiting, then we simply call the notify all, and then all the other threads ended up executing it. Again, because it's a multi-threading, so order of execution can differ. It's completely fine. Now let's go back to notify. Again, let's take the same thing. There are two threads, W1, let's say waiter 1 and waiter 2, W1 and W2. Now what will happen? Again, I have called the start, so there are two threads who will come in this piece. So W1, W2, W1, W2. Obviously only one of them will be able to occupy the lock, one of them will come inside. As one of them will come inside, one of them will print this line and will try, oh, I have to wait. If I have to wait, then what? Okay, no worries. If I have to wait, then I will simply wait. And as I wait, I will release the lock. So lock is released. So if lock is released, the W2 can also come inside. He will come inside, he will check, he will print this line, and then he will also wait, which means W2 will also wait and will also release the lock. So while this was happening, to simulate this, I slept my main thread so that my main thread can sleep and he does not jump very fast due to this portion. Now, when both of them have released the lock and both of them are waiting, we are simply calling a notify.start, which means only notifying one person. So I'm just calling a notify thread who is calling a simple notify, do notify method. I saw that lock is not occupied by anyone. So one thread will come inside. He will put the condition as true. He will print this line and then he will notify any one of the waiting thread waiting on that specific lock. I'll just simply notify. So I realize that I have two threads waiting on this specific lock. I will notify any one of them. So any one of them will get a chance. Let's say W1 get the chance, or let's say W2 get the chance. So W2 got the chance. He will try to acquire the lock again. Obviously, meanwhile, you will see that notifier thread would have gone out, releasing the lock. Only then W2 can come inside here. As W2 came inside here, he will continue. Again, when I say came inside, I mean like he acquired the lock again. He will continue his process. He will see while loop condition got released. Then he will come out, print it, and then done. Now, was W1 waiting? No, because notify only notified one person, and one person notified, did his job and went ahead. What about W1? Yes, W1 is still waiting. He's waiting that someone will notify me and then I will proceed ahead with my further process. And this is what I was referring, that you should very consciously make sure that you are notifying everyone. If you don't, then this thread will literally keep on waiting and will keep on taking your resources. So to tackle that, what we did, that lastly, firstly we waited in the main thread for a while, and then lastly we called a notify all. Although you will see that there's only one thread which was waiting, W1, so I'll just simply call notify all, although notify all will notify all the threads, but here in this case you will see only one thread was waiting. So I'll just simply notify it, and then he will try to acquire the lock again. Yes, he can acquire because no one is holding the lock. And then he will, again, when I say notify all, so you will see that this was a corresponding thread calling notify all. So obviously it would go firstly here, right? Firstly it will come here and then acquire the lock, then for make the corresponding condition as true, and then it will repeat that corresponding process what you wanted to do. And then this will be notified, and when this is notified, he will try to acquire the lock again. He can acquire because no one is holding it right now, because notify all also has gone out and he has also released the lock. And then when he came inside, he will realize, okay, now continue the execution, this is true, condition got violated, come out and then print this line, and I am now free. So this is how your actual task was executed. So if I show you that firstly there were two threads waiting, then you called a simple notify, then one of the threads actually resumed its execution. Then for there was another thread which will be still waiting. For that you called notify all, which will ultimately notify all the remaining waiting threads. Then my remaining waiting thread will resume, and then I will finish my execution. With that, now again, although in the very beginning portion also I showed you, but now again I showed just so that you are very much aware of how exactly wait, notify all works. It is a very, very, very important. I cannot stress enough. So now wait, notify all. Let's see a very standard problem, which is a producer consumer problem. Again, this is not a pub sub problem, so don't link it with this problem. This is much more advanced version of producer consumer problem which we will be seeing, but right now we are seeing a very basic producer consumer problem where producer will be producing data in some buffer where we are seeing a simple queue, and consumer will be consuming from that buffer. Now you might ask, Aryan, where and why would I need a wait, notify all here? It is primarily the producer. Let's say the capacity I am saying is 5. The producer can only produce 5 items, and let's say the capacity is 5 of the buffer, so I can consume only 5 items. So obviously I want the producer to not produce more than 5 items. I want the consumer to not consume an empty list or empty buffer. So what I do and why I would need the thread communication here is, as soon as producer know, let's say if it was empty, right? So my consumer was not consuming anything. But then my producer said, okay, I just ingested some data. Now I should notify my consumer. Right now, here is only one consumer, but if I have multiple consumers, as what we will do in a pub sub model, you will see I have to use a notify all. But here, considering I have only one consumer, I can use notify as well. It's completely fine. But obviously, if multiple consumers are there, then I should use notify all. But in this case, as soon as I ingested a data, I know that consumer can now consume a data. So simply notify the consumer that, bro, now you can continue consuming the data, right? And thus he will consume it. What if there's a scenario in which the entire buffer is filled? Again, these are exactly same. I'm just showing it so that you can imagine it easily. Imagine the entire, entire buffer is filled. Obviously, in that case, the producer cannot produce any data. So when the consumer will consume any record, he will tell producer that, bro, one of these spaces has become empty. Now you can produce the data. So did you see that producer on producing the data notifies consumer that you can consume? Consumer on consuming the data will notify producer that, bro, you can produce, because there's a chance that the buffer would have become empty for you to produce. And here the producer will say that, bro, now there's a chance that the buffer would have become sufficiently enough full for you to consume. And that is the reason where we would need a thread communication here. So producer will wait when the buffer is full, consumer will wait when the buffer is empty. Let's see the corresponding code, how we will go about it. So we will have a simple produce function, we will have a simple consume function, which will keep on running infinitely, right? Which will keep on running infinitely. Now I will have the corresponding producer thread. Right now, I am, for simplicity, I'm keeping only one threads. Same way I have the consumer thread. So producer thread will simply call the corresponding method produce, and same way consumer thread will call consume. Again, both of them running parallelly and indefinitely. So what will happen? Producer will come inside this while loop. He will synchronize on the current object. As you will see that we have a producer consumer class. We made an object called as PC. So both of these threads are operating on the same object. So they will come inside this, which means that inside this synchronized block, only one person can come, which means if the producer is inside and he hasn't released the lock on the object, the consumer cannot come inside. So what will happen? Obviously, firstly, let's say producer came in, right? Producer came in. It's a while true condition. Obviously, he came inside the synchronized block. So producer came in inside the synchronized block. When the producer came inside the synchronized block, he realized the buffer in the very beginning was empty. So this condition was not there. So what he will do, he will add the value. So value in the very beginning, as you can see, is 0. He will just add it and then increase the value. So he added 0, then 1, then 2, then 3, and then 4, right? So I just added the value. Again, when I added the value, I'm also making sure that I'm notifying all. And when I say notify all is on the current object here, because again, there is no lock mentioned. So usually we have lock dot notify. So lock is on the current object right now. So why I'm calling notify all on every ingestion is because I want that my consumer can also consume parallelly. Although you will see that again only one of them could be processed at a time, because I'm taking a lock on this. So considering, worst case scenario that consumer did not even start and I was literally producing. Now at a time we will come inside and we will see that the buffer size, which is 5, is equal to the capacity. which is also 5. So I cannot produce any item. I cannot produce any item. If I cannot produce any item, obviously I will release the lock. So producer will release the lock. Now, Aryan, are you saying that the producer would have released the lock only after producing all these items? No, I am not saying that. Why I'm not saying that is because you will see as soon as you came outside of this synchronized block, you were sleeping for a while, just to simulate that you are producing some item, and then you were going while to, like, you were going back to the while loop, and then you were taking the lock again and then coming inside. So it is possible, very possible, that you might have produced, let's say, only 2 items, and then when you were trying again for the while, then you were trying again to come inside the synchronized block. What if consumer would have continued its own block or its own execution inside it? So anything can happen, right? Okay, but I just want to show you that what exactly could happen, considering, right, considering my corresponding producer is full. The producer has produced entirely, it is now cannot produce, so he will release the lock and then he will go away. He will, like, wait here and then he will simply release the lock. Now with the releasing of that lock, obviously I know that consumer can consume its own process, which it has been doing earlier as well. So consumer will come inside and then consumer will check if the buffer is empty. No, it is not. It has values. It has values now. So it will consume that value. Okay. And then notify all. Again, why is this required is because now you have consumed the value. So buffer size has now gone to 4. Now your producer can literally produce an item, because now one item has gone. So now you can produce next item, let's say 5. And again, when I say notify all, this producer thread, which was on wait here, it will again try to go out, come inside, and try to take lock when he will occupy the lock, because meanwhile what will happen, that your consumer thread would have been sleeping to do some consumer operation. Then in that portion, I will be simply taking up and checking the buffer capacity is not full. I will produce some item also. So this is how my production would work. Now coming on back to consumer, what would have happened, that obviously I will wait and then I will try to consume again another item, another. Lastly, you will see that if it's consuming, it will become empty. As it becomes empty, it has to wait. It has to wait. Consumer has to wait for any new records to be ingested here. And as you already know, that producer that producer was notified at every step whenever the consumer was taking or consuming any and every data. I was notifying all of my producers. Again, in this case, there's only one producer, but I was notifying all of the producer to actually produce the data, so that I always have some data in the buffer. And same goes for my producer. That producer, on producing a data, was always notifying all the consumers, such that he has an empty buffer for it to insert data into. And with that said, you will be able to achieve the corresponding result. Again, the output is very straightforward. Firstly, you produced, then you consumed. Again, so this is how it looks like. That firstly, the producer produced a value, then obviously it will notify, then notification reached the consumer consumed it, then obviously it will notify. Producer was still there, producer, because again it is empty, so producer was already outside of the critical section, but yeah, obviously it wanted to come inside because the while loop was still ongoing, so it will still try to produce the record. It will try to produce 1. Meanwhile, let's say it produced another record, let's say 2. So it produced 1, then 2. Then obviously at 1 also it would have notified, at 2 also it would have notified, but obviously maybe the consumer was basically doing something, he did not get time. Now my consumer got time, no worries, he will consume this record. Okay, he consumed it. Meanwhile, he will tell producer, bro, keep on producing. Although producer wanted to produce because his buffer is not full, but still, as soon as consumer consumed, he will still notify about to the producer that, bro, produce something. So I will produce 3. then I'll produce 4, then I'll produce 5, and then, oh, is my buffer full? Technically, I consumed 1. I produced 2, 3, 4, 5. Technically, my buffer is not full. So ideally, you will see that my buffer capacity, again, here in this case is not 4. But yeah, you will see that my buffer would not be full yet. But imagining, okay, let's say if my buffer capacity is, let's say, 4. So now it is full. In that case, okay, obviously, I cannot produce anything further, but I will consume things. Okay, I'll still consume things. Okay, I'll consume, let's say. Oh, as it is consumed, obviously I can now produce more. I'll produce, let's say, 6, right? Then I'll, let's say, consume 3. Okay, I can produce, let's say I consume 4, I can produce 7, I can produce 8, and so on and so forth. That's how my simple producer consumer would work. Now, this is a very good problem asked mostly to the college graduates. For industry folks, they ask PubSub, right? Which is much more better and utilizes a lot of good concepts. Although when I would be teaching you PubSub as in Kafka, I will tell everything around Kafka as well, because Kafka scares a lot of folks, but we'll go about a very easy version of it. There's one more thing I want to go about, that how does thread interruption work with the communication methods. So basically when a thread is waiting, I can interrupt it by another thread, and this will simply cause an interruption exception. That's it. So my thread who was waiting, I will just simply call an interrupt. He was, let's say, sleeping. So he would have come here, thread going to sleep. Obviously he was sleeping. When I call the interrupt, he will directly throw an exception, which is interrupt exception, and thus he will directly come here. So firstly he executed this line, then he was sleeping, then he did not execute this, he directly interrupted and came here. So this is exactly what we got the output as, going to sleep and then interrupted. Again, very basic, very very standard, which we have been already seen previously. This is how you communicate via your threads. Again, in this, I wanted to primarily show you the producer consumer problem and wanted to revise you about wait, notify all, because this is very important. Next, we will see exactly about locks and especially various type of locks. Although we have already seen the utilization of locks when we are doing synchronization, wait, all that about locks we have already seen. Now we will primarily discuss or primarily deep dive into types of locks, which will be very important for you for any of your LLD problems in future as well. Let's go. Now, although we have already seen a lot about locks, but now we will see about specifics of locks and different types of locks again, which are useful for us. Now, if I just give a quick recap, we have already seen a lot about synchronized keyword, in which I can pass in a lock object. My current object can also actually act as a lock on which I can take a lock. I can pass in any random lock object. I can make any object and can pass in as is as well. But now we will see very specific types of locks which we can utilize and which you will be utilizing most often. Although there are many type of locks, but we will primarily focus on reentrant lock and read write lock. There's stampede lock, there's many more locks, but we will focus on these two. Primarily, you will always be using reentrant lock. Always. Now, before we go on ahead, let's see that what we have been seeing. We saw that we have the synchronized keyword, which provides us the basic locking functionality. But we have this concurrent.locks package, which offers us very highly sophisticated flexible locks implementation, which is giving you a more fine grained control, and that is what is explicit locking is used for, giving you a very high grade flexibility, obviously giving you a non-blocking structured locking. What I mean by that is giving you a try lock feature. You can go ahead and try to acquire a lock if you want to. It is non-blocking, it's not lock, no, it will just try to acquire lock. If it was able to try it, then it will acquire the lock. That is the beauty, that you can perform a non-blocking operation as well. You can have multiple other things. For example, timed lock attempt. You can have interrupt lock acquisition. You can have non-ownership releases, which means that you can release the lock from a different threads altogether, which you were not able to do in a simple synchronized keyword when you're doing locking from there. Obviously, you can have multiple condition variables, you have multiple fairness policies. There are literally a lot of advantages which can come up when you will use fine grained locking. But obviously, with greater responsibilities comes greater risk and greater implementation details. That now I will have to make sure of many things which could go wrong. Obviously, if I would have used a simple synchronized, keyword inside my method name, I know it will be synchronized no matter what. But now if I'm using explicit locking or locks, I have to make sure that I'm locking it, unlocking it, and so on and so forth. It's kind of a overhead, but obviously giving us a lot of advantages as well. Now, let's go ahead with actually going, ahead with locks. So locks basically in Java offers a very fine-grained control, and one of the very most, I should say literally most important implementation is reentrant lock. Now, obviously, as the word says, is reentrant because the thread that holds the lock, it can reacquire it back without causing any of the issues. Now, it means that it is used when you want advanced control over locking. And obviously, when I am saying I want control, I mean, okay, I'll try to acquire a lock, or I can use fairness policies. I can actually, when any portion is actually having a critical section and it's very complex and require nuanced locking handling, then I can use my reentrant lock. Let's see with the help of example that how we will use it, how we'll use a reentrant lock. Now I made a reentrant lock, simple, a new reentrant lock. Now this is a reentrant lock. Obviously, I will have simple functionality of lock and unlock. Again, I'm showing you a very, very basic examples so that you can use it as and when you want it. Now, with this, what will happen? Okay, no worries. First of all, we will say I will use ExecutorService to simply execute, or I should say submit my corresponding task. Again, here, if you want to, get something out, you can use submit. If not, you can use execute as well. So here I will simply say I have 5 threads, new fixed thread pool. I hope so you guys remember it, that in executors factory we can have this corresponding new fixed thread pool, and in my executor service I have this method of submit, execute, invoke, and so on and so forth. I can use them to actually start and call example.increment. It will come up here. Now this lock will be acquired. So lock dot lock. Again, you can name this anything. You can name this as reentrant lock as well. So it will be reentrant lock dot lock. And then reentrant lock dot unlock. So what happens? What happens here is that you will firstly lock it, come inside, print this statement, increase the counter, print this statement, and then in the finally you will print this statement and then will unlock it, because you have now 5 threads acting parallelly. So all 5 of them would try to come inside, but obviously because of locking on that lock, only one will be able to come inside, execute everything, and then before going outside it will unlock. As it unlocks, other thread 2 will come inside, repeat the process, go outside, before going outside unlock, and same thing will be repeated. So the output for all these 5 threads will be like first thread doing all these operations, second thread again same thing, third thread, but obviously doing in a sequence. Now when I say sequence, it can be T1, then T3, then T4, then T5, then T2, or any order, but all of these tasks will be performed and then only I will be going ahead with the next thread. So as you can see, all of them are being performed and then only you are going to the next corresponding thread. Ultimately, because you use lock, the counter will be 5. Apart from reentrant lock, there is another lock which is a reentrant read write lock. The benefit of this read write lock is literally immense. This is why separately you had to make a separate read write lock, is because that if you have some resource, it can be some buffer, some data structure or anything, whatever, you want multiple people to read simultaneously. Again, they are reading because obviously if something is, if I give you a page and that page, a simple copy page, right, that page has something written, so obviously multiple threads should be able to simultaneously read it. But if I have, or if I'm doing some writing, firstly, multiple writers should not be able to write simultaneously. No, I mean like only one person. Let's say if there are three writers. No, only one person should be able to write, and along with it, there should be no reader who should be able to read while I am writing. Obviously, if I will let them read, or again, you will see that in concurrent, when we will be learning about Java concurrent collection, we will see that there is copy on write array list, which will let you read the existing state, which it will be actually build a copy for. And again, there are nuances around it, that how you go about it, on how you want things to happen. But in a read write lock, I will not, again, there can be one solution for it. I will let them read the previous state before the lock was required. Yes, it can be one solution. But the read write lock internally says that if I am writing it, no other thread could even read it. Which means that on writing, no thread could write or no thread could read. And again, same way on reading, obviously no thread could write. And but on reading, multiple threads can actually read simultaneously. That is what my reentrant read write lock provides. It has two parts to it, read lock and write lock. You will see that we will use both of them. We will use, again, reentrant lock RW has two parts to it, read lock and write lock. So if I am saying that multiple threads need to read, they can do so concurrently. But no writing should happen at that time. And there should be exclusive writing, which means when the thread is updating the data, no other thread, reader or writer, is actually allowed in that resource. They cannot read, they cannot write. And it is used to improve the performance in scenarios where there are many threads who want to read in comparison to the writer threads. So let's see the example. Firstly, I'll make a reentrant read write lock saying RW lock. Now, obviously, as I mentioned, that I will have a function which will write, I will have a function which will read. Now, I will call my executor service with 4 threads, and I will simply call 3 readers in the very beginning. 3 readers. Again, there's one line missing, but yeah, imagine that there are 3 readers here. So 3 readers will concurrently and will be able to read it. Right? Okay, so 3 readers will be able to concurrently read it. So I'll just simply let 3 readers. So there are 3 reader threads which will come here. And again, read write lock dot read lock. It will lock. And when this is locked, it will only check that there should not be any writer thread which is occupied. And he will say, no, there is not. In that case, he will let all these 3 threads to come inside. So all these 3 threads has now come inside. Now again, all these 3 threads can perform this task in literally any order, whatever they want. So first thread could execute this, next thread could execute this, and then this, then third thread could execute this, and then first thread back could execute this, next thread could execute this, next thread could execute these 2 lines. So again, you see that the order can be literally anything. Now, when these threads, let's say they were simulating some work. Again, I'm saying let's say they were simulating some work. All these 3 threads, they have acquired the read write lock and they're simulating some work. Again, although to simulate a work, here I have done a simple for loop. Although you can do a sleep, thread.sleep for let's say 5 seconds as well, you can do that. Now, when it is doing it, you will see that the main thread will come down and then he will say that write. He will call the write function, write value function. So this write value function will come up here. Now that writer thread, let's say W1, will try to come inside. But then the read write lock dot write lock, it will say, bro, there is still some readers reading. So these readers, all of them have to go out. Only then this writer thread can actually go inside. So what will happen is this writer thread is actually blocked, or I should say locked outside. So what will happen? These all threads will be doing their work. When all of them get out of this, then only my waiting writer thread could actually come inside. And then he will write this thing acquired log, and then he will do some work, right? Let's say if he has come inside and he is doing some work. Now imagine the main thread went further, and then I have another two reader threads. Obviously another two reader threads has now come up here, R1 and R2, right? Here they have come up, they are trying to go inside, but again there is one writer thread which is already there, so these two cannot go inside, they will have to wait for it. So which means they will wait for this writer thread to complete. When this writer thread completes, he unlocks. Only then these two reader threads can simultaneously go inside. It's completely fine, they can go simultaneously inside. Even if there's another rethread, let's say if they would have come up, let's say right now I have only two rethreads, what if another one would have come up? That also would have easily gone inside. I can literally let any number of rethreads go inside. Now when let's say those two rethreads are right now, let's say waiting here, or let's say one of them has gone out, one of them is, let's say, waiting here, then if I would have called a writer thread, obviously that specific writer thread would be still waiting here. Let's say writer 2 will be still waiting here because one of the read threads is actually still inside the log, they have not given out the log. So when this read thread will actually go out and will release the log, then only this writer 2 thread can come inside and do the corresponding task. And this is how actually your read write lock works. So again, if I show you the output, you remember that firstly we had three reader threads. So obviously three reader threads will perform the corresponding read. And again, in any order, they could perform the operation. Only when all reader threads are done, then only I could actually start my writing. So only then I will start my writing. Then when the entire writing is complete, only then I can start my these two readers in parallel. So then I will start my these two readers in parallel. Only when these two readers are complete, then only I can start my another writer. I can start my another writer. And lastly, as you can see, I have another reader which I will start only when the writer is finished. And that's how you can use your read write lock. Now, a simple question, what's the difference between synchronized and reentrant lock? Although you must have seen that this is very basic, this is very advanced. So you can just use those terminologies here as well. That my synchronized, basically it's a keyword built in language and it automatically acquires and releases the intrinsic lock, right? And again, because it's so much easy, it's very simple to use. But you cannot try to acquire a synchronized lock with a timeout or even check if the lock is available by using a try lock kind of functionality. Now, when I say check, I mean I want a non-blocking accusation. What I mean by that is if I call synchronized, and then I give a lock. Here you might say, Aryan, I will simply call this no. Then I will realize if it goes inside, then obviously this is not locked. But again, to actually go inside or to even check here, you will actually be trying to lock it. If you're able to acquire the lock, you will say it was not locked. But again, this is the blocking operation. You are acquiring a lock just to check, can I go inside or not? So this you cannot do with the help of simple synchronize, that you are just checking, which means you are not blocking it, or you are not locking, actually taking a lock itself. That you can do via reentrant lock. How? Obviously, you can use try lock. Obviously, we'll see the example as well. But some other things is it provides more explicit locking management, and also with that giving you a very high flexibility. And again, the try lock is one of the key things. As you can see also here, timeout is very normal. It's it's kind of, you can just integrate it anywhere. So like timeout is not the big selling point here. Big selling point is my try lock feature. And obviously I can attempt to acquire the lock with the try lock and see that in a non-blocking fashion. Another thing, apart from basic functionality of synchronized versus reentrant, is that one of them is automatic, one of them is manual. Which means that in synchronized, I have automatic release of lock, and whenever I go out of the synchronized block, I'm good. I'll release a lock. But in reentrant lock, it's explicit locking, and usually you will see that unlock happens in the finally block. So if I go up, you will see that unlock I'm doing finally. No matter what, even if the interrupt comes up, still lock should be unlocked. If it will not be unlocked, I will actually starve on resources, and again my program will actually become very bad. And that's the kind of nuances around all these multi-threading code, that you have to make sure that your things are actually perfect. Now obviously it will give you additional control and much more responsibility for a developer. Now let's see the example of a try lock. Right, for try lock, as you can see, I simply took a very basic reentrant lock. Right, again, anytime let's say you want to take a lock, you can take a reentrant lock. That's kind of it should be a go-to for you. Now again, when I say go to, I mean, let's say if you're using a synchronized block, then obviously you can use any object as a lock. But if you want your own specific locking functionalities and unlocking functionalities, I'll highly recommend go ahead with reentrant lock. That's most common, everyone knows about it, that's most basic and will be most used for you every time. Now coming ahead, we will say, okay, I have a long task which will run for 5 seconds, which is a long time, and then I have a try lock task which will try to lock or try to come up. So what I've been doing here is I will run thread A, run the corresponding task A. So he will just run, which means that this thread will come inside. I know I have this reentrant lock has not been occupied by anyone. He will come inside. So thread A doing a task 1 came inside, printed the statement, and then slept, which means this thread A has slept. Now I hope so you guys remember the difference between sleep and wait. Wait will release the lock, but sleep will not release the lock. Now obviously I am sleeping here, I will not release the lock, I have taken the lock. What will happen? Another thread, after 100 millisecond, another thread B, I have spun up, and that specific thread B, let's say task B it is handling, so that tries to acquire the lock, and it will try for 2 seconds, right? 2 seconds. As it will try for 2 seconds, it has been only 100 millisecond since the specific thread started. My previous task will sleep for 5 seconds. Roughly imagine that it is now 3rd second, it will come in the else condition, and it will simply print this line that it could not acquire the lock. And then ultimately what will happen after 5 seconds, this thread will come down, finish the task, and it will come to the finally block. It will release the lock and it will come out. So this also came up here. Again, this did not even acquire any lock, but it checked, can I try to acquire a lock or not? And that too with a specific time. I can try to acquire up till this specific time. And that's the beauty, that firstly the task A, it acquired the lock, then task B tried to acquire a lock, it did not succeed, but then task A finished after 5 seconds and then ran completely. So I hope so you got it. The two, again, there like you will see there's stampede lock, there are more types, but we are focusing on the most important, and we are focusing on 95% rule. What will actually help you in 95% of the time? Elsewise, this actually course multithreading will go very long. I want you to focus on the very important stuff and tell you by my experience what exactly is asked or you should know for solving any problem in your concurrency questions of Leetcode or even your LLD questions. Now obviously we saw about reentrant lock, read write lock, and why specifically these locks are much better than your synchronized keyboard, giving you extra add-on functionality. Obviously these can help us create more efficient, scalable, and robust concurrent applications, but obviously coming at the cost of handling things by ourselves and not letting things fall from our hand. And when I say fall from our hand, make sure that you all when you acquire any lock, Make sure to always release it. To put that, always put that in the finally block, so that no matter what, even if some exception comes up, even if no matter whatever comes up, still you should release that lock, because it is very, very, very important. Else you will go into a deadlock situation and you will screw up. I hope you guys liked it. Now, next, we will see about Semaphore. Another beautiful thing, because you will see there is tiny philosopher problem. There are many problems which revolve around mutexes, semaphores, because semaphore is another beauty from it own. Cool. Let's see Semaphore. Now, after we have seen a lot about logs, a lot about synchronization, let's go to Semaphore. Now, obviously, what is the need of it? It is pretty obvious, right? You were earlier talking about logs, that you are having that synchronized keyword, and then you can just have a synchronized method and so on and so forth. Now, the biggest issue with this thing is that only one thread can go inside at a time, right? If I remove this, any number of thread can go inside at a time. So can I use something in which I can actually control how many threads can go inside a critical section? And that is where Semaphore comes in, right? It's kind of that giving you the actual control of how many threads can actually go inside a critical section. So let's go ahead and see that what exactly is a semaphore. Basically, as we saw, that locks basically enforce exclusive access. Okay, only you, as in only one person, one thread can go inside, while semaphore can control access to specific number of resources. Let's say X number of threads can actually go inside this critical section. Now, it maintains a count of permit. Permit as in you can say tickets. Let's say I can give tickets. So if I, let's say, have 5 tickets, let's say semaphore have 5 tickets, and let's say I have 8 threads. Obviously, if the semaphore only has 5 tickets, he can just hand over these 5 tickets at max, right? So 8 threads will come. The first one will take first ticket, the next one will take next ticket, next one next ticket, next one next ticket, next one next ticket, and next one last ticket. So 5 tickets I distributed. 3 threads are still remaining. They did not get any ticket, and they will not get it. Now let's say one thread, he took the ticket, he went away, does his work, and then came after some time and then returned me the ticket back. Now I have now got one ticket, so I will give that one ticket to the one who was waiting for a ticket. That is how whenever I say permit, you can imagine it as a ticket. I can give a ticket. So basically, when someone came up and took a ticket, this was actually saying I'm acquiring this permit. I'm acquiring this permit, or I'm acquiring this ticket. And when he'll come back and hand me over the ticket, he's releasing that permit, whatever he had. So that is the thing. We have acquire and release. Acquire will decrease the count of tickets or permits. Release will increase the count of permit. Now, it is possible, again I'm repeating, it is possible that imagine I had no ticket at all. Still, I can call a release. That release will give me one ticket. Even if that ticket did not belong to me, still someone can call a release as in giving a ticket back or giving a permit back. It's still possible. And again, we will see that later on as well. But yeah, this is one thing which is possible. And we'll also use that as a question when we will be doing on, these actual multi-threading questions. So obviously the same thing as we saw also, that when a thread attempts to acquire a permit and no permit is available, the thread will be blocked until any permit becomes available. Or again, obviously there's worst case that you interrupt it and obviously it will actually go. So acquire will say I'll obtain a permit, and again I'll block if there is no one, and I'll block until one of the permit becomes available. Release will simply return a permit to the semaphore. That's it. So type of semaphore, again there's no as per type of semaphore, there's only just one semaphore. The semaphore you can simply say as one, but people have given the type of it unnecessarily just because that binary semaphore, also called as mutex. Like again, whenever I say also called as, doesn't necessarily mean both are same. It's just that I can interchangeably use binary semaphore, mutex, or a simple lock because they will give exclusive access to the any resource whoever is taking up. And that is the reason, again, you can, as we saw, that Semaphore's entire beauty is giving controlled access, and I can control if it can go 1%, 3%, 4%, and so on and so forth. So it's pretty easy for me just to say that if only I want only 1% to go inside, I will put one inside and I will only hold one ticket or one permit. That's it. So that's how I can simply make a binary semaphore. So that's the reason I was saying that there's no such types of semaphore, but still we discussed it because this is pretty important in terms of can be used or can be asked about mutexes and stuff. So obviously it has only two states. Either I will have no permit or one permit. Initially I will have one permit. If one thread come up, takes this and goes away, obviously I will have no permit. And this will help us to achieve mutual exclusion. It is similar to what you have been doing and what you have been learning about locks, right? Okay. Now, let's see an example how a mutex binary semaphore would work. So I will initialize my semaphore with one permit. As you can see, I've initialized with one permit. Now I'll simply say in my code, let's say I'm simply saying acquire. So what will happen? Like I'll simply, again, when I say acquire, so imagine I have two threads, right? T1 and T2. So both threads will try to come inside. T1, T2. Obviously, both can access this line. This line both can access simultaneously. But as soon as they both entered this line, only one of them can acquire because I only had one permit. So let's say T2 got lucky and T2 acquired this. Now, as T2 acquired this, the permit count becomes 0. I now have no permit, which means that T1 will end up waiting here. Now, T2 will perform this task, T2 will sleep, and then T2 will come in finally block. T2 will then release it. As soon as T2 releases it, now T1 can come inside. And again, when I say my T1 can come, he can come inside, he'll come inside this, just print this. Meanwhile, T2 could have printed this line, right? It is possible that T1 would print this line first and then T2 would print this line first. That is why I actually showed you that this portion is outside the release. So the lock was only taken in this portion. So this is what I can guarantee, as this will be executed by one thread at a time. But obviously at this point in time, two threads can actually at any order execute anything. Now again, my T2, let's say my T1 executed this line. After that, my T2 executed this line. After that, my T1 executed sleep. Then my T1 came here. He released it. He gave back me my one permit, and then he printed this line. This is how simply you can go about. As you can see that your T1 came up, acquired the lock. T2 is attempting to acquire a lock, but obviously he cannot because T1 has acquired it. When T1 releases it, only then my T2 can actually acquire the lock, and then obviously he will also release it. Now, obviously we saw that we have a binary semaphore. We also have a counting semaphore. That's the main thing actually. Now counting semaphore will obviously allow you multiple permits. Now again, the only change here will be that now I can give a count 4, 5 again, right? Now you might say, Arun, one is also count. Yes, I was saying that the type doesn't actually matter here because it's ultimately one or more permits which you can give. So I'll manage access to a pool of resources, and with that I can give any number of permits. Again, obviously non-negative because you will actually hand over cards, right? Access cards, something like that sort. So obviously these are non-negative number of permits, and the best part is that multiple threads, whichever I define, let's say if I define 3 as a permit, so only 3 threads can acquire the semaphore simultaneously, and obviously until all of these are exhausted. And that is the beauty of your semaphore. So it can actually give you that, okay, whenever you want limited access to your database connection, let's say if you have some database and you want only 5 people should actually access at a time, then you can actually have a semaphore on top of it. Now, if you want to, if let's say, I'm not sure if you guys have seen, if you download something from Chrome and if let's say download 10 files, but it only downloads 3 at a time. So that's how you can control the corresponding concurrent downloads, and obviously handling thread throttling and so on and so forth. Again, there are many use cases. It's entirely that you are getting the flexibility of literally using only the required number of threads accessing your critical section. Now, let's take an example. Let's say we have made 5 threads and I am only having 3 permits. So I'll only allow 3 threads at a time. So when they will call this access resource, all 5 threads will come here, right? All 5 threads, T1, T2, T3, T4, and T5. Now, all of them will execute the first line, or all of them can. Now, as soon as they will see this acquire, so one of the thread, again, right now, there are 3 permits. So one of the thread will take a permit and will go inside. So like T2 is right now here. Again, my permit has reduced to 2 because one permit was used by T2. Another permit I can still use. So T3 will also come here. Same way, I can use one more permit. T4 can come up here. So now you can see I have 3 threads who have got 3 permits, and now T1 and T5 are still waiting outside because they did not get permits, so they cannot enter this critical section. So what they will do, T3, T2 and T4 in any order can perform these tasks, which means let's say T3 can perform this first, and then T4 can perform this, and then T2 can perform this, or T2 can perform first, then T3, and then T4. That's the beauty of multi-threading. And then all of them will sleep, and then they come to finally. Let's say T2 comes at the finally first. They will release it. As soon as T2 releases it, right? T2 releases it. It will increase the permit by 1. Now, the moment T2 releases it, T2 will come down, right? But obviously, let's say my T2 thread hasn't executed this line yet. T1 still have a chance to come inside. So now T1 will come inside. Now he will consume that permit. Now let's say T2 wrote this line and then T2 went away. Now meanwhile, what would have happened? Let's say T3 would have also come up here, but maybe before that T1 executed this line, and then T1 is actually in the sleeping, right? Meanwhile, T3 came up this and he released it. Okay, he also increased the permit. Now again T3 came up here, but meanwhile what happened? Let's say T5 came inside. T5 came inside and occupied the permit. Now obviously my T3 let's say executed his line, and then let's say T4 also would have come up here, and then T4 released the permit, and then T4 executed let's say his line, and then T4 also went away. Then T1 executed this line, T1 increased the permit, T1 executed this line, and then T1 went away. Then T5 came up, then T5 went sleep, then T5 came up here, and then T5 also released the permit, and then he also went away. So ultimately I have got my 3 permits back, and that's how the process was executed. Cool. Again, the code also says the same thing, that 3 threads were able to acquire the permit, and obviously my other 2 threads are actually waiting outside. Then what happened? Again, I just released the permit. Then let's say my T1 released the permit, then T4 acquired the permit, then T2 released the permit, then my T5 acquired the permit, and then remaining T3, T4, T5 will ultimately release the permit. And that is how you can literally use your semaphores. Now, obviously, very common use cases for semaphore include manage access to pool of resources. That's the most and the only, I guess, important stuff. Right, when you want limited number of resources to be accessed, for example, database connections, file handlers, thread pools, and so on and so forth, I can literally only allow 5 permits for, let's say, if I have 5 resources. Now, other thing is producer consumer pattern. Again, we have already seen this pattern. If you remember that we had a buffer and we want producers to produce in that buffer and consumers to consume from the buffer. Now, obviously, I want that producers can produce only up till the capacity of the buffer, and consumers can consume if I have something in the buffer. Now, to replicate that, I can simply use semaphore as well, because it is trying to say, right, that up till the capacity. So whatever capacity I have these many number of empty slots which can be filled. So I can allow these many number of threads to parallelly fill this, right? So that is the reason I can say empty slots, I will have buffer size equal. So which means I can allow 5. Let's say if the buffer size is 5, so I can fill up 5 slots, which means I can allow 5 threads concurrently to come inside and fill this location. And same way, if my fill slots is 0, okay, I have no fill slots, which means I cannot consume. But if let's say my fill slots would have been 5, which means I can actually start 5 threads to consume parallelly. And this is the benefit, that you will not run into situations where you are kind of not, or maybe over putting up things onto the buffer, or over getting things from the buffer, getting into a corrupted state. So you will not get into it. Next, obviously you can control the concurrency level, which means because the semaphore can limit the number of threads which are running, so you can literally avoid overwhelming your system by so many number of threads and so on and so forth. And obviously, if I just say, if I have 10 number of threads, that's it. I will restrict that to 10 threads at a time, and no matter, more threads will not be accessing it. Again, as we saw, that we can actually make semaphore counting as 1 to make it a binary semaphore or a mutex. Now with that, only one thread, again, this will work exactly same as a lock as what we have seen already before. Now let's see some of the interview questions here. What's the difference between semaphore and a lock? As you can simply would have seen that a lock would only allow one thread to access the resource at a time, because it's kind of, one thread only can come up, while semaphore allow X number of threads to access the resource concurrently. And obviously, lock is owned by a specific thread and that must release it, while a semaphore can be acquired and released by different threads. And this is also what I was mentioning, that it's a permit. It's a permit. So anyone can take, again, it doesn't matter that if the permit, like I have, let's say semaphore, let's say has 5 permits. It doesn't matter which thread takes what permit. It just takes the permit and then go away. And then also any other thread can come up and then give me one more permit and I'll accept it. So that's also beauty. I can increase the permit also. Other thread can come up and can also increase the permits. That is also another thing. Again, because you will see that in future we will use a scenario in which semaphore will have no permit, and then one person will come up and will give a permit, and this is the permit which I will be using to actually do a mutual exclusion scenario. So these are also the beauty of semaphores. Now let's see an example that how does a lock and a semaphore. So if you remember that we will use our famous lock, which is a reentrant lock, and obviously semaphore, which have 3 permits with it right now. So in my simple example, I have one thread for my semaphore and one thread for my lock. So what will happen? Obviously, so what will happen here, that I have 5 threads which I'm making for both my lock and my semaphore. Now the beauty of lock is that this is lock. So if 5 threads are here, only one thread can go inside. So one thread will go inside. He will release the lock. Only then the next thread will go inside. Will release the lock. Only then the next thread will go inside. Then release the lock, and so on and so forth. So one by one, these 5 threads will go inside this critical section. While in case of semaphore, if I had 5 threads, because I know semaphore count was 3, so 3 threads can go inside. So these 3 threads are actually inside here. Then obviously, if any one of them removes or releases the permit, one more thread can come inside. If one more thread releases the permit, one more thread can come inside. And that is how 3 threads were actually inside this critical section at a time, because of my semaphore. And that is a difference between your semaphore and a lock. And again, if you want to replicate this scenario, you can just change the count to 1 and you will be good to go. So that is your beauty, that that your semaphore, I was able to go, like I was able, 3 threads can go inside, while in lock it was just 1 thread, right? Semaphore, same way, as you can see, 1, 2 and 3, like 3 thread actually, like 3 threads release the corresponding locks. Again, whenever one thread releases the corresponding permit, other thread can actually take that permit as well. So although here we have taken the permits here and here, but again you could have taken a permit here as well, because obviously one permit is released, so I can easily take a permit now. And again, lock simply works like taking a lock, releasing a lock, and then taking a lock, releasing a lock, and then taking a lock, releasing a lock, taking a lock, releasing a lock, and then taking a lock, releasing a lock. It's kind of that take, release, while in semaphore I can take X number, at max X number of threads at a time, and that is defined by my semaphore count, permit count. Now, difference, what if we call release on a semaphore without calling acquire, which means that, simply saying there is, let's say, no permit, or even if I have some permits, let's say I have 5 permits, can I call a release? Yes. The release will simply add one more permit. That's it. So yes, we can obviously call it. It's perfectly legal and perfectly possible and perfectly done as well in real life. It will increase the permit count beyond its initial value, because you are giving an extra permit, because you did not call acquire at all, which means you haven't acquired any permit, but you are calling a release, which means you are giving a new permit to it. Again, this will actually help us to dynamically increase the number of resources, but obviously it actually comes with the cost of uncertainty and getting things in an inconsistent state and so on and so forth. So you have to handle this very carefully and make sure that unnecessarily you are not doing things. Now, let's see an example that how we'll go about it. So imagine that I just simply called a release. So I have a simple semaphore, and from that semaphore I'll simply call the release. So you will see that initially I have only 2 permits. So ideally only 2 threads can actually access a critical section at a time, right? But I called a release. So what will happen? Actually, this will increase to 3. This will increase to 3. Now, what will happen is that I now, let's say, make 3 threads. Now, because I have increased this to 3, 3 threads can come inside the critical section together. So what will happen? These 3 threads can actually come inside. If I would have not released it, only 2 threads could have come inside, and then one would have waited outside. Only when one thread go out and release the permit, only then I could let it come in. But now when I have increased it to 3, all 3 can come inside. With all 3 coming inside parallelly, all this will be executed parallelly, and that will also show with the code that all 3 actually acquired the corresponding semaphore. Now, how would you implement a barrier synchronization pattern? This is actually very important in terms of understanding, because it's important in terms, in many production code bases, you want that no thread can proceed past a certain point until all threads have reached that point. It is important in terms of, and again, although in real life, you can use many other things for it, but that's a very beautiful thing. Now, the beautiful thing, what I'm trying to say here is that imagine you are running 5 threads, right? So 5 threads, they have a task to perform. So I have these 5 threads. Obviously, they can perform this task concurrently, right? In any order, they can perform it. Let's say T1 can perform this, or maybe T3 can perform this first, because they can perform it. Now I want a barrier that, okay, firstly, all these threads should perform this task. Only when all of them are done, only then I will let these pass this barrier. And then when they pass this barrier, they can again perform these tasks parallelly. Again, they have a barrier, which means that all of them has to complete performing. Only then I will let them pass below. So this is actually the beauty of your barrier, that it will again allowing you to actually parallel execute stuff, but at the same time controlling that, okay, before exceeding this point, all threads should be done. So how will I implement it? Obviously, again, it's kind of a bit tricky to think of it from your own at the first step, but let's see how we'll do it. We know that we have 5 threads and we want all of them to stop. So if I have 5 threads, I want all of them should stop. And only when the last thread has actually done his task, only then I should release the barrier. Right? Again, this is the function. So you will see barrier is actually this class object. So barriers await I'm calling. This is not the actual inbuilt thing. This is my own built-in, my own built-in object. So this is barrier object, and for that await method I have made here. So this is the await method. This is all built by me, right? Now, what I will do, so you got the idea, right? That ultimately you want that if you have 5 threads, you want that last thread, when the last thread is actually gone, then he should make sure that the other thread should also be released for the further process. Which means technically I want that my sum process, when it is being performed, right? It is being performed by one thread, he should halt up here and he should not go beyond it, right? Okay, and let's say the next thread come up, he should also halt. Next thread come up, he should also halt here. Next thread come up, he should also halt here. Again, halting in the very end, that it should not return back anything, or it should not go beyond this function, right? Because I'm calling this. So I want all these threads to halt. But the fifth thread, he should come up at some location and should let all the other person release. So as you saw that 4 people were waiting at this point, the 5th person came up and then he just ran some command via which all these 4 waiting people got released, and then he obviously has done his own task, so he will also release. So this is exactly what we're trying to achieve. Now, if I ask you, if I want to halt some people to not go beyond some point, right, I can simply acquire. If at this point in time, I'll say there's a barrier and the semaphore count is 0, obviously no one will be able to acquire it. And if they will not be able to acquire it, they will not be able to surpass this point. So I will do the same thing. I will say that, bro, take that barrier with a semaphore count of 0. So this is exact same function which I was telling, that let's say my 5 threads simultaneously came up. So firstly, I made sure that I initialize my count with the number of threads, which is 5 in this case. So my count is initialized. Again, the parties is nothing but a copy of count, right? Parties is a copy of count. That's it. Like, it has no more task. It is just so that I know how many count I initialize in the very beginning, because you will see I'm decreasing the count, right? So I should need to know the initial state of count. That's the reason I just kept parties. Now, what will happen here is that 5 threads will come here. So T1, T2, T3, T4, T5. Now, obviously, only one thread can go inside a critical section. So one thread will only go, and then he will decrease the count. So now the count becomes 4. Obviously, if it is a 4, I will say release the mutex, which means another thread can come inside now. So T2, let's say T3, T4 and T5. So T2 can come inside now, but obviously T1 is still here. So T1 is trying to acquire barrier, but it is saying I am T2. You cannot acquire. So T1 is stuck here. But obviously T2 can come inside. If you remember, the count variable was 4. Now T2 will come inside, it will decrease the count. The count will become 3. Is it 0? No. It will come inside. It will also release the lock, and then T2 will also be stuck here. When it releases the lock, no worries. T3 can now come inside because T3 can now acquire the lock. So T3 comes inside. T3 will reduce the count to 2. Reduce the count. It is 0? No. Okay. Then T3 will obviously release its own lock, and then he will also be stuck. T3 also stuck. Now after releasing, T4 can come inside. T4 can come inside. He will decrease the count. Count will become 1. He cannot go here. He will come here, and then he will also release the lock. But he is also stuck here. T4 is also stuck here. Now T5. T5 was able to acquire the lock, decrease the count, it becomes 0. Now this was the last thread. The indication that the count is 5 was indicating I have 5 threads who could perform a task. So count 0 indicate that, bro, you are the last thread. If you are the last thread, you should not go in here. No, you will have a separate condition for you where I will let you go. And then I will say, firstly, bro, your task is to free your brothers. So he will say that I am here, my 4 brothers are waiting, which are equal to the count minus 1. Because if there were 5 threads, only 4 will be waiting, because last one will be the one who will rescue all the other brothers. So this person, with like the last person, will release 4 permits, with releasing 4 permits. Now this will have 4 permits in place, and I saw that 4 threads were waiting here. So all these 4 threads will release simultaneously, and then before the last thread will go away, he will make the count back to the default value of 5, and then he will also release his own lock and then will go out. So with that, what happened? All 5 of them was able to go out simultaneously. And that is how we were able to implement a barrier synchronization pattern. And with that, what happened? All these threads performed the task. Then all threads literally waited for the last thread to complete, because last thread was the savior thread who let them actually get the permit. And with that, all of them actually surpassed this barrier. And then again, all of them will perform the same task. Last thread will be the, their hero, who will get all of the other ones permit, and then they will also let them pass this point. And that is exactly how your barrier pattern works. So you will see that all of your threads perform the phase 1, then they will perform the phase 2, and then ultimately all the tasks are done. But again, internally, phase 1 tasks can be performed in any order, because there are 5 threads who can do task in any order. But obviously they will be performed first, and then phase 2 task, because there's a barrier, and the barrier will say the phase 1 task needs to be performed first. Now, next question. How will you implement a read-write lock? Now, I hope so you guys remember about type of locks in which we saw reentrant read-write lock. Now, if you don't know, then please watch the previous section. That reentrant read-write lock was primarily saying that multiple readers can access the shared resource concurrently, while only one writer can access at a time. And when that writer is accessing, no reader can actually access it. That is what my read-write lock, reentrant read-write lock, was doing. Now I have to replicate the exact same behavior by using my Semaphore. That's the only task here. Although you might say, Aaron, why it is necessary? No, it is not. It's kind of that how you utilize your knowledge of Semaphore to build up existing libraries, whatever you have. How will you implement them by using a simple Semaphore? That is kind of low level stuff which we are trying to teach you here. So what will happen? Obviously, I know my target. I will start explanation that I will have 2 reader threads and 1 writer threads, and I will start all of them. And again, my reader threads will try to lock. So reader threads will have their own lock and unlock method. Writer threads will have their own lock and unlock method. Now imagine, now again, you have 2 reader and 1 writer threads. Now let's say reader thread, what they are trying to do, reader thread will try to lock, do some task, and then unlock. Same way, writer thread will try to lock, do some task, and unlock. So let's say reader thread got the chance. So if reader thread got the chance, which means that reader thread will have to lock. So I have 2 threads, R1 and R2. They will both try to lock, right? But I want that the moment R1 or R2 is trying to acquire a lock, I want that writer should not be available, because if reader or writer, again, although in theory I should let both of them read, but I can let both of them read provided there is no writer thread. So the first reader thread should will have a responsibility to check, can we actually acquire the lock or not? Which means that there should not be any writer thread who has already acquired that lock. So which means that there is only one lock, which is the writer lock. That is the reason I have one writer lock. That's it. So this one writer lock will help me say that is that lock acquired. If this lock is acquired by anyone, either reader or writer, if it is acquired by writer, reader cannot read. If it is acquired by reader, then writer cannot write. That is the, again, if you don't know about read-write lock, please go and watch the previous section of this course. Now, we write, okay. And again, to actually handle this, I'm just letting only one reader to go inside and try to increase the count just to indicate he is the first reader. He came up to check, can I acquire a lock or not? Or is there any writer lock acquired or not? So he is the first reader. He will come inside. The first reader indication is by the count. Because he is the first reader, the read count will increase to 1. If it is increased to 1, it is the first person who came inside as a reader. Thus, his task is to acquire the write lock. If it's already acquired, I will be stuck here. But if it is not, then I can simply acquire it. Yay! So I will acquire the write lock. So write lock is acquired by reader, because with that, the writer can also not write while the readers are reading. And then when this reader is done, he will simply release it. When he releases it, the other reader can simply come inside. He will increase the read count to 2. Now he don't need to acquire any lock. No. Why? Because already the lock, the write lock was acquired by the first reader. He was indicating that, out of the entire reading people, the first reading person will be the hero or will be the king, and he will keep the lock with himself so that all the other readers can read and no writers can write. So all the other readers coming in will not acquire or will not be needing to acquire the lock because they don't want. Already the lock is required by one of their leader readers, so they are pretty much good. And with that, he will also come inside and he will also release the lock, let's say. Now, what has happened so far? So far, both reader R1 and R2 have acquired the lock, as in writer lock has been acquired by one of them, but now both of them have come inside, have got inside this lock read method. So when both of them have come inside this lock read method, now they both can perform this task. Right? They both can perform this task. Now, obviously, you will see that writer thread was also on meanwhile. So obviously, writer thread can also try to write, or I can say, just simply lock that write. But when the writer thread tries to come inside, he will try to take a lock on write, but he will not be able to take it because readers have already occupied it. And to be more specific, reader 1 has already occupied it. Thus, my writer cannot take it. So my writer will be stuck here. My writer is still stuck here. He hasn't written yet. So what will happen? And when will my writer will be able to write? Obviously, when the readers will release the lock. And how will the readers release the lock? Only when the last reader will go out. So when I say unlock, what will happen in the reader? That firstly, I have two readers, R1 and R2. R1 comes up, right? Acquire the lock, decrease the count. Again, why am I acquiring a lock here? So as to just, decrease the count atomically and also checking the condition. That is the reason I am just having another lock outside. So what will happen? My reader lock will come here, decrease the count. The count has become 1. From 2, it has become 1. Has it become 0? No. Okay, then release the lock. So reader 1 has gone away. Reader 2 came up, he decreased the count. Now the count becomes 0. As soon as the count becomes 0, he will say that I am the last person from the reader group to go outside the critical section. So please make sure that you release the writer lock, because obviously elsewise the writer lock will not be released. So now the writer lock, obviously one of them has gone away, right? One has already gone away. Last person before going away, he will release the writer lock, and thus as he releases it, he will release his own lock, and then he also release the writer lock. As soon as he releases the writer lock, now my writer is free to come inside and writer will acquire his own lock. And again, if there are multiple writers, no, only one of them can acquire the lock. That's the beauty of writing. And obviously, the writer will perform his own task, and before going out, he will just unlock, or he will simply release that specific permit. And with that, I will be able to achieve the same functionality of read, write, locking. So what happened here? My multiple readers was able to read only when all of them ended up finishing. Only then my writer was able to start and then finish. That is how you can use your Semaphore. So I hope that you guys got to know about Semaphore. It is very important. You will see that we will be discussing these Leetcode concurrency interview questions. These will involve a lot use of Semaphore. So please make sure that you guys understand exactly what Semaphore is. And that is the reason we try to implement the entire read write log for you, the entire barrier pattern for you, and also, binary Semaphore and counting Semaphore, so that you understand how exactly your Semaphore work, how multiple threads can actually access that critical section, and especially how multiple threads I can control that how many threads can actually come inside. Cool. Let's go on next to our one of the most important thing, which is Java concurrent collections. It's very important. Let's go on to it. Now proceeding ahead with one of the important to know about, but not so important to go in actual depth, but still we'll go on to a bit depth. Now, this is going to be a bit big section because we're going to discuss few important concurrent data structures, or you can say concurrent collections in Java. Now, are all of them important? Not really. Only the first one is very, very, very important. Rest all, if you want, you can ignore as well. But still, I will say you can go through them. At least you will know about their names and a bit background on how they work internally. But make sure if at any point in time it feels a bit hard for you to grasp anything, because again, all of them I will go on to the internal working as well. So, how does concurrent hash map work? How does copy on write array list work? How does concurrent linked queue work? And so on and so forth. But if any point in time you feel like, oh, it's too much, no worries. Just make sure that you understand what is concurrent hash map and also how does it work, because this is the only one which will be very, 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 very highly used. Now, before we proceed ahead, there's one general stuff which I hope you guys would know. For any collection or data structure which you would have, any collection or data structure, let's say if it's an array, hash map, set, queue, stack, anything, if there are multiple threads who are adding something onto stack or array or anything or hash map, obviously they will have corresponding collisions and can result in a corrupted state. This is the same thing which you have already seen considering even a simple variable count. Even if I do a count plus plus, we have already seen that how this becomes corrupted. When I say corrupted, which means getting an incorrect value of what I could have actually received. That's called as corruption. So if let's say I wrote 123, or this is the correct, let's say this is the correct value. If I'm getting 120, or let's say 124, or let's say 125, or let's say nothing, this is a corrupted state. Now let's start off with Java concurrent collections. As I mentioned, that these are specialized thread safe collection implementations, obviously designed for multi-threaded environments. Now we will study major ones, and again, whenever I'll stress this is very important, only make sure that this is important, and then again I will specifically tell that you can skip this, you can skip this, you can skip this, it is not that important. And also I'll also tell this is not even important to even learn about or even know about its internal working. So make sure that you focus on what I'm referring as important. First one, concurrent hash map. I cannot stress enough, this is very important. I cannot stress enough, this is very, very, very important. Now basically you know that we are using a concurrent collection of what? Hash map. So we will see a bit about hash map, and then we will see a bit about concurrent hash map. Now let's see a bit about hash map, simple hash map. So basically a simple hash map is not thread safe as similar with other data structure. If I want to make it thread safe, I have to lock the entire hash map. Same thing which we could have done in any normal general scenario. Any Tom, Dick and Harry would have done the same thing. He would have locked the entire hash map, which means for every read and write operation on my hash map, I will have to do a lock. Although you will see that there are inbuilt synchronization mechanism to wrap around a specific collection to make it synchronized. But obviously, whenever I do this, I'm ultimately locking the entire data structure, right? Now, obviously, when I lock the entire data structure, it becomes what? It becomes a performance bottleneck. Because in high concurrency scenario, there are multiple threads trying to access something, maybe doing a read, maybe doing a write. If you lock something entirely, for every read, they have to come inside, they have to acquire a lock, which is obviously bad thing. So we got as a concurrent hash map as a remedy for it. It is specifically designed for concurrency. What it does is it splits locking, or I can say it uses a non-blocking technique. Now, just a quick caveat here, like whenever I'm referring non-blocking technique or optimistic locking here, you can easily understand that I am referring compare and swap underlying hardware technique. Although I will discuss about compare and swap. Again, in Java we use compare and set, but this is how actually they get things working. Again, do you have to go in deep? No, not really. Will I tell you about this? Yes, I will. Now, let's proceed forward. So what can happen is that multiple threads can operate on it without locking the entire structure. because again we'll see why and how. And thread safety is obviously inbuilt in my concurrent hash map, and I don't need to do any manual logging. That's not required. So this is kind of theory portion. Let's see how exactly my hash map works. Now I hope so, and I for sure bet many of you would not be even knowing right now how a hash map works. Now obviously hash map is separated into buckets, right? So we have these keys which are hashed out, and again to actually store, each bucket holds a linked list. Now we also know that it starts as a linked list, but the moment it grows higher, and again this is a threshold which can be tweaked, but it is typically it is converted to a balanced tree, again typically a red black tree. This is how exactly your hash map works. Is this required internal working? Not really. But still, I just want to touch so that if anyone asks you, you should know about it. Now, when you put any key value pair, obviously you find a hash code of the key, and then you determine that which bucket it should ideally go to. And if there is already something, then you put it as a linked list. And again, if there's hash collision and there are multiple things placed into it, it starts with as a linked list, but then convert as a tree. And again, red black tree. And again, we have a couple of PMs operation: get, put, remove, and so on and so forth. Now, how does a concurrent hash map works? So basically, I divide the entire hash map into segments. Now, earlier it was called as segments. Now it is called as buckets. Logically, it is same thing. So what happens is that I now acquire lock on each segment or bucket rather than the entire hash map. So which helps us that for different segments, I can, multiple threads can actually access different segments simultaneously. And that's what makes this much more performant. So I have fine locking at bucket level. Now again, as I was also mentioning previously, that we have optimistic locking via SAS, compare and swap operation. Again, whenever I refer optimistic locking, I refer non-blocking operation. That is what I was referring. And again, for read operation, there is no locking required at all, because whatever was the current state at that point in time, it takes that snapshot and then iterate on it. And that is how you can simply achieve that specific read operation without doing anything. And my reads can proceed optimistically. Now again, when I say snapshot, per se, it doesn't make a snapshot, physical snapshot. No, it is kind of optimistic snapshot. Just saying, okay, I assume that whatever I have right now would have never changed it. So I just simply keep on consuming whatever I have, from that specific hash map. Now, why I specifically mentioned that this is not actual snapshot, because you will see the next we will see as copy on write array list. That makes a literal hard copy of your entire data structure or entire collection. But here it doesn't. It actually believes on that optimistic locking. That okay, I can just simply go about. Again, when you apply lock, that's a pessimistic lock. You have to apply it, and if the person cannot apply, they have to wait. But optimistic lock, again, as we mentioned, via compare and swap, it simply says, okay, I'll try locking. When I say I'll try locking, which means I'll compare and swap, which means I have gone inside. I will compare two values. If they are same as what I expect, I will change it. If they are not same, which means someone else have modified the value, I'll come back and try maybe again later, because I know that things have modified in the meanwhile. Now, obviously, hash map to achieve concurrency will have to log the entire stuff, which means that all the operations will require the entire map to be logged, and obviously it will limit your concurrency very severely and will result in a very low performance. So in a simple system, this is how a simple hash map would look like. You have to do the entire locking of this entire hash map. Obviously not good thing. So what will happen here, that even if the one thread is putting a new entry in my hash map, obviously all threads must wait, because ultimately I'm locking the entire hash map, and they will have to keep on waiting until the first thread finishes. While in the concurrent hash map, I did via buckets, and again, rather than one lock on the entire hash map, different buckets will be locked. Although if there's hash collision and then for the same bucket I want to do something, obviously that they will have to wait. But if let's say some other hash key is being modified, added, performed, in that I don't need to do anything. And that is where the beauty comes in of my concurrent hash map. So what happens here is that each segment can have concurrent access being done. And that is how your concurrent hash map works. For example, if let's say you have 16 segments, there can be 16 threads who can perform the right operation simultaneously at the same time, obviously making sure that all of them are touching different segment. Now, with that, these threads reading data usually don't even need a lock, because as you mentioned, that we will kind of believe on the optimistic locking behavior, that we just simply go and just read whatever current state we find out, and it's very efficient for read heavy workloads. Again, for write heavy as well, it's pretty good, because now I am individually going on and targeting the buckets. But for read heavy, I'm just kind of believing, okay, whatever current state I have, that is the correct state, and I will just simply keep on reading whatever the current state I would have. Obviously, what if the things would have changed? No worries, I'll ignore it. I suspect the things would have never changed, or even if they change very rarely. So how does the code look like? Now, we would have used a simple hash map, but obviously, as I was mentioning, there is synchronization, like synchronized map. This is how I can synchronize it. So I can wrap it around synchronized map just to make things synchronized. So what will happen? This entire hash map will be logged at every operation, obviously limiting the actual freedom which we have, or limiting the performance which we have. While the concurrent hash map, it's pretty straight and simple. Concurrent hash map, again, the same way how you define a hash map, the exact same way you write the concurrent hash map, exact same way. It's just that instead of hash map, write concurrent hash map. But obviously, it's already thread safe, so you don't need any such wrapper around it. Now, a simple hash map, let's say I make one thread which will add values, right? I make another thread which will iterate on things. So what will happen? Obviously, I started both threads at the same time. Now, hash map will obviously, here's the manual locking is happening, but we are saying at the same time, we are iterating on things. Now, when iterating, we need to actually manually lock. That's again an overhead, right? Again, keeping things a bit hectic. But obviously, when I use a concurrent hash map, I can simply iterate on it. Things, I can simply, write, which means put things in my hash map. I should say concurrent hash map, and I can simply iterate also very easily, because it's safe. It's super safe. I don't need any such locking or any such synchronization. For again, you will see that even after wrapping it as a synchronized map while iterating, still I had to lock it. And again, if I would have not put up this, I would have actually had to manually lock it, which is again an overhead for us. And that is the thing, we are saying that concurrent hash map is pretty good if I want to actually handle multithreading. And you will see that in many problems, like literally all the problems down here, we would be using concurrent hash map, and that's the beauty of it. Now, as I was mentioning, that here the iterator does not take a snapshot per se, or the copy of the map. It does not take that thing, but it traverses the underlying data structure, reading the current state. Whatever the current state it could find, it will just simply read that specific state. Now, obviously, as I mentioned, because it is reading the current state, whatever it could find without taking a snapshot, it may or may not reflect your updates, which your other thread could have written into. But yeah, that is kind of optimistic behavior is. I expect things not to change, and that's the reason I just was reading, thus making my read performance much better. Now, next is copy on write array list. Now, although anytime anyone asks you in an interview, difference between simple hash map and concurrent hash map, just say that to achieve concurrency, you have to synchronize or lock the entire hash map, while to do the same thing, the individual buckets will be locked. And that is how you can actually improve performance, because if there are, let's say, 16 buckets, I can actually run 16 threads parallelly, while in this only one thread can run at a time. When it is done, then only the next thread will actually come up. You don't have to go in depth about optimistic locking. You don't have to go in depth about CS. All that stuff is not required. This is, I told you, good. Although I will tell a lot of stuff in the internals for other data structures, other collections as well, but you don't need to worry about it. People usually don't know, and they don't even care that much. But yeah, on high level, you should know that, let's say, copy on write array list. You should know that, okay, a simple copy is made, although the word itself says copy. But again, even if you don't know about copy on write array list or concurrent linked queue or maybe blocking queue, no worries, no one cares. That is not that much important. Important is concurrent hash map. Now, with that said, let's move on to copy on write array list. As the itself says, it's kind of a thread safe variant of simple array list. Now, what copy on write simply means that on every write operation, I will literally create a copy, or I should say a fresh copy of my underlying array. That is what my copy on write array list is. So what it allows us, it allows us to have a non-blocking reads. And again, why non-blocking? Because obviously now there's a copy altogether. I can simply read this copy, right? Why do I have to worry about anything, right? That's the reason. I just simply can read this copy altogether. And obviously, when I simply can read the copy, I can literally have many threads reading the same copy at a time because no one is modifying the copy. So I'm pretty good with it. And that is the beauty, although there are other differences. But the best is write performance. It is fast in terms of array list, but obviously not thread safe. In copy on write array list, it will be slow because there's a copy overhead before even writing anything down. Now, simple array list, it's very simple. Internally it uses the dynamic array to store your elements, and whenever you reach a capacity, the new larger array is built up and all the elements are copied in that specific new array. This is how your simple array list works. Dynamically the size keeps on increasing. But the issue is that when you have multiple concurrent operations, it can lead to data corruption, and obviously that is the biggest challenge in any simple data structure. I cannot do all these operations because then I will have to lock it, or I will have to use a collection.synchronized kind of wrapper around it just to lock the entire data structure. Which means that if that you are doing a modification and another thread comes up and they start iterating on it while some other thread is actually modifying it, you will simply start getting concurrent modification exception. I hope so for the folks who have done CP, competitive programming in Java, they must have obviously got this error like once in their life. And again, for the folks who have done CP in C++, they have also got this error for sure. When you got this error, when you are actually modifying the data structure while you're iterating on it, this is when you get this error, concurrent modification exception, right? Because obviously the iterator will see that the collection was modified, but because while iterating it was modified, that is when you will find concurrent modification exception. But your copy on write array list simply says that I will maintain an immutable array as a copy, and I'll only change the actual thing by creating a new instance so that reads can happen parallelly and write will actually happen on the new instance altogether. So all the operations can be done easily. How? Because the entire array is copied now and the new version is created with all the corresponding changes which I have. And now if let's say I do some additions or writes, now I know this is a new state, I will copy it back and say now, again, like when I say copy it back, I mean, I'll say that now I will reference and I'll say this is my new array. So firstly, if it was my existing array, I'll make a copy to do the write operation. Now everyone can still read from this. When the write is done on the new array, when it is done, then I will simply reference and will start pointing up here. That is how simply things can be done. With that, what happens is, because there was already a instance of my array, so it helps me to enable non-blocking reads, because obviously everyone can come up and simply start reading, and iteration can also happen. And obviously when iteration can happen, because other instance of the array is being modified and the first instance is simply meant for read, there will be no concurrent modification exception, right? Now obviously, as we already have said, that any of these normal data structures will result in data corruption or inconsistent states whenever we will run multiple threads. So we can use a wrapper, collection.synchronized list, and wrap the actual array list into it, which can actually help us. But again, that the issue is that the performance will be the actual performance will take a hit. And it will because why? It will simply lock the entire structure, and multiple threads, even for reads or writes, will have to acquire the lock, come inside, do the job, and then come back. So concurrency will literally be affected. And why? Because imagine this is a simple array. There are 3 threads. Obviously, to actually go and modify it, I will have to take a lock. If not, if I'm trying to modify it directly, obviously I will get into a corrupted state. Again, to refer the corrupted state, the simple thing we can think of is a simple count itself. A simple count, if multiple threads access, obviously, again, this is exact same example which we have taken already before, so I'll not explain it here. But same you can refer for a simple array as well. I want to add element. 2 people added the same point, same underlying storage or same underlying address. Obviously, they will overwrite. If they overwrite, which means they wanted it to be 5, 6, but they actually got only 6 because 5 got overridden. So that is what the corrupted state actually is, right? Incorrect state. And again, it can happen for anything. And that's the worst part about normal data structures when multiple threads try to access it. So I will simply get concurrent modification exception. I'll also get data corrupted. Obviously, this condition will come up. And to get rid of all these issues, I will have to manually synchronize it. Again, either by using collections.synchronizeList or by using my locks. But my copy on write array list will use copy, which means it will literally make a photocopy and then will do the operations on top of it, and then will replace the original copy after the update is completed. With that, one thread can modify a list at a time. That's perfectly fine, because obviously on the copy itself I cannot run multiple threads. That's impossible. To write, I will have to stop it. But obviously the read can happen as many as you want. Now the reads will be not blocking and multiple threads can read concurrently, but obviously even if the writes are happening, because writes are happening on entirely different copy altogether. Now how the diagram will look like, obviously there's original array, but to write, let's say the write operation come up, I simply make a copy first and then I will start adding. Again, on write, obviously only one thread can come up, but on read, any number of threads can actually read it directly. Now whenever this copy is done, I will simply say the new array will become the corresponding current array. Whenever the copy is done, which means whenever the write operation is done and I have added the value which I wanted, it is done, then I will simply assign the reference. That's it. This will now become my original array. So with that, what happened? Obviously the read operation were processed without blocking anything. There will be no concurrent modification exception because you will be iterating on this and modifying this. So there are 2 different underlying structure which are being iterated and modified, and obviously this copyright array list internally is thread safe without you to worry about locking or synchronization. Now example, let's take a simple array list. Now what will happen? Let's say if you add a few elements, right? This is all happening on the main thread. You added a few elements, then you spawned another thread to actually add few more elements, which is 4, 5, and 6. But you also spawned another thread which is much faster, right? This is only sleeping for 25 milliseconds, but it's still sleeping for 50 milliseconds, which means that this thread will be sleeping just so that I could have added these things completely, and it will be much faster, which means it will be reading. It will start reading before it could start writing, so that I can actually showcase that concurrent read and writes are happening at the same time. So this will actually start reading it. Now because it is reading it, it is iterating on it, and at the same time it is writing. It is writing 4, 5, 6. I am reading the entire array. I will get concurrent modification exception will be thrown here. And that is the thing. But on copy on write array list, this thing will not happen. Why? Because let's say I did the same thing. I added 1, 2, 3. Then I made another thread which will do the writing into my copy and write array list. Another thread will do the reading. Now because while I started writing, it would have made a new copy altogether, and that copy was being read while reading. So this reading would be happening on the copy which was made up of when I only had the elements 1, 2, 3, while this writing is happening on the like this reading is happening on the original array while this writing is happening on the copy. So on the copy, I'm just writing 4, 5, 6, while the reading only know I have elements 1, 2, 3. And then when this writing is completed, it will reference back, which means original array reference back to this copy array. Now what happens when I start it? What will happen that I will read only 1, 2, 3, but then writing would have been still happening parallelly, and my final array would still have the values 1 to 6, 1, 2, 3, 5, 6. While in the first case where I was using a simple array, as I started reading, obviously I will get into a concurrent modification exception because the list got changed while I was reading. Again, writing can still happen parallelly, but again, reading will give you issues. And again, writing was also still happening parallelly because I was only having one thread. So this was kind of to showcase the collision between reading and writing. This was to showcase collision between reading and writing. But obviously, the best part about your simple concurrent will be that I can do multiple concurrent reads while I can do also writes parallelly. But again, finally, you will see that writes are also there. Now, with that, you know that what is your copy on write array list. It is not that much used, but still good to know about it. Next, we have concurrent linked queue. Now, is it important? Not that much, but you will see that we will use concurrent linked DQ into our bounded blocking queue problem. Can we use a concurrent linked queue? Can we use a concurrent linked queue in this problem? Yes, we can. Yes, we can. And that is, again, although in the same collection down below, we will also see a blocking queue, which is exactly what we will be implementing here as well. But again, as I mentioned, that yes, it has a bit of significance. It is important. So again, whatever I'm teaching in this entire course is important. It's just that how much something is important in the importance criteria itself. That is also I'm focusing. When I focus, let's say concurrent hash map is very important. It is actually at the top of the pyramid of being important. And then, okay, you can say you will have concurrent linked queue, you will have copy on write array list, you will have your blocking structures. So this is inside the importance criteria. This is their own individual importance criteria. That is what I am saying right now. Now, coming on back, as you can see that it is a concurrent version of linked list. Again, for the folks who don't know, to implement queue, we actually write the new linked list, right? This is how we implement the corresponding queue. So it's a thread safe version of your actual queue. That is your corresponding concurrent linked queue. Now again, because again, if the folks who have watched the previous portion of this crash course, when we're discussing about producer consumer problems, when we were discussing in semaphores, all that stuff, we also discussed about producer consumer problem. And again, here also we discussed entirely about producer consumer problem. So this, again, for the folks who don't know, please continue watching the video. You will just realize what exactly is producer consumer, but I guess you should be knowing about it. So this is kind of, you can use for simple multi-producer, multi-consumer scenarios where you have high throughput concurrent systems. Again, obviously, if you are using concurrent collection, you are targeting high concurrency. That's obviously the case. And obviously, the best part is it is lock-free and wait-free access, which means that this will not make a copy. No, this will use your CAS, compare and swap, which means the underlying implementation is compare and set. That is what it will use to build that optimistic behavior to attach links. We'll see how, but yeah, let's continue. So obviously we use our linked list, in general sense, and even linked list or your simple concurrent linked queue. Again, linked list is actually, when I say linked list, I am referring queue only, right? So like do that change, keep that I'm interchangeably using them. All of them have the same corresponding methods, no doubt on that part. But the actual fun starts when I do multiple thread access. Obviously, in the simple linked list or the queue, I will get data corruption and inconsistent state. And obviously, if I also iterate while modifying, I'll get concurrent modification exception. This is bound to happen in a simple data structure or a simple collection queue. But my concurrent linked queue it gives me a or it takes a non-blocking algorithm. Again, as I was mentioning, this non-blocking algorithm, it's built on atomic compare and swap operation. This is a like hardware level thing, right? You don't have to like worry that much about it. And if you know about it, then well and good. Although I will tell exactly how it works, but still, it's good if you know about it. If not, then it's completely fine. But still, this is good to know about that. How does these non-blocking operation works? Again, when I say a simple lock is a blocking operation. Other thread have to wait for it. But these kind of operations are not blocking. Like they doesn't let any other thread, like other thread will come, check, okay, it's not correct. Okay, he will go and do something else or maybe try back again later. So this is not blocking any thread. That's the reason they are called as non-blocking algorithms. So it will try, like it will allow multiple threads to progress without any locks, right? This is the beauty of it. Now, what exactly is compare and swap? Because we have already seen it twice, one in concurrent hash map and other now. Let's see how exactly what it is. But again, not needed to go into much deep. So it's basically a hardware supported atomic operation. You know, like the way you have atomic integer, right? All that stuff. Similar way we have compare and swap. Now it works in two steps. We have compare, which means I will read a value from the memory location and compare with my expected value which I wanted. And then if they are same, right? If the current value is equal to my expected value which I wanted, then I will write the new value to that location, right? This is how actually my compare and swap works. And again, if this operation fails, which means these values are not same, which I wanted them to be same, and are in why they will not be same. What if some other thread would have changed it in the meanwhile, right? In that sense, I will say, okay, these are not same, which means some other thread came up and changed it. In that way, okay, my thread will do some retry or can do some other task. It's totally up to what the user wants. And that is what I will use. Now, obviously, to actually implement this compare and swap, the Java equivalent we have is compare and set, right? Again, compare and swap uses, compare and set uses compare and swap under the hood, because again the underlying hardware primitive is compare and swap. So logic is compare and swap, implementation here in Java is compare and set. So what it does is it simply returns a simple boolean which simply indicate that was the swap successful or not. If not, then no worries, my thread can go and do some retry or maybe do some other task, but it will not be blocked on this operation to complete. That is the beauty. So let's see an example. So for example, I take a current node as a reference, right? And I will check the current node if it is same as that of the corresponding new node. So my reference will hold the corresponding current node, and then I will update to a new node considering my compare and set returns true. If it returns true, I will update to the new node. And what if some other thread, updated the corresponding reference? Then, okay, it will simply return a false. In that case, my operation will go to a retry or maybe some other task based on the business logic. Now, obviously, we realized that in simple multi-threaded environments, my concurrent access to linked list obviously can lead to data corruption and inconsistency. To handle that, again, we have a workaround to use collections.synchronized list. Basically, what it will do, it will wrap your data structure around this corresponding list, but it will take the lock on entire thing. And that's the worst part. Taking lock on the entire thing will limit concurrency very highly and thus reducing the performance as well. So what happens ideally in the simple case of a queue is, imagine you have a simple queue. Now you have a task where you are simply, actually looking at the head and then let's say removing the head. Then you are looking at the tail and you are adding something on the tail. Then obviously, firstly, you will lead to a corruption. Now, simply said how? Simple, like imagine that there's just one node, both are head and tail. Now I am saying that tails next should be a node, and I'm also saying that head should be removed. So am I saying that nulls next should be a node? Obviously not. And this is what you can easily see that how it can lead to a simple corrupted state. To get rid of this, you have to apply locking, which means first operation apply, get to the head, and then simply next operation, which is take the corresponding tail and then put something next to it. That's how you can go about it, just to get rid of the corrupted behavior what you can have. Obviously, the solution which we have already seen is concurrent linked queue. Obviously, it is built on lock-free design and optimistic concurrency, which means it will attempt to acquire the lock without acquiring the lock. That's the beauty, via compare and swap. Which means if it will check if the structure has changed, then okay, hold on. If the structure is unchanged, then I will go and do the operation, whatever I wanted to do. What if the structure has changed? Which means some other thread would have changed the structure. In that sense, I should go and do a retry. And I will do a retry until I'm successful, or maybe I can drop my operation as well. It's completely fine. I can simply return whatever I drop. So the thread will not block any other thread, which means, let's say if I have two threads, these will not be blocked on each other. It is not like that, okay, one thread will complete the job and then when it is done, then the other thread will be free and then do the job again. No. One thread will see, okay, the state has changed, which means some other thread has modified it, or then I should go and do something else. And yeah, in that sense, I will be good. So there's no waiting or lock contention here. So obviously it is benefited for high throughput and multi-threaded performance. Again, right? Because I can do much more stuff. So what I do, I simply, let's say, I have a head and I have a tail. Now there are some updates coming up dynamically. For example, that you have a simple compare and swap pointer. Now imagine that you have your last node I have put up and this corresponding tail. Now if my last next is still null, which means no one has updated it yet, in that sense I will simply say if it is true, then I can successfully append a new node, and now I can try to update my tail pointer to this corresponding new node. But if this would have already been something, which means it is not null, which means that someone has already attached something on top of it, I should not touch it and I should retry, or I should do something else. And that's how I can perform that operation. Cool. And again, if the your compare and swap operation fails, because again, how it can fail, only if another thread would have made some concurrent change while you were actually doing that comparison and you could not swap it, then I will say that my current thread can retry the operation. And again, it will reevaluate the entire structure and will update things accordingly. That's the beauty of it. And with that, I will ensure that there is no blocking happening at all. Now, there is a small difference between simple copy on write array list versus your concurrent linked queue. Why I'm telling, obviously you must have realized so far that on copy on write array list, you actually were making a duplicate entry of the array each time you were doing any write operation. You were making the corresponding copy. So it is good for reads. But again, you can read as much as you want, like infinite reads you can do. But if you have very high writes, this will actually be very costly. But on concurrent linked queue, basically there is no copying involved. I just update my corresponding node references as I do CAS, and that's the beauty, that it will be very fast. Obviously, in terms of writes, and there will be no memory overhead because I'm just simply keeping one copy of everything and giving us corresponding stable structure. Again, if there's a mixture of read and writes, it can go not that as fast as copy on write array list, because obviously, let's say if read is coming, then write is coming, then only one could come, then other will retry. So there are many nuances to it. But obviously on write, it will be much faster in comparison to your copy on write array list. Now, how it would work? Imagine that you have a thread 1 and let's say thread 2. So obviously, like this thread 1, let's say, is pointing to the corresponding head. Now it will simply read the head. It will say I am the A node, and then my next node is a node B, and I want to swap, and I want to say that okay, this is the new head, because I want to remove the node from the head. If I want to remove it, I'll simply say okay, my next node is B. It should be B. It is B. Okay, I'll simply do a compare and swap, and I will simply update my head to this node B, and it is removed. Same way, if I would have, let's say, added a new node in the tail. So let's say this is the current tail. Now I will check the actual node. Right now I am at D. I want to add a new node after it. So I'll firstly make a new node, let's say E. I'll say that, okay, this is the D, the current tail which I have, and its next is right now null. Okay, obviously I will simply, obviously I had made the new node E. I'll attach it and I will put the new tail as this one, E. And thus I again, so you see that it is checking, am I at the correct state to apply or to proceed with the operation? If yes, then proceeded with it. So with that, I can proceed my operations without blocking anyone. And with that, there will be no logs required per se. And obviously I will get high throughput, and multiple producer and consumer can actually do the production and do the production and consumption at the same time. Now, many of you might start arguing that Aryan, I have different way to go about it. I can make, copy for in this scenarios. I can make do, I can do this thing. I can take logs from this thing. I can do rather this. Yes, there are multiple ways to go about and achieve the same stuff. But the catch here is that we should know the underlying implementation, how these data structures are implemented. How copy and write array list does, how concurrent hash map does, what does your concurrent linked queue does, and so on and so forth. Is it asked? Not really. Like, no one has asked me ever, but it is good thing to know about. And if you remember, then well and good. If not, then okay, completely fine. But yeah, there are multiple ways to go about achieving the same stuff. It's only a catch on how fast things are and on how people read and write. What's the read write pattern for any data structure, and also what you have built, how fast it is. And that is the reason, again, like Java is not built in a day. It is actually pretty old, and people have built it, with strong, feedbacks. Again, it is still building. Like, that right now, I'm not sure like how many folks that right now we don't even need to write that boilerplate code which we used to write earlier. So yeah, that's how Java is building. So again, there was specific nuances of why this wanted to have a array, your like copyright array list, why it actually needed a copy, and why it could not rely on simple snapshots as what my concurrent hash map does. So again, these are kind of nuances of how fast, what operation you need, and then how much affording you can actually have. Considering I have simple memory space, it's much more easy to have a copy of it entirely than actually making stuff. And because again, if you know that if in a simple array as well, you make a new copy altogether and then copy the entire stuff. That's how the things are built. Now, continuing ahead without spoiling your more brain. So simple example that we have a simple linked list. Again, it's a simple queue. What I will do, I will simply do 1000 writes, which means 1000 addition, and I will do reads as well. But when I am reading, I will say, again, both are running parallelly. I'll simply realize that, my count firstly, okay, I'll simply try to see the count, but my size, what do you think? What will be my size? You are reading, and which means you are writing and you are removing. So here you are adding elements, here you are removing elements. So adding, removing, obviously happening on a data structure or a collection which is not concurrent, which cannot handle concurrency. Obviously you will reach in a corrupted state, which means that you will still have some elements left. Ideally, you wrote 1000 elements, you removed 1000 elements. So ideally you should have a 0 here. But no, because the things can overlap and you can actually run into situations. That's the reason you will end up having you can have a 0 number as well, but if you run it thrice, 5 times, 6 times, you'll realize you'll actually get a non-zero value. While on the other hand, if we have a concurrent linked queue, again, and I do the same thing. I do, let's say, 500 writes. I will do another 500 writes. I'll do pulling out of another 500 elements, another pulling out. Obviously, in the very last, we will see I wrote 1000, I removed 1000, my answer will be 0. And that's what actually will happen. Again, all of them was happening concurrently, which means all read and writes were happening concurrently. When I say read and writes, I mean like adding element and removing elements from my queue. And again, as I mentioned earlier as well, we have concurrent linked queue. Same way we have concurrent linked DEQ as well. And this is concurrent linked DEQ is what we have used in this problem. of design bounded queue. Now, proceeding ahead, but before that, just giving a quick stuff that our linked list can actually give us this condition and internal state corruption. And there is some items which may never be removed, or some insertions which might be lost entirely because of overlap. And thus, because of conflicting updates and stuff, I might miss things. While in concurrent modification exception could come, not really, because you were not reading stuff, you were adding and removing stuff from it. It was not reading per se, it was you were just maintaining the count while running a loop. It was removing stuff and adding stuff, and thus concurrent modification exception comes up when you iterate on stuff, right? So that's the reason you will not see a concurrent modification exception here. Why I put this point here is because people might get confused. Aryan, why did you not show a concurrent modification exception as what you have been showing in the previous collections? Because obviously we are not iterating on it per se. Now, next one is a blocking queue. Is it important? Not really, but still, let's see. So blocking queue, again, it also has a word queue. So how is it different from a concurrent linked queue? That's the first question. So basically the only difference between simple queue, when I say simple queue, I mean a concurrent linked queue, and a blocking queue is that it will wait or it will block. If the queue is empty, I will wait until some element comes up. If the queue is full, I will wait until the queue becomes, until I can actually do some things. Again, this is while inserting, this is while removing. So while removing, if the queue is empty, you will wait. While inserting, if the queue is full, you will wait, which means you will block. That is your blocking queue. And exactly this is what we would be implementing here, design bounded blocking queue. This is exactly what we will be implementing by using semaphores. So what it is used in, obviously, as a consumer producer pattern problem. Now, in a non-blocking queue behavior, for example, a concurrent linked queue, basically here you don't have anything, like you simply used a CAS, right? Compare and swap. But here in blocking queue, you will use explicit locking. For explicit thread coordination, you will use locking, reentrant lock. Right, again, if for the folks who don't know, we have already discussed what reentrant lock is. So we can just check locks and type of locks. Then we have discussed reentrant lock is the most important lock which you should know no matter what. Even if you forget about cached, new cached, cached corresponding, even if you forget about any other lock, it's completely fine. But you should be knowing about reentrant lock. Again, if you forget even about read-write lock, stampede lock, no worries, I don't care about it, but you should know about reentrant lock. Okay, now coming on back, we realize that okay, that's one thing that we will use explicit locking, but also that the threads will have to wait when the queue is full, which means the producer will wait. If the queue is empty, the consumer should wait. And obviously the condition will change as soon as the insertion or removal happens from my buffer. Buffer, I mean the corresponding data structure. There are a couple of common blocking queue implementations. We have array blocking queue, we have linked blocking queue, we have priority blocking queue, we have delay queue, and so on and so forth. All of them have this blocking operation in them. Do we need to go about it in deep? No, not really. So yeah, if you want, you can read about them, but again, not required to actually go into deep into them. It's just if you know about this blocking queue itself, it's perfectly fine. The only thing is that non-blocking queue will simply return immediately without waiting for what? If the queue is empty or if the queue is being modified. What I mean by that is that imagine you have a simple concurrent linked queue and it is right now empty. I just called a poll. Poll is happening on an empty queue. What should it ideally do? In the ideal sense, it should stop. It should stop for something to enter inside it. So what it will do? It will simply return a null, but it will not block. It will not wait. It will simply directly, because it is empty, it will return a null, and then I will simply get a null here. So what happened if I just show the output? Yeah, this will be a null. And again, if I add something, then okay, if I do a poll, I will get a 42. So this is your simple non-blocking behavior. So what happened here is your poll and add methods execute without causing the thread to wait, which means that they were showing a non-blocking behavior. While in your linked blocking queue, which let's say we are using a blocking queue, a linked blocking queue we are using, what will happen is if I have a thread which will insert some data, let's say after 2 seconds, and then I, on my main thread, I just ran a simple thing called as take. Simply take whatever you have. Now, although right now when I ran take, currently this thread did not run. This thread did not run yet, right? Because again, when I say did not run yet, because it will run after 2 seconds. So what will happen in this case is it will block. It will wait. As soon as after 2 seconds, the data will be ingested. I have 99. Then it will give you 99 back. And then it will print your number 99. And that is what your blocking behavior is. And that's the only difference. That's the only difference in your blocking and non-blocking queue. Cool. Last thing, again, not linked to anything, but there's one question which people might ask you sometimes. What are fail fast and fail safe iterators? Basically, fail fast, as the word itself says, fail fast. So basically, I can throw concurrent modification exception if the collection is modified while iterating, which means fasting, like failure is achieved fast. And again, in the simple collection which I have, array list, hash map, and so on and so forth. While fail safe, it's in concurrent hash map, copy on array list. So basically, I operate on the snapshot of the data, whatever I have, and basically the iterator will take that snapshot for its actual iteration process, and it will not throw you this concurrent modification exception while you're actually iterating on it, which ultimately ensures the thread safety. That's the only thing what you should know about thread fail safe and fail fast iterators. Cool. I hope you guys liked it. Again, in this entire lecture, you should remember firstly the names of copy on write array list, concurrent hash map, concurrent linked queue, and so on and so forth. And specifically, you should know about the implementation of concurrent hash map, especially how it locks on individual buckets rather than taking a lock on the entire hash map. Cool. I hope you guys liked it. I hope you guys will remember at least concurrent hash map. And now we'll go on to one of the important ones which people rarely cover, which is future and completable future. Again, in this also I will specifically tell that what you should focus on. We will primarily focus on things in completable future, because again, future's advanced version is completable future. There are many methods in it, but not all are important, or not all are even significant, and people get confused a lot. And to reduce that confusion, we will see the most important ones and how not to get confused. Let's see future and completable future now. Now, one of the last concepts which we're going to cover here is future and completable future. Now, are they going to be used in these Leetcode problems of multi-threading concurrency? Not really. These are primarily used in your production code basis. If you are in any company and you are writing a multi-threaded code, always you will be using executors, you will be using your Java concurrent collections, and you will be using future and completable future. Again, this highly unlikely, again, you will be using logs and stuff if required, but these you will find no matter what. Again, see, I'm specifically saying that if you are using or if you are writing a production level code, is it important to write a concurrent code to involve all these? Not really. We can go to lower level stuff. We can go to logs, synchronization. Primarily, you will see that people use synchronization in any of the code because it's hard for other people to understand logs. But after this crash course, I hope so, you will be comfortable. Again, if not, please make sure you watch it again, because as I mentioned at the beginning of this course, it is cyclic in nature. The concepts which you learn right now, obviously, will be used, maybe future, coming back in past we learned something, that is what we're gonna use in future, and so on and so forth. Now let's start off with future and completable future. Now This is a small brother, this is a big brother. Now, they are primarily used in asynchronous programming. What I mean by that is, in very simple terms, it's simply, again, this future word. Again, only and only forget about this word, complete future. Only remember about this word, future. The extension of this future only is the completable future. So right now, forget about this word altogether. Only understand about future right now. Again, people always get confused about what this future is. Future simply represents anything, any asynchronous computation which happened. Like, right, when I mean by asynchronous computation, imagine that you spun a thread and then you let something process on a separate thread. Let's say, and it will take 10 minutes. Although it's a very big time, let's say it takes 2 minutes. You let it process, and then the result of it, whatever result of it, that is put in what? Future. So basically, future represents the result of this asynchronous computation. Again, it will be computed later on. Obviously, let's say if you spun this thread and you let it process, it will be completed after 2 minutes, but it will be put up in this future. And CompletableFuture is kind of a bigger brother of future, advanced version, flexible version, which will allow you composition, exception handling. Arun, what is composition? For the folks who have seen streams or have learned about Java streams, you know that we have dot and then we can just call some method, then another dot. Again, even if not, then I hope so you guys must have at least watched builder design pattern in this LLD series. You know, in that you can chain stuff. That chaining is nothing but how you achieve composition from that chaining. Now, with all that quick idea of what exactly a future is, and again, even if you don't understand this, forget about it, we'll see it, but I hope so you got the idea of what exactly a future is. Anything, you know, any asynchronous task which is done or asynchronous computation which is done, its result will be put in a future. That's it. So you can imagine your future as a container which will have a result for some asynchronous callback in future. Now, why this is helpful? Because it helps us to work with the results which are not immediately available. For example, if I do int val, this will represent, okay, I should have an integer. Even if I call a function, I will get that integer right now. But with this future, I can keep that result in a future, and I know it will be coming in future only. It will be coming in future time only, but I'm keeping that result in this specific container, right? Because again, I don't know when it will be available, but obviously it's a non-blocking call. What I mean by that is, non-blocking operation here mean that I will simply let this thread spun, let it compute its computation, let it complete, and then I will put the value in the future. This will not affect the main thread which is processing the thing. It will be computed in its own time and will come up here. Again, it can be a bit tricky to understand in the beginning, but keep on going with the flow. I'll bet you'll understand for sure after this video. Now, as you already saw that I can have multiple ways, right? Like to check if the computation is complete, and I can wait for its completion. I can retrieve the results. There are multiple things. Again, this is a bit of theory. We will see with example literally everything. So hold on, keep tight. When I say retrieve a result, as I mentioned, that we have a future. The task. So what happens? Again, I hope so you guys have already seen ExecutorService and executors and stuff, and I hope so you guys have remembered that why I mentioned that, you know, it is very important. So here we have taken a single thread executor. Now I'm just simply saying that in my executor I'll submit a task. That task is just to do an addition. Now, right now it can take just 1 millisecond. But what if in this task I have put up, let's say in this I have put up any task, let's say that would have taken 2 minutes. 2 minutes. So this future, whenever this task after 2 minutes is completed, then it will put up the value here, right? This is kind of a placeholder. Imagine it as a placeholder. Now, my main thread will still keep on propagating. So what happened? My main thread came here, it executed this, okay. Then it came here, it called this because this will take 2 minutes, okay. And I know I have a placeholder. So whenever it is completed, it will come up and will be placed in future. But again, I will not wait for 2 minutes. I will keep on proceeding forward. Let's say I have some other task here in between, which took 1 minute, right? Now, again, let's say that was a blocking call and I specifically slept, let's say for 1 minute, right? Then I came up here and then I did a future.get. So whatever was placed in my container of future, right? Imagine it's a container, right? The way you have a variable, right? Every variable you store it as at some place, right? So imagine you had this. Now when you do a get, now your thread will firstly have to print it and give a result. It cannot go further beyond it. So it's a blocking call. So your main thread will actually be stopping here and getting the result. Now if you remember, I guess you should remember, you had a task which took 2 minutes or which will have taken 2 minutes. Now while your main threads was processing down below, your main thread took 1 minute. Your main thread took 1 minute in some task in between. Now when it came up here, 1 minute has already passed. So when it called future.get, ideally the task would have taken 2 minutes, right? 1 minute had passed. I still have to wait 1 minute. So this will be a blocking call for 1 minute. Why? Because again, even if let's say this would have been 3 minutes, I did some task for 1 minute. So I will have to wait for 2 minutes before my main thread will proceed for next step. That is what is called as a blocking call. All right. So this is what this will do. Now, some of the functions, whenever I call submit, I will, start the corresponding task asynchronously. So here you did same thing. You did a submit. So this task started the moment you did a submit. This task started asynchronously. And that is the reason, even if in between your main thread was doing something, this task was also running. What if you would have done some other task for 4 minutes, or maybe let's say even 3 minutes, you would have done some other task in between, right? And then when you would have called here future.get, it would have returned immediately, because by that time this would have been completed. And that is the beauty of your future, because now anything which was running asynchronously, it knows whenever the result will be done, it will be placed here. I just have to call the same thing. So submit starts my task asynchronously. Same way future.get, it blocks the thread until my task finishes and I will return the result. So it will block it until my task is finishing. Now I can also have status checking, which means I can check if thing is done. Okay, so this is a non-blocking call, right? This only checks if your feature is done or not. If not, okay. If yes, then do something. So this tells if the task is finished or not. There's also cancellation support. Basically, cancellation for tasks that haven't started, or maybe if they are still in progress, then also I can cancel them. What I will do, I will simply call cancel, and then I will simply interrupt the thread for me. Now there's a small catch to cancel. The small catch to cancel is that it tries to interrupt if the task is running. The catch for interrupt here is that I should specifically go and check that, inside my task, that how is cancellation happened or how is interrupt happened. Because when this is called, it will simply send an interrupt signal, but my Java will not stop the corresponding thread. It will only say, okay, the interrupt flag is true. That's it. It will not stop it. So I myself have to keep on checking about the interrupt. So I can use a thread.interrupt, which will keep on checking, okay, did I got an interrupt or not? If yes, then do what? If not, then do what? And so on and so forth. Again, it's not important for you to remember, but yeah, it's one thing which, if you know, it's good. Now, there are blocking operations. We have already seen, right? Future.get, it's a blocking operation. because I will block and wait for its completion. Until before it, I will not proceed ahead. Now, some of the very basic common usages of future which you will see is, as I've already seen, as I've already showed, it's kind of a placeholder for your any asynchronous task which can take any amount of time. When it is done, the result will come back and will be placed at a location called as future. Now, you primarily, the benefit is that your main thread can actually be free and do some other task. For example, in this case, you will see that firstly, again, let's say you make one thread. Here, I am just calling submit. Again, submit you have already seen that submit, right? Then I give a task. Now that task, imagine, takes 2 seconds, right? This takes 2 seconds. Now my main thread will come down, right? My main thread will firstly check, is the task done? Because I just started, right? It would have been just 1 millisecond right now when I came up here. Obviously that the task is not done yet, so it is false. Now I call future.get. Now this get is a blocking call. So this main thread, obviously it has been, let's say, only 2 milliseconds now. But this get is a blocking call, which means I have to stop until this entire task is completed. And I know it will take 2 seconds. So this will be blocked until 2 seconds. So my main thread will be blocked. My program will be blocked until 2 seconds. Like for 2 seconds, it will be blocked. And again, what if, now you might say RN, but what if meanwhile it was coming up here? Let's say I would have elapsed, let's say 100 milliseconds. Okay, then this task will be blocked for 1990 milliseconds. Not really, 1900 milliseconds. Because obviously this would have taken 2 seconds, which is 2000 milliseconds, and 100 milliseconds already passed. So some computation would have already been done. Remaining time it will take here, it will block. You cannot proceed forward. So after it is done, you will get the result back. Result will be the task completed is the corresponding future of string. So this is a string. I make a future of string and then I result it and then I got it back. So when I did a future.get, I will get this return which I was getting from my corresponding task. So my result is task completed. So my print statement will look like result : task completed. This will be my result. And when I check it again, is done. Obviously, the future is done because it has already been passed 2 seconds. So obviously, my future was done. And in that case, it will be true. So this is what your output will be. And this is for false, this is for true. Now, obviously, we saw that how beautiful the future is because obviously I can just place something, right, on top of it. And I can always ask that, okay, like, have I got it done? If not, then get me, and so on and so forth. But there are limitations of future. And that's, why these limitations are important? These are important because these will help us to know why we even needed completable future at the first place. So all the limitations which we will see right now, all of them will be handled very easily by completable future. Now, first is there is no composition. As I already told in the beginning that I have no chaining support of task, right? If I tell you like, do something, then do something, then do something, this is not possible, not possible. And again, this line is very important because this will tie back to why there need to be blocking operations no matter what, right? Again, although you saw that for blocking operation, when I mean by that is, this is a blocking operation. This is a blocking operation. But in completable future also, I have this blocking operation. But still, the limitation we have mentioned as blocking operation. And I will deep dive into the fact what I'm trying to tell here. What does this blocking operation actually mean? Because this can be confusing for new folks. Now, before we go on to the third point, the second point says that there is no exception handling, which means that there's no built-in mechanisms to handle exceptions which we have. Obviously, if you want to handle it, we have to do try catch manually, which is cumbersome. But you will see that in CompletableFuture we have dot exceptionally, dot handle. That's the beauty. That is the beauty of CompletableFuture. Now, there is a lot of blocking operation. Again, this is primarily when you have multiple things which needs to perform. What I mean by that is that you have to call .get on any future before you try to do any task on top of it. What I mean by that is, you know that .get is a blocking call. But what I'm trying to tell here is that there is one task, let's say T1. There's another task, let's say T2. Let's say there's another task, let's say T3. There's another task, let's say T4. Now, imagine this T2 task can only be done when T1 is done, right? Now, we are saying that this T4 task can only be done when T3 is done. So, with future, what will happen that when this task will complete, obviously you will have to call .get, right? And then you will be able to call your T2 task, right? So obviously, firstly it will block here. Firstly, it will block here when you get it, and then you will be able to perform this. And then when it is done, then you will call again .get. Same way for T3 task. Obviously, you will firstly get this .get. When this is done, then you will perform, this T4 task, and then you will get .get. So you realize that this .get is a blocking call, blocking call, blocking call, blocking call. So again, finally calling .get perfectly seems fine. But at this point in time, I'm specifically calling .get. Don't you think I will be unnecessarily wasting time? Maybe meanwhile I could have performed some other task on my main thread, because obviously main thread will wait on this .get, right? Same way, it will wait on this .get. It has to be blocked. So what's the solution? Solution is using CompletableFuture, which will help you to chain these two asynchronous processes after one another without even calling .get. So I don't need to firstly let it complete and then complete it manually here. No, I can simply chain them together, which means after this task, do this task, and then when both are done, I can simply call a .get. So imagine that this is now another task. Let's say T3, or let's say I should say TN, and this is another task which is TM. Now, rather than individually calling, T1.get and then manually doing and then manually calling T2.get, so on and so forth, I will just say TN.get like this. This is kind of beauty of your CompletableFuture, that you can chain asynchronous operation, thus not blocking anything else who wants to perform task, right? Again, I will show with the help of a concrete example of time and stuff as well. I will take one as 10 milliseconds, another as more 10 milliseconds, and so on and so forth. I'll explain by that also. But yeah, this is the idea of your blocking operation, which will be, again, if I have only one task and no chaining, obviously like both CompletableFuture and future will be same. But if I have chaining of tasks, then this future will actually block, and that's the issue. Now, obviously, there is no completion notification. What I mean by completion notification here is that basically there's no event-driven mechanism to notify whenever a task completes. So I have to manually go and .get or .is done and so on and so forth. I will have to keep on looping things, which is not good. While in your CompletableFuture, you have then accept, then apply, when complete. All these, you can literally attach callbacks on top of it, and whenever something is done, when my async operation finishes, these will be executed. And that is how I can attach notification on top of any task. So what we realized is that these are the limitations of your future, and obviously the same thing will be the benefits of your CompletableFuture, which means you can perform chaining, which will give you composition. You can easily perform exception handling, easily. There is no blocking callbacks. Again, this is important. You understand what does blocking here means. Ultimately, even if you chain things up, you will have to still call .join. Still, obviously, this will block the main thread, but individually they are not blocking, and that is the beauty. So you might ask, Aryan, with that I will always use a CompletableFuture, right? Why I will even use a future? I'll say you are perfectly 100% correct. You would never be wanting to use a future. you can always use a CompletableFuture. But still, where to use the future? Because it's easy to write, to understand and stuff. Because again, obviously, it's kind of basic stuff. So if that if your operation is also basic, you can use your future, which means if it's a very simple asynchronous task where you can simply have, let's say, one task, there's no chaining involved and blocking is acceptable if chaining is involved, then you can use your future. But is it recommended? Not really. You can always use CompletableFuture, and that would do your job much more perfectly in a clean manner. So obviously, if you want to use chaining, combining tasks, non-blocking handling, you will always go ahead with CompletableFuture. Again, exception handling is also perfectly awesome here. Now, the thing which I was mentioning, blocking operation. Let's give an example for it. Although I have already explained in very depth example here, but just code example. Again, the code example is also very flaky in terms of not concretely showing, but I will show you. So here, what is happening is that you are just submitting a task which, let's say, take 1 second. Ignore time for now. The time you will understand what I will tell you. So I am saying that this will take 10 seconds, right? Again, ignore time what is written. I am saying it will take 10 seconds. So it will take 10 seconds. This is my era. Like this is my my area. Whatever I'll say will work. So what happened here is that you have a thread. You just called a future, and then here you are saying that after this completes, you wanted to perform another operation, right? And I am saying that this operation will take 10 seconds, and after this completes, another operation will take 10 seconds, but another operation can only be done considering this one is done. So what will happen in your main thread? What will happen is, firstly, if you do a dot get, firstly you will block everyone else for 10 seconds, right? Which means you're blocking everyone else who could have done something. You're blocking everyone else for 10 seconds. Then when you have done this, then when you come up here next, again you will be blocking everyone else for again 10 seconds. So is the issue this 10 seconds? Not really. The issue is this 10 seconds. Why? Because in that time, if I could have actually done some task of actual 10 seconds, because again, right now this is just waiting for it to complete for 10 seconds. But what if I have some other main task to perform which could have taken 10 seconds, right? That I'm losing at. So what if I could easily chain them, right? Bro, I'll easily chain these two tasks and say after this task, complete this task, right? And then I know it will take 20 seconds, right? But in that time, my entire future will take 20 seconds when these are done. So for 20 seconds, I can literally perform any task. And then I can come back and ask, bro, okay, after 20 seconds, I can come and ask. So the entire catch here is 10 seconds asking for a pit stop and then checking and then again 10 seconds. So that is the issue. Because if I do a check right now here, I will have to block it at this point in time, while I could have done some other task at this point in time. But if I just chain them up after 20 seconds, again, even if you might argue, Arun, but what if I just have to call it, dot get, I have no other operation? Okay, no worries. If you have nothing else, then it's okay. But if you have something else which could have been done in those 20 seconds, obviously, you could have chained them together so that you don't have to individually wait for them to perform their own task. And that's the beauty you will see by using CompletableFuture, that I will simply have another composition or another chaining involved called as then except. So go in the English terms. People usually get confused in RN. How will I remember then supply async? Simple, very simple. On the CompletableFuture, you supplied a task when, and then this task will be performed. Again, keeping it very simple in English. Then you will accept something else, right? And when obviously all this is ready, then you can do something. So when all this is done, I can do something. So what happened that you do not specifically have to do a dot get here and then wait and then do it again, then do a chaining by manually and so on and so forth. No, you just did this chaining, this will perform. After that it completes, automatically this will start performing. This is the beauty of chaining. Now, obviously, when we saw the beauty of CompletableFuture, let's go a bit deep dive into different methods. Before that, we know that it simply addresses all the limitations: exception handling, composition, combining, chaining, handling async tasks, and so on and so forth. Now, obviously, some of the key features will directly come up by the limitations. You can perform non-blocking operations, you can perform combination, composition, exception handling, completion callbacks, explicit completion, and so on and so forth. Again, all good stuff you can do with CompletableFuture. Now, starting off with the first method, dot get. Do you remember something? I hope so. You must be remembering dot get. Same thing, exactly same stuff what we saw in future. This also is a blocking call, right? Now I hope so you guys will not get confused on why I was referring that your CompletableFuture gives you a non-blocking operation. It was non-blocking for chained tasks. You can perform them in a non-blocking manner. Individually, lastly, they will have to block, obviously. But that is the beauty, and that is what I try to focus on. That what I meant by non-blocking when I was referring for CompletableFuture. Now, obviously, we will have a CompletableFuture. We will simply supply a corresponding task to it, and then I'll simply get that task. Again, obviously, this will block, and then I'll be good to go. There is another method called as join. This will do the same thing as get. The only thing is this will throw unchecked exception. Now, for the folks who don't know the difference between checked and unchecked, please watch the previous portion of this course. This is a course, complete multi-threading and concurrency course, which involves a lot of stuff and a lot of problems. So we can go in the beginning portion that will explain you entirely everything about your checked and unchecked exception as well. So this will do the same thing. It will also block, but the only thing is it will simply throw me unchecked exception, which means that you should use join only when you know the exception will not come. So you will see that later portion we will be using join, but we are using join just because we know that exception will not come. So ideally you should use get. You can use join as well, because then you won't have to handle exceptions separately, else the code becomes very untidy. This makes the code a bit tidy. That is the reason we are using this. But again, repeating, in the production code basis, you will always be using get. Here we are using join because it keeps the code clean for you to explain. Next is complete with a value, which means simply manually complete a feature. Let's say if you don't want to wait for anything, you want to manually complete it, you can complete after a threshold manually as well with a specific default value. So whenever you will call get, again, you know why I'm calling join right now, right? You know why I'm calling join? Because I don't want to write big code, try catch stuff. No, I just want to show you how exactly this thing works. So it's the reason I call a join. But what you will do, you will call always a get. Now coming on that, it will simply return you this output. Next we have is done. Same thing. It simply checks if your feature is done or not. If not, then no worries. So that's the same thing as what we saw. Now your favorite, which you have been using, supply async, basically saying that I'll perform some operation in a different thread without blocking the corresponding main thread or the current thread. So what it does, it will simply say that I'll supply this task and I will perform that on a different thread altogether. And this is what it will simply do. When it is done, it will simply return me a CompletableFuture. That is what it does and how it does. Now, next, we have then apply. We saw this one as well, right? When we were seeing the chaining portion, when we do a supply async and then we do a then apply. So that's same. Now again, there are many things you can get confused on RN, then accept, then apply, then combine, so on and so forth. But again, you can keep few and use them. obviously in specific interview scenarios, you won't be able to, like, you won't be getting such complex stuff. You can keep one of them. Okay, I'll use this, and that's it. Now, coming on, then apply obviously allows us to chain, transformations, and they can be executed synchronously or asynchronously. Now, again, I am saying don't get confused on the wordings. When I say then apply and then apply async, I don't mean that obviously because you have called supply async, it will be running on one thread. Obviously, it will be running on a separate thread. So I have a main thread which was running. Then I called supply async, which will make it run on a separate thread. So this entire thing is running on a separate thread altogether. Now, when this thing comes up, it is not saying that then apply will run on the same thread and then apply async will run simultaneously or will run concurrently on a different thread. It is not saying like this. It is saying that, okay, you were using your main thread, you were using your new thread, which could have performed your task. Then apply will sequentially perform the task on the same thread. Then apply async will sequentially also, again, mark my words, this will also perform the thing sequentially, not concurrently. This will also perform the same thing sequentially, but on a different thread. Now, you might ask, Aryan, why? Why is because there is a chance that you are using an important thread. It can be an event loop or an IO thread. Now, you don't want the, let's say if I'm using this corresponding thread, that specific thread which I have, and I want to offload the corresponding work to prevent the busy or important thread from doing any heavy computation. Well, I don't want to do any heavy computation. I want, okay, some other thread, because again, this is the important thread right now. It can be event loop thread or an IO thread. I don't want it to do any heavy computation. I'll simply say that, bro, a different thread from your fork join pool will pick up this task and that will do it, but do it sequentially only. So that is the difference between your then apply, which will use the same thread, again making sure this will also do sequentially, this will also do sequentially. It's just that here you get a new thread which is not as important thread, and that will do your job, while this one will simply do your job in the same thread, right? Okay, continuing further, we have another combining policies. We have then combine, all of, and any of. As the word itself says, it combines it combines the output from two tasks. It literally waits for all the tasks to complete. It waits for the first task to get completed. Again, the example, if I have two futures, if I call a then combine, obviously I'll combine the records from both the futures. If I call all of, I will wait for all the futures to complete. If I call any of, I'll wait for any feature to complete. Any one complete, I'm good to go. Any one complete, I'm good to go. So that is your then combine, all of and any of. All of and any of. Now again, there can be a quick question around, what's the difference between then apply and actually then combine? Simple. Then apply will take one complete feature and then will transform it. Then combine will wait for two complete feature to complete and then combine their results. Again, if you want, you can actually do things, I'll use then apply only and then I'll just do the combination stuff. You can go about it. There are multiple hacks you can actually try. But again, is it required? No, maybe, yes. But again, the catch here is that these are all the corresponding functions which you can use just to make your code clean in production. In interview, not required. You can simply use supply, async, then apply, and that's it. Now, there's also, which you've mentioned about exception handling. The same thing is here, that I have exceptionally and I have handle methods. Now, exceptionally, basically just to say that, this is exception happened and I can simply handle that. Dot handle will manage both success and exceptions. So whatever you had in your supply async corresponding task performed, if exception is thrown, then I will handle exception gracefully. So I will have that dot exceptionally, which will handle exception gracefully. Same way, I will, run my corresponding task in a separate thread, but then I have dot handle, which will handle success or failure gracefully. That is how you can handle exceptions via using dot handle or dot exceptions. Now, next, although not important at all, but still there are timeouts and cancellations. So basically, this simply says that I have or timeout or complete on timeout. This will make sure that you handle timeouts gracefully, or you can provide some default value. Complete on timeout. You can provide some default value as well. So what it means here is that you will have a simple feature. It will take some time to complete. But what I can do is I can call a feature.timeout with this time of 2 seconds, because again time unit is 2 seconds. So what will happen is, if this feature, which obviously will complete in 3 seconds, if it does not complete in 2 seconds, my this specific without timeout feature will complete with exceptionally, right? Again, an exception will be timeout exception. So this with the timeout feature will be completed in 2 seconds with exceptionally, and that's it. While this specific feature, right, this will continue running up till 3 seconds, and then maybe it is possible that in future I am calling this feature.get. Possible, I can use that, but here it will say that for this feature, I will wait for 2 seconds. If it completes, well and good, I'll get the corresponding feature. If not, then this will be completed with, exceptionally with the exception timeout exception. Same way, I have complete on timeout with some default value. The given timeout is 2 seconds again. If it did not complete within 2 seconds of time, I will complete it normally with providing a default value, making sure that this feature will still be running parallelly and will still be completing in its own time. So that is your complete on timeout and your or timeout. Cool. Again, never required, never used in interviews. Again, it will be used in your your prod code basis, but not really here. And that is it. You learned a lot about futures and completable futures. Now, some of the things to recap: you have blocking and non-blocking operations which you can perform. Composition, possible with futures. Exception handling, robust as hell. Completion notification, you can have. Combine results, you can have. In total, you can do literally everything with CompletableFuture, but obviously comes with the nuances of a lot of methods, a lot of complexities and stuff, which can be a bit tricky for a newbie to understand, but obviously very highly used in your production code bases. Lastly, remember, CompletableFuture is God, like literally a God. Bye bye, take care. I hope you guys liked it. Make sure that with the like target of 250 likes, we plan to complete 100k views. If that is done, then only we'll go to HLD. And if we go to HLD, I swear you will never be needing any paid course for HLD as well. Again, this course will mark the demolition of any paid courses of LLD along with multithreading if there is. But yeah, cool. I hope you guys liked it. Let's go on to concurrency for interview questions, which will be pretty easy for you if you would have seen Semaphore video and concurrent collection video. It will be pretty easy for you. But again, the catch is to understand Semaphore and this, you should have watched these videos. Bye bye. Take care. Now, after covering all the concepts which we wanted, again, primarily you will see that mostly you will be using concurrent collections for actual LLD problems, and you'll be using Semaphore quite a lot. You'll be using locks, you'll be using synchronization quite a lot. And again, obviously, to actually manage the threads, you'll be using executors quite a lot. So these are primarily what you'll be using. Let's start off with very easy problem statement, which is print number. So basically this is that if I have, let's say, print number 7, it will simply print a 7. Your task is that you are given an instance of 0, even, odd, which means you have three functions: 0, even, and odd. You have three functions, as you know, function 1, then function 2, and then function 3. So you have these three functions. Now what they are saying is that you have thread A, which will call 0 function, and this should output 0. We have thread B, which will call even function. This should output only even number. Thread C, which will call the odd function, it should output only the odd numbers. Your primary task is to output a series like this, right? So now your task is that how will you write the corresponding code? Now think from the very base level, what exactly is happening? You have three threads, right? Always draw, always see what exactly each thread wants to do, and with that it's going to be very easy for you to perform what exactly you want to achieve. So I have a 0 thread, right? I have an even thread, I have an odd thread. Now again, they will be targeting their own functions. So thread 0 will go to the 0 function, thread even will go to the even function, thread odd will go to the odd function. Now in the very beginning, I want it to start from 0. So I want that these two should not enter their own functions, right? Even and odd should not enter their own functions, but 0 should enter. So I want that 0 can enter its own function. Now, what by the knowledge which we have already studied here, right? What you can think of as any of the logic which will allow you to, come inside and will not allow you to come inside. Imagine again, to refer this, imagine that you are going in a concert, right? You are three friends. To enter the concert, what do you want? And again, obviously if he can come inside, he will have that permit to go inside, right? So I can simply use a semaphore, and again, considering it's only one thread, so I'm good with using a binary semaphore. For the folks who don't know binary semaphore, let's go on, we can go on to the previous section where we discussed about semaphore in very depth. In semaphore lecture, we discussed a lot of things about binary semaphore, counting semaphore, we discussed producer consumer problem, and we discussed barrier synchronization as well. Now, coming on back, we realize, okay, I will make this again. So this will be a semaphore having no permit. This will be a semaphore having no permit. And this will be a semaphore having one permit. Now, as soon as he will come inside, he will execute his function. Now he goes outside. Obviously, 0 will be printed. Next, I should print 1, which is obviously odd. So I have to know that after it comes outside, he should give one permit to the odd thread. So what he will do, he will release a permit, but for what? For odd one. Again, make sure he has occupied his own permit. So his permit, considering he has acquired his own permit, so his permit, like my thread 0's permit has become 0. But obviously at this point in time, he has to call a thread, he has to make sure that he has to call corresponding thread 0. Now with that, sorry, I should say thread odd. So with that, he will release the permit for odd one. After releasing it, now again, there will be a very logical question that how will it even know that it has to call for even or odd? So I can keep it, right? Again, in the very beginning, keep odd equal to true. Go and call for odd, right? I simply go and call and increase the permit for odd by 1, which means now thread 0, thread odd can go inside in his function. As soon as he will go inside, before going inside, I will acquire the corresponding permit, and then his permit will come again. Obviously his permit has already gone to 0. As soon as he comes inside, his permit will also go to 0. Now obviously after he comes outside, he has to call 0 again, which means that after he comes outside, he will give a permit to the 0, semaphore 0. He will give the permit to him, and as he gets the permit back, he can enter inside. Now as he entered inside, obviously he will utilize the permit. Then when he comes outside, now obviously his task is to print 2. So if I just erase, now its task is to print 2, which is even. So now I should make sure that I will point it to a even, which means I will increase the permit of my even. So you realize that as soon as it comes the next time, I should, invert this value. And let's say invert it. If it is false, make it true. If it is true, make it false. With that, I will be realizing that which permit to increase. Is it the odd permit I have to increase, or is it the even permit I have to increase? As soon as it comes inside, right, it will obviously, as soon as it tries to come inside, it will try to use that permit. Comes outside, obviously, next thing it has to do is print a 0 again. So it will go and try to increase the permit of thread 0, increase it back to 1. Now obviously make it, transform it like back. It is true. Again, he can come inside, utilize the permit, goes outside. Now it has to know, it has to go to it has to increase the permit of a odd one. So it will go to the odd one and will increase the permit of it. Obviously can come inside. As it comes inside, it uses the permit. As it goes outside, now it knows that it has to, no matter what, go to the 0 only to increase its permit. So what happened ultimately? Ultimately, your thread 0, I should say your semaphore 0, will actually be increasing the permit or releasing the corresponding permit. If it's odd, it will release the permit of odd semaphore. If it's even, it will release the permit of even semaphore. But your even and odd semaphore, when they will come out, they will always be releasing your 0 semaphore's permit. And that is how you can simply solve it. Cool. Let's see the code. Now, again, I did not go into, unnecessary, all that, all this unnecessary stuff. It's entirely explanation itself, which we right now saw. Let's see the code. So firstly, I will make 3 semaphores. One is the 0 semaphore, another is an even semaphore, another is an odd semaphore. 0 semaphore will have 1 permit, but others will have no permit in the very beginning. Then my 0 function, as soon as I enter here, obviously I will acquire my 0 permit, right? I will acquire my 0 semaphore. So when it is acquired, I should print no matter what 0. So its only task is to print 0. Now obviously this thing should keep on repeating, right? This thing should keep on repeating until when? So that's the reason we have this for loop. Because if you remembered, let's say if I say print 5, so I have to print up till 5, right? So I have 0, 1, again, just say as if I say print 2, simply print up till 2, right? That is what exactly you are looking for doing. So again, that's the reason we have this for loop here. But obviously, if we ignore this for loop, the main thing here is that we will acquire the 0 permit as in, right? Then if it's odd turn, again, obviously printing is the main thing, but if it's an odd turn, release the odd semaphore. If it's an even turn, release the even semaphore. As I come on to, let's say, odd turn, I will firstly acquire that odd semaphore. Then I will print, the corresponding number. Again, it's an odd number only I'm printing right now. And then I will release no matter what the 0 semaphore only as I'm going out. Same way for even semaphore also, when it will come inside, it will acquire the even semaphore, then print the corresponding even number, whatever is right now, it has to print, and then release that 0 semaphore again. And that is simply how you can achieve it. The main task was here is figuring out initial states of all these semaphores. And also you can say, again, there are multiple ways to solve it. You can actually solve it by multiple ways. But this is going to be the most easiest and intuitive way for you to solve it. Cool. Now, I hope you guys got it. Again, if you want to see the corresponding diagrams and stuff, just corresponding state and exact same thing as what we showed you in the form of diagram above, the exact same you can also see as the diagrams down below. All these notes will be also available on the website. So no worries. You can just obviously anytime you can come up here. Although the notes will be visible here itself when the lecture will be live, although you can come up on the notes article as well, and here also you will see all the articles readily available. Cool. Now let's go on to the next question, which is going to be very interesting. Bye-bye. Now, hoping you understood the entire print 0 odd even, roughly same is going to be FizzBuzz. Let's see what exactly the FizzBuzz is saying. So FizzBuzz simply says that I have a print Fizz, which will simply print a Fizz. I have a print buzz, which will print a buzz. I'll have print FizzBuzz method, which will, print FizzBuzz. And I have print number, which will print the corresponding any number which you will give to it. Now, you have 3 functions, Fizz, Buzz, FizzBuzz, and number. What you are given is that you have 4 threads, thread A, thread B, thread C, thread D. Thread A will call the Fizz function, thread B will call the bus function, thread C will call the Fizz bus function, thread D will call the number. And again, it should ideally output Fizz, output bus, output Fizz bus, and then it outputs the corresponding integer. Again, this is what they can do. Now, again, whenever I say this, all these corresponding stuff, you can simply, again, I'm just giving you a corresponding glimpse that what exactly can happen. So you will see that print Fizz dot run. I can simply call this thing. Again, this is exactly what is given to you, that, print Fizz, just to print the actual output, right? This is not just, it is that whatever you want to print, you can print that actual output. That is what we are saying, that this will help you to print the actual output. Now, in order and what to print, this is what they are giving. They are giving 4 threads, and these threads are targeting their own specific functions. So this number function will target number, right? This Fizz will target Fizz method. This buzz will target buzz method. Again, this is corresponding thread, and this will target Fizz buzz method. So this is what they are targeting. Now, this thread, when it comes inside, this thread can call this print number dot run, and this can print the corresponding number, whatever I want. Now, what exactly is the goal? The goal is that you should be able to print a series like this: 1, 2, Fizz, 4, buzz, and then so on and so forth. Now, how you will print this? So you can simply imagine, I will print a sequence. Let's say if I give you n of 10, so you will print a sequence up till 10 numbers. If it is divisible by only 3, I will place a Fizz instead of it. If it is divisible by only 5, I will place a buzz onto it. If again, let's increase the sequence, right? Let's say 14 and 15. If it's divisible by both 3 and 5, I'll place a Fizz buzz instead of it. And then on other places, let's say here I'll place a number. Here it should be a Fizz, because it is divisible by only 3. It should be a number. It should be a number. It should be a number. It should be a Fizz, because it is divisible by only, it should be a bus, because it is divisible by only 5. Same way, number. This one should be a Fizz, because it is divisible by 3. Same way, this should be a number, this should be a number, and then this would be a Fizz buzz. So this is what you want to print: 1, 2, Fizz, 4, buzz, Fizz, 7, 8, 9, buzz, 11, Fizz, 13, 14, Fizz. This is your target aim. Now, exactly same as what we did previously as well, that you are given 4 threads. In the very beginning, you know that you have this target. The target is to print a number. Again, let's take the same sequence. Let's take this only sequence, and with that we'll be easily able to figure out what exactly we'll do. We'll first print the number. We don't want anything else to be printed. We only want this to be printed. What do you think we'll use? Obviously, we have a concert. We have 4 friends. We only want this friend to go inside and not the other ones. So we will say that, bro, you have no permit, you have no permit, you have no permit, but you have 1 permit. You can go inside and print your number. So what he will do, he will peacefully go inside the function, its own method, and acquire that specific permit. The permit will become 0. Now I have no permit. Now as it goes inside, he will print the number first, right? Calling the corresponding print number, right? It's a simple runnable. It can simple run. And then it has to go out. Now the challenge, or now the question for you guys is that when it goes out, obviously it should release someone's permit, right? So that something else could be performed, because now these are still stuck. They don't have any permit. But now as it goes out, it has to release. Let's ask, okay, I have to again print a number. So when it goes out, it will release its own permit. Yes, it makes the permit as 1. Then it will come back again and can again come inside this specific method. It comes inside, print the number, and then again trying to go outside. When it's again trying to go outside, then the question is which permit to release, right? Which permit to release? obviously in this case, we realize we have to release the Fizz permit. So I should go and release the Fizz permit. But how, Aryan, how did we know about it? As simple as that, because it is the number based. You can simply see, if you can simply have a for loop as what you were doing in the previous question as well, right? You can simply iterate on your I, and then if your I mod 3, right, if the I is divisible by 3 and is not divisible by 5, then I can release the permit of Fizz. If it is divisible by 5 and not by 3, I can release the permit of Buzz. If it is divisible by both of them, I will release the permit of FizzBuzz. If it is not divisible by both of them, then I will release the permit of my own number. Now, my number was currently 3, right? Because this is the third step. So in this case, I will release the permit of Fizz. Right now, as it released, it will come inside. Obviously, when it comes inside, it will consume that permit. Obviously, it is also gone. It will consume that permit, and then he will print Fizz and then go out. Now, when it goes out, whose permit he should actually increase? Again, going back to the same thing, he should increase the permit of 1, because obviously we know that number is the one who will print. So I should go and increase the permit of number. So the deciding factor, again, what if Aryan, now you might ask Aryan, what if you release the permit of this person, but what if after Fizz I want to directly print, let's say, Buzz? What if? No worries. Then what I will do, I will let it come inside, and because I have a for loop and I have this if else condition which will decide on all these conditions, so with all these conditions in my mind, I can decide which permit to release. So technically, you can still imagine that this as a pit stop. It will come here, decide which permit to release, and then release that permit. So everyone else, Fizz, Buzz, can simply increase the permit of my number. Number will act as a printing machine also, printing the number along with the decider, the controller, that I will control who can get the next permit. Although if you want, you can actually make another controller as well, but it's unnecessary because you will have to call that function from somewhere, because you only have 4 threads which are given to you, right? So that's the thing. I will make my number itself as a controller. So now Fizz will increase the permit. He will come inside. He will check the current number is 4. Now 4 is not divisible by 3, not by 5. So okay, I will just print the number, and then as I print the number, I know the next number ideally would have become a 5 in this case. If it's a 5, I know that I will have to go and increase the permit of Buzz. As I increase his permit, obviously he will come inside his own function, he will print Buzz, and then he will go outside and he will increase the permit of, permit of number. Then obviously now my corresponding count would have reached 6, and now I can just simply repeat the process. Right now, let's see the code. It's exactly same as what we discussed, that we will have 4 semaphores now: number semaphore, Fizz semaphore, Buzz semaphore, and Fizz Buzz semaphore. Obviously only number semaphore has 1 permit, rest all of them has no permit, 0 permit. Now let's come on to the number first. So number will simply iterate on the number and will keep on going. Again, you will see that all of them also will have to iterate, because they will have to keep on going and printing until they can print. So that's the beauty, because obviously I'll just simply call that and it has to keep on, like my thread will simply be called. It is not calling again and again. It will be called once, and then your task is to keep on printing until you can print it. So again, you can keep a while loop as well, and you can keep that someone will inform as soon as things are done. That also you can do. But again, simple for loop up to a fixed step, you want the thread to check in, you can do that simply. Now, what will happen? Obviously, the number semaphore will acquire 1 permit. Then he will decide which one to release. Should I release a Fizz Buzz? Should I release a Fizz? Should I release a Buzz? Or should I release myself? And again, when I say I will release myself, I should actually ideally print it. So I'll simply print it. Now, in any of the case, I will simply release one of the person. If I release myself, I will come back to myself and then try to figure out again what I will do. Now, but again, at every point in time, you will see that I will always keep on moving ahead.
So you don't have to worry about that, oh, Aryan, what is the value right now? No worries. I will always be moving ahead. So that is pretty chill here. That's the same thing, right? If I call Fizz, then Fizz will try to acquire the corresponding lock. It will print Fizz and then it will release number only, number semaphore only, because that's also acting as a controller for you, right? Then again, my buzz will try to acquire its own lock or acquire its own permit, print buzz and then release my number semaphore. Same way, my Fizz buzz will try to acquire it, print Fizz buzz and then again release it. That's exactly how this will happen. Now again, for the folks who had even a slight doubt of understanding, please make sure that you watch print 0 odd even. It's a bit easier problem. Even if you have doubt in this also, then only watch this one video of semaphore. You'll get everything into it. Cool. I hope you guys liked it. We'll next go on to design bounded blocking queue. Now let's step up a game a bit, and now we'll go on to design bounded blocking queue. Although, like again, all these are Leetcode questions. I hope so you guys remember when we were talking about Semaphore, we were discussing about producer-consumer problem, right? That's exactly the same thing we're gonna implement, which is a thread-safe bounded blocking queue. Why this is bounded, why this is a blocking queue? Because we will have to, we'll have a simple constructor saying, I will give a corresponding capacity. Capacity of what? Basically, there will be a queue with this defined maximum capacity. I cannot insert more elements than this capacity. I cannot extract out if there are no elements at all. This means I will have an enqueue method, which will, again, imagine it's a queue. So I will simply enqueue. In queue, inside this queue, I'll just put some element. So it will add the element in the front of the corresponding queue. So as I add it, this will simply go in the corresponding front. Now, obviously, if the queue is full, that's a very important thing. If the queue is full, the calling thread should be blocked. If that, say, the queue capacity is 3, I cannot insert more elements, obviously, if it's full. And again, there's another one which is dequeue. Obviously, from the last, extract out the corresponding element. So I will return the rear element of the queue and I'll simply remove it. Now, if the queue is empty, make sure that the calling thread is blocked until the queue becomes no longer empty. So if it's empty, it has nothing, then this calling thread should be blocked. It should not fetch something if it is already nothing here. That is the beauty of my dequeue. And then size, we should simply return the size of the current state of my queue. Now, with all that said, you will have some number of producer threads, some number of consumer threads. Producer threads will be calling enqueue, consumer threads will be calling dequeue. Your task is to write that corresponding multi-thread application which satisfies these conditions. This is for enqueue, this is for dequeue. Again, size is pretty simple. I can simply return the size. So size is not a big deal. The primary deal is enqueue and dequeue. And if you guys have remembered about producer consumer problem which we have seen in Semaphore portion of this crash course, then it should be very easy for you. If not, then please go and watch that video. Now, we will take the example which is already given, right? So we'll take a better example. So we'll say I have 3 producer threads and 4 consumer threads. Now, at every step, I'm gonna do a bit of diversion from the main problem by adding more threads so that I can explain what exactly could go wrong if you don't use XYZ stuff, which we're gonna discuss right now. Now, we are seeing we have 3 producer threads. So all these threads are producing simultaneously. All these consumer threads are consuming simultaneously. Now, in the very beginning, you defined the capacity as 3. So this queue will have a capacity of 3. Right now, there's nothing there. So whenever I will put something, I will put it like right? This is how I will put it. And then I want to remove it. I will simply remove it like this. Now, let's see how we'll go about it. So it initially says that I will have to enqueue stuff. Enqueue, then dequeue, and then enqueue. And ultimately, in the last, I will get the size as well. What's the corresponding size currently? Now, before we go on to replicating what exactly we are doing, let's talk about some things.
Forget about whatever is here. If you remember, we earlier talked about, let's say it's a simple buffer. A simple buffer, although we will take exact data structure as well, but right now imagine it's a simple buffer. You want only capacity number of insertions. Again, right now, let's hard code the capacity to be 3. So capacity right now is 3. So I want at max 3 number of insertions. Even if there are 5 threads, 5 producer threads, still I only want that. Imagine, again, let's keep this as a buffer. So imagine this is a buffer. So I only want that only 3 threads can come inside for even inserting data to my corresponding, this thing, which is the buffer. Now you might ask, Aryan, but what if you already have 2 elements here? Then yes, in that case, I only want to allow only 1 thread to come inside this buffer. Again, when I say come inside, which means to actually start inserting some data actually inside their data structure. So what we realize is that even if right now we have 5 threads, but only 3 threads can actually come inside to ingest data because I have only 3 empty slots. So empty slots matter. In the beginning, I have 3 empty slots. Again, empty slots will tie back directly to the capacity. So if I have 3 empty slots, only 3 producer threads will be able to come inside to insert some things. Now, why can't I let 4 threads come inside to insert things? Why? Because if 4 threads come inside and if all of them 4 try to insert it, obviously we will talk about later on what that data structure should be, this actual stuff, this pink stuff. But if 4 thread come inside, I know that only 3 is the capacity. Obviously, I will override something or I will not follow my condition, which was that if the queue is full, the calling thread should have been blocked. But I did not block it. I allowed it to come inside, which is wrong. So it's a reason I should make sure that how many empty slots I have, only these many number of threads I can allow it to enter inside my section, critical section. Now, same goes for the calling thread, right? If I will say my fill slots in the very beginning, nothing is filled, it's 0. So no thread can actually come inside. When let's say 1 is filled, only 1 thread can come inside to consume. When 2 are filled, only 2 threads can come inside. When 3 are filled, 3 threads can come inside. Obviously, the max fill can be the capacity size, so there cannot be 4 fills. So obviously at max, only 3 threads can come inside. And that is the beauty, how we will make sure that we are actually incorporating that blocking behavior, even if it's a DE queue. Because if the queue is empty, you should not be consuming, because if I let 4 threads come inside, I know the capacity is only 3. Let's say 3 of them consumed it, 1 of them remained. Then what? Obviously, I did not block it. I had to block it. Now, this we discussed about blocking these threads, and we have correctly shown it. Can you think of what exactly can we use? Out of all the concepts which we have studied, can you think of what exactly we can use? Although in the very beginning itself, I gave a very big hint. We have already covered the same problem, right? Yes, it's a simple producer-consumer problem, which you've already covered. And again, like the best part is we will actually discuss the LLD version of this problem as well when we will be discussing about Kafka. And again, in that I will show you a more beautiful version of it. Again, that's going to be a bit more beautiful and in a bit different way. Now, again, because obviously this will be kind of repeating if I show you, same thing again and again. Now, coming on back, what we will use. Can you remember of any of the things which you remember that if let's say there are 5 people, but I only want 3 people to go inside, I will simply give them tickets. So I will give them permits, which means I will use Semaphore here. So what I will do, I will simply say that I will use Semaphore. Now, again, when I say Semaphore, but for Semaphore, you have to give some number of permits. Same way for Semaphore, you will give some number of permits. Can you think of what the permit will you give in the very beginning? Imagine that you have everything is empty. So empty slots you have 3, full slots you have 0. So what will be the number of permits you will give in the very beginning to your producer threads? You will give 3 semaphore because you have 3 empty slots. And if I ask you about consumer threads, you will give 0 semaphore because you have 0 fill slots. So this is in the very beginning how the scenario will look like. Now again, this is a very good progress if you have made it so far, and if you were able to think of even this thing, you are literally genius. Now, because again, this thing confuses people a lot because they try to cramp it, like they just try to go about, okay, no, like I have to learn. No, it's a simple understanding. I have 3 empty locations. My 3 producer thread can come inside concurrently, so I can allow 3 permits. Obviously, there's nothing inside in the very beginning, so no one can consume. Obviously, I should allow no permit. That is how I can simply make it. Now let's proceed ahead with the actual problem. Firstly, let's say I have made the capacity. Now I got in queue operation thrice. So 1, 0, 2. So 1, 0, 2. But obviously, this would have come up first and then this, right? Because obviously I'm giving operations. So if there are multiple threads, they can perform this thing simultaneously, but obviously it will come, okay, 1, 0, and 2, and then correspondingly 2. Now, if 1 came inside, then let's say 0 and then 2. Now, if you had a simple queue here, then can you think of anything which could go wrong? Can you think of anything which could go wrong? Obviously, you allowed 3 threads. So semaphore only the semaphore only took care of the part that if you have 5 threads, you will only allow 3 threads. But still, these 3 threads, if they will try to access a data structure which is not concurrent, it will give you corruption issues. So if I have a simple queue, and then if I try to insert data, right? Obviously, because it's not a concurrent data structure. And again, if you don't know about concurrent data structures inside Java, please check concurrent collection video. Now, we know that obviously one way is to take a lock on this. We realize it is not good. It is not good practice to take a lock. Rather, we have concurrent data structures, concurrent collections in Java, which we can use. So again, there's one way. One way is to actually take a lock on this entire queue. If you make a simple queue, you can take a simple lock on it. That also will work, but it's not efficient. Efficient will be to actually use a concurrent data structure. In this case, we can use a concurrent linked queue. Again, usually I always try to use a DEQ, so I will use a concurrent linked DEQ. With that, what will happen? Now, although we have 3 threads, again, semaphore is restricted number of threads. But now, even if I have 3 threads, I can perform that corresponding task synchronously. And that is the beauty. I will take my data structure as concurrent linked DEQ. Now, let's proceed ahead. I will firstly insert 1, right? Then my 0 will be inserted and then my 2, right? Then I will call DEQ, right? Thrice. So DEQ I have called. Now, obviously, as and when things were inserting, obviously, the corresponding producer thread was consuming or acquiring that permit. So obviously the permit will decrease as and when things go. So let's say when 1 came up and then tried to use it, the permit decreased to 2. Then 0 came up, tried to use it, the permit decreased to 1. Then 3 came up, the last thread with the value of 2, it used the permit, and now the permits are 0. Right? Now, the permits are 0. There are no more permits here. Again, forget about this now. This is only useful for the initial state. Now you have no more permits remaining because your queue size is full. You should not insert anything now. But as and when you are inserting things, do you see that something should have changed? Yes. When you inserted 1, you consumed 1 producer permit, but obviously you should increase 1 subscriber or consumer permit. You consumed 1 producer permit, but you should increase 1. You consumed 1 producer permit, but you should increase 1 consumer permit, because now the consumer can actually my consumer can actually consume some things. Now same way, when 0 came up, I consumed my producer permit, but I should increase my corresponding consumer permit. Again, for me, consumer actually is actually, keeping that stuff in which I think, okay, did I say something wrong? No, I was right. That's what I just keep on pausing right now. Good. Then when 2 came up, it will consume the producer permit. It will become 0, but obviously it will increase the consumer permit. Now, when I tried to dequeue, I realized, yes, I have 3 permits. So one consumer will consume a permit, and then it can consume things. It will dequeue things from the last. This is gone. And when this is gone, my producer permit will increase, right? So you see, producer will consume its permit but will release consumer's permit. Consumer will consume its permit but will release producer's permit. This is also what we saw in the producer consumer problem, right? And then let's say this is consumed. Now I have to two more consume, so I'll just take one more permit. When I take one more permit, I will consume it, consume 0, and when I consume it, I will increase the producer permit because now there is more space, so producer can produce more. Same way, I can consume one more, I'll consume one more, I'll consume this, thus my producer permit will increase. Now obviously I cannot consume anything because I don't have any permit, so I'll stop. Now next is enqueue. Obviously I have 3 permits available. I'll use one of the permits to enqueue a value of 3. I'll enqueue a value of 3. I'll use one permit. Now one permit is done. So whenever any DEQ can call, let's say I call DEQ twice, okay, only one of them will actually get the call, accept the call, because as the producer did, it decreased his permit, but it will also automatically would have increased the consumer permit. So I know I can actually use one consumer to consume one thing, just indicating I have one thing in my corresponding queue which can be consumed. Now with all that in mind, let's see the code. So you realized that the benefit of Semaphore is to control the number of producers and consumers based on the capacity of my buffer, and to make sure that buffer don't go in the corrupted state. Rather than using locks on top of it, I can use it, though it's completely fine. Rather than using locks on top of it, I used a concurrent collection, and that is the entire beauty of this question. Cool. Again, if you want to read all this stuff, you can read it. Everything will be available on the website as well. But let's see the code. It's pretty simple. Firstly, I made a full semaphore and an empty semaphore. If you remember, empty semaphore initialized with a capacity of buffer, and full semaphore with a capacity of 0. As in the permits are 0, here the permits are capacity, because in the very beginning I have capacity number of full slots. So producers can produce capacity number of things. Consumer cannot consume anything because there is nothing. So it's the reason we just initialized with the corresponding value. And here I took my concurrent linked DEQ as a concurrent collection. Now, whenever I will do an enqueue, I will try to acquire an empty slot, because again, to enqueue something, I need to have an empty slot. So I'll try to acquire my empty semaphore. I will push something at the first, into my DEQ, and then I should make sure I should release my full semaphore. Why? Because now I have something inside, right? So release one corresponding slot. For consumer, same way, when I do a DEQ, I will firstly acquire my full semaphore, which means I'll use one permit for my full semaphore. Then I will get the result from the last, and then I should make sure, because I consumed something, the slot becomes empty. With that, I should increase, or I should release my empty semaphore. And again, size is pretty simple. Just get the corresponding size and simply return. It's completely fine. We don't have to take any of the corresponding one, but again, it's obviously concurrent linked DEQ, so it's perfectly fine on everything. We can simply do multiple reads on top of it. And with that, you will be simply achieving one of the most beautiful problems of all time. Right? Again, it is called as blog,
your producer consumer problem, it is called as Kafka, it is called as bounded blocking queue, it is called as multiple things. But again, there are slight catches. This is a very straightforward problem, right? Simple one buffer and then multiple producer, multiple consumer. But you will see there's an advanced version of it, which you will see as a Kafka, right? And with that, you realize how beautiful these things are. Now, with that said, let's go on to the next problem, which is again a very famous problem, dining philosopher problem. Again, using the same concept of what we have been seeing, but always using the same thing from scratch. Let's see the next problem. Now, after seeing a lot of easy problems, let's go on to a bit harder problem, but this is a very famous one. Dining philosopher problem. Again, I think that you guys must have read this problem in your CS syllabus, but yeah, let's continue here with fresh knowledge. So it simply says that you have 5 silent philosophers. You know, 1, 2, 3, 4, and 5. Right? Again, this is a very standard problem. So we are saying we are taking only 5, but you can have more as well. So it doesn't necessarily mean, okay, this problem is only applicable for 5 philosophers. It can be applicable for n philosophers. But to generalize the standardness, we are taking the standard problem. 5 philosophers only. They're sitting in a round table. As you can see, this is a round table. Now, why exactly a round table? Because you will see that they will use these forks. And you know that these are also 5 forks only. 1, 2, 3, 4, 5. And also they have corresponding spaghetti bowl. Right? They like spaghetti. I don't know why. But yeah, all of them will have their own bowl as well of spaghetti. So I have placed forks. You know, forks are placed between each pair of adjacent philosophers. This is the placement. And also the philosopher must think, eat, think, eat, think, eat, and so on and so forth. Now, any philosopher can only eat spaghetti when he has both the forks, both the left and the right fork. Whenever he has it, only then, again, mark my words, only and only then he will be able to eat that spaghetti. Right? Now, obviously, the fact is that each fork can only be handled by one philosopher at a time. So, if he wants to eat, he will pick these forks, these 2 forks. He will pick, and then he will eat. Obviously, when he's eating, which means he's holding the fork. When he's holding the fork, he cannot obviously take the fork or maybe use the fork. No, when he will keep the fork down, then only the other philosopher can actually take it. And again, any philosopher will eat the adjacent fork, which whatever forks are adjacent to him. Now, again, it is basically a fork can only be used if it is already not being used. That's a fact. Now, after eating, I should make sure that I am obedient. I will put both of my forks down. Now, these forks, when I will put them down, now then these will be available. But again, after eating, I will eat and then put those forks down, and then these will become available for the further forks to actually start eating. And again, philosopher can take either of the forks whenever it becomes available. So obviously, let's say if this is a philosopher, he will take any fork whichever becomes available first. It doesn't necessarily mean that he will take left first and then right. No, he can take any fork whichever becomes available first for him. Okay. Now, but obviously, I cannot start eating until I have both the forks. That's a primary requirement which I have. Now, ultimate aim is that no philosopher should starve. Now, what is the starving logic which you have already seen before? It's a simple deadlock, which means there should not be a deadlock scenario. Now, by this time, you must have already thought of a scenario. The scenario is, what if this philosopher picked the left fork? This also picked the left fork. And again, imagine that all of them picked the left fork simultaneously. Let's say this one also picked the left fork, this one also picked the left fork, this one also picked the left fork. Now all of these philosophers are actually looking for the right fork, but they cannot occupy it because someone else has already occupied it. So, can I say one thing for sure? That all 5 philosophers can never eat simultaneously.
all 5 philosophers can never eat simultaneously. So, how many philosophers can eat then? Can you guess? Obviously, I know that as soon as I can have one fork free, I can eat it. So, I can simply say that 4 can eat simultaneously. Again, when I say simultaneously, at least they can try eating. So this one, let's say this person will not eat. Let's say this person will not eat. So he will pick this fork, right? Let's say he also picked his left fork. Let's say he also picked his left fork. Let's say he also picked his left fork. But considering this person is no more eating now, this person can easily acquire one more fork. When he acquired, he will eat, and then when he will eat, he will release both the forks. Now, when he will release this fork, obviously he will pick up this fork, and then he will start eating. When he will eat, he will actually eat, finish, release the fork. As he releases this fork, obviously he can start eating. As he will eat, obviously he will release both the forks, then he can eat. And when obviously he eats, he is done, he'll release both the forks. And considering I was saying 4 at a time, now obviously no one is eating. Even if these 3 were remaining, still I could have allowed him. Now he can also participate, and again he would have picked up this fork, but then he would have been waiting for this fork because it was, let's say he was eating it. Then as soon as it is available, he'll also eat it. So one thing we realized, that obviously, so that they don't reach a deadlock kind of a scenario in which every philosopher is waiting for every other philosopher, I'll make sure that I will only allow 4 philosophers at a time to enter my table. Again, I'm saying 4 philosophers at a time. As soon as one of the philosopher eats, whenever, let's say, when one person eats and then goes away, obviously then I have luxury. I can bring the other person in, but I will only bring 4 at a time, such that again it can be anyone who goes outside, but I will bring only 4 at a time, such that no one goes into starvation and everyone can keep on eating, thinking, so on and so forth. So again, by so far you must have thought of that what you will use to implement it. Did you see one thing, that you have 5 people, but you only want to give tickets to 4 of the people? What you will use? Obviously, you can use Semaphore. Same concept. I will give 4 permits, and then these 4 permits, any of the 5 philosopher will try to get the permit. Whoever will get the permit can come and sit on the table. As soon as they will eat, again, right now I am saying table, but again, when I say table, when they come onto table, they want to eat. Imagine like that. So although you can argue that Aryan, all of them are sitting on the table, so why are you saying coming on the table? Just so that you understand that they are having this permit, only 4 can come and sit on the table, so that I can discard one of them is not even here. I'm just kind of ignoring him altogether. So what will happen? 4 people will get the permit, so only 4 people can actually come and sit on the table, and with that I will be ignoring any one of them. Again, anyone who could not, because obviously for all the philosophers they will have their own corresponding thread, so they will try to take a permit. Obviously he did not get it, he was not lucky, no worries. Obviously next time he will try, because again, why he could not take a permit? Because my Semaphore only had 4 permits. These 4 came first, maybe again randomly they came and they were able to get the permit. When the permits are finished, no worries. Any philosopher, as soon as he will eat, he will remove or put down his forks. He will eat completely. Then he will go out. As you go out, he will increase the permit by 1. Then obviously he can grab that permit. So with that, again, imagine the same thing as what we have been doing for the past problems. Same concept we will use here as well. Now, although you have got the entire idea, let's see that how exactly we will implement it. So we have this function wants to eat, where I will have philosopher ID. I will have pick left fork. Now this is the function to pick the left fork. I will have pick right fork. This is a function to pick the right fork. Then I have eat. This is a function. When philosopher has both the forks, then he will start eating. Obviously, after eat, he has to put both the forks. So this is a function to put the left fork. This is a function to put back the right fork. Now, you have 5 threads, each saying for each individual philosopher, as we also mentioned previously. Now, all these philosophers will simultaneously use one object of my class to simulate their dining process. And again, as mentioned, that all the philosophers will have their own ID. Now, when I say they will have their own ID, I can simply figure out corresponding fork for them. So I can simply say that go and do philosopher and philosopher plus one to get the corresponding left and right fork ID. What I mean by that is that here I can say, let's say here I can say the fork ID is 0. Here the fork ID is 1. Here the fork ID is 2. Here the fork ID is 3. Here the fork ID is 4. So for this philosopher to get the corresponding fork, obviously it will be left and right. So it is same plus 1. For this one, 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 it is same plus 1. But again, it is a round table. So I will do plus 1 mod by the round table size, which is 5. And that's how I can easily figure out for any philosopher which of the two forks they are looking for. Now, with all that in mind, can you tell me that how exactly you will implement it? Now, you know that you will use Semaphore, obviously. And obviously, you will also realize that Semaphore number of permits you will keep as number of philosophers minus 1. So, you will keep the permit as 4. Okay, you will use the Semaphore. Now, Semaphore will only guarantee that only 4 philosophers can come at a time on the table. Is this sufficient for you to solve the problem? Not really. Because imagine that this person could not take the permit. So 4 people came inside the table. Now they will start eating, which means this person will take the fork. This person will take the fork. As soon as this person takes the fork, obviously the other person cannot take it. What is this scenario when any one thread comes inside, and when he comes inside or take it, other person cannot come inside or cannot take it? That is called as my lock. So obviously this philosopher will apply lock on the left fork and on the right fork. Then he will eat peacefully. Then he will release the lock on the left fork and then the right fork. Thus, any philosopher, before they start eating, they have to apply lock so that no one else can take it. Else, what will happen? Again, what if he does not apply the fork? What if he does not apply the lock? So let's say if he does not apply the lock, and let's say if it is empty, he does not apply the lock. The moment he will go on the other side, oh, here the fork is available, then he will pick it. But in that meanwhile, this fork would have been gone. So obviously for him, he knows that if he got on the table, ultimately he will be able to eat. So what he will do, he will simply see that, apply a lock, take it. See that, apply a lock, take it. Now he has both the forks, eat. As soon as he's done eating, release the fork. Release the fork. And now go out, which means increase the permit back. That is exactly what you will be doing. So you realize that you will use Semaphore to let only 4 philosophers come in, and then you will use locks. Again, I can use a binary Semaphore as well to indicate the corresponding locks on individual forks. Or if you want, you can explicitly use locks as well. But again, we learned in our Semaphore lecture, that we easily can have the corresponding locks as binary Semaphore as well. And that's exactly what we'll be using. Cool. Let's see the code. It's exactly very simple. Again, although this is kind of what I've shown as an output, which you can just figure out if you're doing or solving on Leetcode. But again, it doesn't matter as such, because yeah, why not? So again, just to give a quick recap, we will prevent deadlock. We will ensure that no philosopher is actually starving, and I can actually handle concurrent access to my shared resource, which is forks in this case. Again, fork, like it's kind of how you pronounce it. Now, so what will happen? Obviously, in my constructor, I will initialize my semaphore count. That semaphore count will simply say that, bro, you have 4, which means you have 4 permits. 4 philosophers can come up. Again, if you think that the person is asking you to actually have it as a variable, no worries. If it's a variable, then you will try to put the semaphore count as number of philosophers minus 1. Now, obviously, we also want a lock on each fork, so we will have a binary semaphore saying all 5 forks, I will apply a lock on them. Now, the function is wants to eat. These are all the same things which you saw, that philosopher ID, pick left fork, pick right fork, eat, put left fork, put right fork. So firstly, before I enter here, I know only 4 threads can enter. So all of them will try to acquire a permit. As soon as they acquire, now the philosopher will figure out his left fork and right fork ID using the same concept as I showed you above. Then obviously they will figure out what exactly is the left and right fork semaphore so that they can take a lock on it. As soon as the lock is taken, they will run picking, again, this run indicates the simulation of picking a fork, right? So this will indicate a simulation of picking the left fork and then picking a right fork and then eating and then putting the left fork back. Obviously, as I put the left fork back, it is much better that I should release the lock on the left fork. Same way, I will put the right foot back. I will release the lock on the right fork. As soon as I have put both the left and the right fork, I am done eating. I will go out of the table so that someone else can come and start eating. Although I will also come back, but again, I will let others get the equal opportunity of coming in my, coming on the table. And that is the entire piece of code having about it. Although there are multiple ways of how you can implement this tiny philosopher problem, but this is the most easiest and intuitive way to go about it. Cool. Next, we will see another great problem, which is multi-thread web crawler. It is a most important interview question, like literally the most important. Although it's a premium question on Leetcode, but we will see the entire question with this explanation. Let's see now. Now, after tackling all the known problems, we will go on to a unknown problem, which is multi-thread web crawler. This is a question which is very important in terms of if anyone wants to ask you one simple straightforward question of multi-threading, they will ask you this question. That's it. This is not famous, people don't know it, people end up confusing, and that's where this video comes in. Now, the problem is that you will be given a start URL, right? Again, obviously, I know that you guys know what a URL is. If not, then you will see that this is, this is a URL. https://corevariant.com, then system design, then low level design. This is a URL. Now, with that specific start URL, you will be given, and you will also be given a interface called as HTML parser. What that actually means is that imagine you go on to any URL. Let's say you go on to corevariant.com/techblocks. This is a URL. Or maybe let's say you end up being, okay, no RL. I will go on to another URL. Let's say I'll go on to corevariant.com, let's say /techblocks, design splitwise. Now in this, wherever there is any other URL, right? So I'll just simply go through it and I'll find out if there are multiple URLs. Obviously, here you will see there are different URLs which will be there. So what this interface HTML parser will do is it will parse this specific web page, extract out the URLs from this page. That is what this HTML parser will do. Now, what you have to do is you have to implement a multi-threaded web crawler. What do you mean by web crawler? Web crawler is that I'll give you a start URL. I'll go on to a page. I'll crawl that entire page. I will find out some new URLs. I'll go on to those, let's say, new URLs. I'll again extract out, I'll again crawl through this page. I'll extract out new URLs and I'll keep on repeating this process. This is a web crawler, that you have a start URL, you have a page which you will visit. You will visit this page, you will find multiple other URLs being linked. Then you will go on to this URL, click it, again start parsing it. You will again find some URL, again go there, again start parsing it or crawling it, again find the new URL, and so on and so forth. This is how exactly your web crawler works. Now, obviously your task is to crawl all links under the same host name, which means that if, let's say, I start crawling my website and I give you this URL as the beginning URL, I'm only asking you that crawl everything from codevariant.com only. If there is anything, let's say leetcode.com, don't crawl it. I only want to crawl, let's say, one specific host name. That is what they are saying. And again, host name, that specific host name will be derived from the start URL. So if my start URL in this case is codevariant.com/techblocks, the host name will be codevariant.com, and this is what I have to crawl only and only. And ultimately I have to return all the URLs which I obtained via crawling. And again, the order doesn't matter. I can give in any order, whatever I want. So did you realize that what exactly you have? You have a start URL. Then obviously you have a HTML parser in which you can just simply call get URL, pass in the URL. This will literally parse the entire web page. Its duty is to parse the entire web page and give you a list of URLs. This will parse the entire web page and will give you a list of URLs which were present on that web page. Now again, you can individually start crawling them, but that's a different game which you will do, as you will keep on crawling. The task is you should not crawl the same thing twice, else you will run into infinite recursion. Obviously, right? If this page links back to, let's say, this home page, then if you will end up crawling this again, you will crawl this again, then crawl this again, crawl this again, crawl this again, then again, and you will loop into infinite recursion. So it's the reason you should not crawl the same link twice. When I say same link, I mean same URL twice. Obviously, as you explore links, make sure that you are exploring under the same host name, whatever is codewitharyan.com. Codewitharyan.com. Only explore under this host name, that's it. Again, as I mentioned, the host name is this. This is the entire host with the corresponding port. I am not concerned about other things. Now, they are just giving what's exactly a host name. This is same host name. Obviously, this is a different host name because the host name is different. So HTML parser is the corresponding interface. As I mentioned, I will just give him some URL. He will parse in the entire page and will return me a list of URLs. Make sure this is a blocking call, which means this call will take time, and whichever thread, again, whenever I say thread, I hope so you guys have been following series so that you know what a thread is. It's kind of that you will ultimately be calling. If anyone is calling it, it will be calling internally via some thread. Even main thread, it's also a thread. So whoever will call it, it will block that call for some time until this process completes. So what we realize, it's actually a blocking call, and you have to wait for the request to complete. Now they are also mentioning that if you start processing it via single thread, you will not, or you will exceed the time limit, or you will not complete in time. So you will obviously have to make sure that it is multi-threaded. Now what I mean by that, when you will do it by single thread, is, for example, obviously in the very beginning, imagine you have only one thread, right? Now you will get the start URL. This one thread will start parsing this, right? It will go and send it to HTML parser. Then when I say send it, which means this thread is doing all the job. It will send to the HTML parser and then it will start parsing it. It will get you two URLs which links it to this URL, right? So when it is done, let's say again, I'm taking hypothetical number. Again, although if I go up, it is, it is taking 15 milliseconds. Okay, no worries. So I'll take, let's say 15 milliseconds. So it took 15 milliseconds and then it returned back with the two URLs. Now, considering I have only one thread, so I know it is two URLs, I'll keep in memory, but I can only go to another URL. So again, my T1 thread will go to this URL. Now again, it will parse the entire web page. It will again take 15 milliseconds and again will parse it entirely. Then it will get, after parsing it will get another URL. Let's say this one. Okay, no worries. It will go on to this URL now. Again, let's say this is done. Another, the same thread T1 will go to this URL now. Will now parse it, again take 15 milliseconds. Again, let's say when this is done, it has nothing else. Then it will go to this URL. The same thread T1 will parse it, take 15 milliseconds. And then obviously here it doesn't point to anything else, so it is done. So you realize it will take 15 plus 15 plus 15 plus 15. It took 60 milliseconds. Can I improve it? Obviously I can. How? If you remembered, when this first call was completed, you instantly got two URLs, right? Now, when you were performing sequentially, you performed this first and then this first. But if I would have had two threads, can't I perform this parallelly? So these two will be executed parallelly. So earlier, when they were taking 15 plus 15, now I can execute only 15 milliseconds. He will execute in that same 15 milliseconds. So now when this is done, he will have nothing. But when this is done, he will have something else, which will again take 15 milliseconds in some other thread. Let's say T2 only, because by that time T2 will be free. With that, now I'm taking 15 plus 15 plus 15. I'm taking 45 milliseconds. Now you might say, Aryan, is just a 15 milliseconds difference, but it is for this very small example. But now you realize the importance of multi-threading. Cool. Again, this is just for you to know that this is how they have given the input. They have given the list of URLs and also they have given the corresponding edges, that how different URLs link to each other, and they have also given a start URL, right? And with that in mind, we know that we will get all the URL and the same host name as the start URL, right? As the start URL, and these are all the URLs which I can actually visit. Again, this example 2 as well, it's completely same. Now let's go on that how we will solve it. Again, we will take a bigger example. So now we realize that we have primary two things. We will be given a simple start URL. Now, obviously, they are saying that make it multi-threaded. Now, we have already seen that if we have multiple threads, we want to manage those threads. We use existingly managed service. So I can use a thread pool. Again, I'll use executor service, and in my executors factory, I can call a new fixed thread pool. I can call a new cache thread pool. I can literally call anything. But for simplicity and understanding, we will use a very common fixed thread pool. Again, if the folks who don't know, please make sure that you visit the previous section where we discussed about different thread pools. Now we have 5 threads, right? Again, I will say new fixed thread pool of size, let's say 5. So I have 5 threads which will be managed by my executor service. Now, in the very beginning, my task is take this URL and then call your HTML parser. Just pass in this URL. This will return you some list of new URLs which you will start parsing. That's your entire job. So I'll do the same thing. I'll say I have 5 threads. And then I am given some start URL. This is my start URL. I will be only given one URL. and then I have to get all the URLs under the same host name. So here I have put up the same color. Here means the same host name, right? Same color here means the same host name, the same number. Let's say you will see that U1 and U1, same number means the same URL itself altogether. Now, obviously in the very beginning, I have 5 threads. Obviously, to perform this job, I will take one of the threads, because obviously this is the first task which I'm going to perform, right? So I'll take one thread, will tell that one thread, bro, you come up here. So T1 came up here. I will tell him, bro, now I need to parse this. I need to parse this. So he will say, no worries, bro. I will call HTML parser. But before that, you should know that you have to parse one URL. So I'll increase the count by 1, which will indicate I have to parse one URL. It is still not completed. One URL still needs to pass, because again, you remember, it's a blocking call. So you have to make sure that you wait for the entire parsing to be complete. For that, I can maintain a count that, okay, how many URLs still needs to be parsed. So now my URL1 will go to HTML parser, which means this thread T1 will go to HTML parser. And then this is a blocking call for 15 milliseconds. The HTML parser will then return back 3 URLs, U2, U3 and U4. Now I know I have to again parse these URLs. So now I will increase my count by 3. So count increased by 3. Now the count becomes 4. So these are 4 URLs to parse. Now you might ask, Aryan, but like this URL is already parsed, right? So why can't you decrease the count? No worries, we'll do it. But let's complete the process first. So when the count increased, I haven't assigned any threads, or I haven't assigned the job to start. So I will say, okay, bro, one thread is already busy with me. So right, this is already busy. You take T2 thread, right? You take T3 thread, and you take T4 thread. So basically what happened here is this took my T2 thread, this took my T4 thread, and this took my T5 thread. And whenever I have assigned the task, now I know that I have assigned the task, again, even if there are no threads, still my executor service can handle the thread pool. Whenever a thread will be free, that task will be assigned. Which, for what I mean by that is, even if there would have been 100 of other URL spawning or inside this U1 web page, still my executor service could have handled it by just simply having fixed number of threads. So, which means that any thread which gets free will get back to my thread pool, and then my executor service will make sure that I am assigning the task from that thread pool. Again, all these logic of executor service, thread pool and stuff have already been discussed in the beginning portion, so please make sure that you watch it. It's important. Coming on back, we realize, okay, let's say these tasks are performed. Now T1's task is done. He got parsed completely, he got different URLs, and he have also assigned the task to different threads. Now this is done. So when this is done, it will go back to the thread pool. Now these all will happen simultaneously. So U2 is being parsed simultaneously, U3 is being parsed, and U4 is being parsed. Now when I mentioned that U1 task is done, obviously he's parsed. So make sure that you reduce the count by 1. The count now becomes 3, because you can see that 3 URLs still needs to be parsed. Now obviously U2, when it is about to get parsed, I will pass it to HTML parser, which will take another 15 milliseconds, and then will return the corresponding list of URLs, which will be empty in this case because there is no URL from here. So what will happen? Okay, no task assigned, and then this is done. So T2 is done. Now T2 is done. Do I have any other task pending right now? No, because there was nothing to do. But still, at the same time, when U2 was being parsed, same time T3, this U3 URL was also being parsed by my HTML parser. it was also taking in the same time, at the same moment, it was taking 15 milliseconds. But then this returned me another three URLs, U5, U6, and U1. So I will assign threads to it. So meanwhile, my T1 and T5 would have been there again, because maybe by that time T2 would not have had been free. No worries. My T5 and let's say T1 got assigned. So T5 and T1 got assigned. Again, it is possible that U1 is not assigned any specific URL, but before even assigning, I should check, have I visited the URL U1? Obviously, yes. So I have to maintain a hash map which will say that this URL is visited, true or false. Now, considering multiple threads can update the hash map, because as soon as, let's say, I visit U1, I will update it. I visit U2, I'll update it in my hash map. I visit U3, I'll update it in my hash map. So obviously it is possible that I update U3, which means I visit U3 and U2 simultaneously. So I should choose a hash map which can accept concurrent operations, and for that we will use concurrent hash map. This is what we saw in our concurrent collections portion of this crash course. So with checking of my hash map, I would know that I don't even need to assign a task because it is already visited. Now, considering I will be U3, U5, so U3 will get thread 5, U6 will get thread 1, and there is no thread assigned to this corresponding U1 because it is already visited. Now, obviously, meanwhile, when U3 was being parsed, my U4 would also have been started. So, obviously, before even trying to call a HTML parser from here, I should check that is it having even the same host name or not. Obviously, I realized it is not having the same host name, right? With that, I will simply say, okay, bro, you are completed. I will not go inside you. And again, as soon as everything was being parsed, the corresponding count was also decreasing. This is also done. The count becomes 0. Did you see one thing? That we used concurrent hash map because I was updating URL and if they were present or not with the help of, concurrently. But I can also, again, considering, let's say, both the URLs are parsed simultaneously, so both of them could go and decrease count simultaneously. So also have to make sure that this variable is atomic. So again, if you don't know what atomic is, again, I highly recommend, please go and watch thread communication video or the corresponding portion. You will get it what is atomic or what is volatile and how to use them. Now, coming on back, we realized that meanwhile, when they would have come up here, they would have increased the corresponding count to 2, right? Because 2 URLs still needs to be parsed. Now U6, again, I'll just keep it now short. U6 is already of a different URL. So thread 1 will actually, come back to the thread pool. Same way, again, other threads who would have been, completed, they would have already gone back to the thread pool. So that's one thing. Same way, T3 would have gone back to thread pool, and then my T5 would have parsed it 15 milliseconds, taken time, and then given another URL which will again get another thread, let's say T6 or let's say T1, and then with that it will also take another 15 milliseconds to parse it, and then it will complete the corresponding process. This is how, because of multiple threads, I can simultaneously run that parser on multiple threads, thus achieving the task. So you realized that you will have executor service in which you will do new fixed thread pool. You will use a concurrent hash map. You will use an atomic integer number of URLs to parse. Why this is needed? It is because I should not abruptly shut down my system considering I still have some URLs to parse. So this is why I needed that. I know I should only shut down when I have no URLs to parse at all. So you will see that we have used the same actual variables. So I've used a concurrent hash map, URL hash map, right? Concurrent hash map, keeping URL and if they're visited or not. I have used executor service saying use a new fixed thread pool taking 5 threads. Again, you can use a cached thread pool as well, but again, it's kind of much more, as I was also mentioning in the beginning, it is much more easier that you are using a fixed thread pool. Now, obviously, here I am using a number of URLs to parse as a variable, but keeping it atomic. Initial value is 0 because there are no yet URLs to parse. And this is my interface which is already given to me. Now, my actual function starts from crawl. I will be given a start URL and also my parser. Again, I just only have to, call that this specific corresponding parser. Now, firstly, I will extract out the host name from it because obviously I have to only deal with the host name if you remember, right? Then I will update my hash map that this URL is visited. Then I will say now I have one URL to parse. This is exact same philosophy as I was mentioning. This URL is visited, but now I am saying I have one URL to parse. Now I will simply submit a task to one of the threads and will say, bro, go and parse this specific URL. Now, considering I still have some URLs yet to be parsed, this will keep on going. Now, why there is a sleep? It is so that you will not unnecessarily do busy waiting. You will sleep and then run it again. Check, have you got it? No, okay, sleep again, then again. So with that, you will not unnecessarily waste your CPU. Now, obviously, if I wait sufficiently and there is still count of 0, which means my all URLs are parsed, then I can simply shut down, right? But I should not shut down considering until I have any of the URLs still yet to parse. Okay, one task or one thread assigned here. But the moment you call your new task, which means you will come into this run method, you will firstly do a blocking call. And this is for the first thread, for the first URL being parsed, it is a blocking call because I can only parallelize this thing, that I can pass the URLs to different tasks, right? Or I can use the corresponding multiple threads. So I will actually do this blocking call, get all the URLs, which will again this will take 15 milliseconds. I'll get all the URLs and then I'll extract the host name. I will check, is the host name which I grabbed here, right, which is a global variable which I kept it, is it, and again the crawl which I did and the URLs which I extracted, is the host name same? If it is same and also I have not visited it earlier, only then I should firstly increase the number of URLs to parse because it is important. I am extracting and parsing that URL, right? So I'll increase the count and then I will submit that URL. I'll submit that new URL to a new thread. Again, if the threads are not available, no worries. Executor service will actually handle on my behalf any new task. And again, if any thread becomes available and come back to the thread pool, the task will be assigned to that specific thread. Now, when all the extracted URL from that web page are done, only then I will say that I have completely parsed this specific web page. Now I should decrease my URL, number of URLs to parse count. Again, make sure that you do not decrease the count right here. Again, let's say if you're done, let's say if you are just extracted it, don't decrease the count right here, because if you decrease it, it can happen that before it comes down to the next step of increasing the count, you might have already gone out and shut down the system. So only decrease the count when you have entirely gone through all the URLs inside the web page, and also making sure that if they have to visit, assigning the task to them, or maybe assign the thread to them. And with that, with this very simple short piece of code, you can simply achieve your multi-threaded web crawler. Now, the beauty of Java comes up here only.
If you would have achieved the same thing in C++, it would have been a nightmare to handle things. But in Java, it's pretty much very clean, short and concise. I hope you guys got it. Again, you will see there's all, the entire dry run for the folks who are reading the article. There's entire multiple stuff, which is already mentioned here for you to just go through it. But obviously, I just want to explain with the help of an article, as in like with the help of a dry run here as well, because it's a bit tricky on how multiple threads access stuff. Now, I hope you guys liked it. Make sure that with the like target of 250 likes, the aim of this crash course is that we should be able to achieve 100k views in 1.5 months. Only then we will be proceeding ahead with making a similar course for HLD. And I bet the current course for LLD, there is no course right now in market, even free or paid, which can actually compete with this course. And I bet that portion. If you can prove me wrong, I'll give 1,000 rupees to you. Plain and simple. So, if it was helpful, this entire concurrency and multi-threading crash course was helpful for you, then please make sure that you like it and share with your friends. And see you next video. Then goodbye. Take care. Bye bye.